Okay, welcome to this video where we're going to be having a look through a question on every single topic that appears on the GCSE. Now in this specific video we are going to be focusing on looking at the crossover content. Now the crossover content is the content which appears on both the foundation and the higher paper. Now the video that I'm about to go through, you can download all of the questions in a practice booklet that you can work through. I'm just going to show you where you can find it. So if you head to the website, and the link for this will be in the description, you can head into the menu bar and it's in the free resources section. Now the one we're going to be having a look at is the revision guide, but there are loads of free resources that you can download here for free on the website. So you've got the practice papers, there are practice booklets, there's the ultimate revision guide and the revision checklist. Now we're going to be looking through the ultimate revision guide. As I said, we are going to be looking at the crossover content. So this one, if you are going to download it, is labelled as the foundation guide. It's the foundation guide because it's just the content that can appear on foundation, but also on the higher tier, there is also additional content that you will have to cover. So in this particular video, we are going to be having a look at all of the content that you need to get to a grade 5. So on the website, all you need to do is click on Get the Free Guide. You can then click onto the Foundation option, and that will download the revision guide for this particular video. If I show you what the revision guide looks like, we'll just have a quick look through that. So once you have downloaded the guide, you will be able to scroll through. You can obviously print this off, you can have it on paper, or you can have it digitally, however you prefer. And you can see that we're going to be going through all the units that are broken down here in the guide. So you can actually click on these if you're using the digital version. We can click through, let's go through to angles, polygons and parallel lines in unit 6. So we can click into that and it's going to take us straight down to this particular unit. So you can go through, you've got the questions, you have got some answers there upside down, and you've also got a QR code there that you can scan and it will take you to a full lesson on that particular video. So you can work through the questions if you want in the booklet, or if you prefer, you can work through them with me on the video. So at any point, you can obviously check back to the video to go through any of these if you're not exactly sure on how to answer any of them, but there are tons of questions for you to answer with one on every single topic that can appear. So for this one, obviously bear in mind that as we go through the questions, these are just one variation of each particular topic. So for example, if we look at this question here, which is volume of a prism, well, there are different prisms that you can look at. There are different prisms that you can work out the volume of. You could have a triangular prism. And as I go through the video, I do discuss all of these points with each particular question. But you obviously need to be aware that these are only one variation. Another good example here, we have drawing linear graphs. The equation there is y is equal to 3x minus 2. Well, of course, you could be given a graph which is y is equal to 2 minus 3x, and that would be treated slightly differently as well. So if you have the guide printed off, of course, if you want to check any other variations of the questions, you can scan the QR code and it will take you straight through. If you have the digital version, you can just click on that QR code and it'll take you straight to the video as well. So at any point, you can click this button here, it'll take you back to the start, and you can just go through the different units as you see fit to help with your revision. Now this particular video is going to be quite a long one because I go into the questions in quite a lot of depth. But if you want a quicker version, or for whatever reason you need a quicker video to go through, you can always head to the video at the top of my channel there, which is everything you need to pass your GCSE maths exam. That one there is a lot quicker. I do go through the questions a lot faster than I'm going to in this video because I'm going to go into quite a lot of depth for each topic. But if you do want to access a faster video, that is the video for you. But otherwise, we are going to be going through all of the questions, all of the topics, and we will go into quite a bit of depth on each particular topic. Now, before we get started, there are lots of resources that you can access on the website. If you head into the menu, you can obviously have a look around. There is now the grade check feature as well. So you can go into here, you can answer 20 questions, dependent on your exam tier, and it will give you a predicted grade in terms of a percentage that you get correct across this selection of questions. So that is definitely something worth having a go at. It won't take you too long, and that is really useful just for giving you a general idea of where you're at and some topics that you might need to work on. If you would like to join one of my courses as well, you can sign up to either Upgrade or TGMT Live. So if you head to the website, you can have a read for either one. TGMT Upgrade is the on-demand course where you can access everything that you need that matches everything in the revision guide. You can access full lessons, you can do bespoke quizzes for each of those lessons, for each of the units. You can get reports generated that tell you what you need to answer. It's an all-in-one package there just to have a look at everything you could possibly need to. You can also join TGMT Live, where you can join me once a week going through live lessons together, where you can interact with me as well, and we go through a bespoke schema work where we'll be looking at all the topics that you need to make sure that you are happy going into that maths exam. So there's a couple of things to have a look there. Both of them you can have a look and have a free trial, so it's worth going in, having a go, seeing if you like them, picking which one's for you, and if neither of those options are for you, you've got all of the free resources, you've got the grade checker. There's so much for you to have a look and explore on the website. So do make sure you click the link in the description, have a look and see if any of those are going to be useful for you moving forward. So otherwise, we're going to get started with the video. So let's get started. Okay, so looking at our first question, we have multiplying decimals. So if we have to multiply decimals, the first thing that you want to do is to remove those decimals out of those numbers. So we've got one jump out of the first number and another jump out of that second number, so a total of 2 jumps. We can then do 546 multiplied by 43. So essentially just taking those decimals out and treating them as whole numbers. From there, you can use whatever method of multiplication that you are comfortable with. I'm just going to use column multiplication. So 3 times 6 is 18, 3 times 4 is 12, plus the 1 is 13, and then 3 times 5 is 15, plus the 1 is 16. Put my placeholder in. 4 times 6 is 24, 4 times 4 is 16, plus the 2 is 18, and then 4 times 5 is 20, plus the 1 is 21. From there, we'll add these together as normal. So 8, 7, 14, carry the 1, 3, and 2. So we get an answer 23,478. But of course, we know that these were decimals. We need to put those 2 decimal places back in. So 1, 2, and we would get a final answer of 234.78. And of course, a good method just to make sure you put those decimals in the correct place is to imagine what the answer would be if you were to estimate this. So if we were to do an estimation, we would round 54.6 to 50, and we would round 4.3 to 4, and 50 times 4 gives you an estimate of 200. So we know our answer is going to be relatively close to 200. That's going to help us with that decimal placement as well. Okay, so looking at product of prime factors. So for this, we are going to write the prime numbers that multiply to make 56, and I do that using a tree. So for 56, we just need to think of any 2 numbers that multiply to make 56. One option that you could go for is 8 times 7. That's quite a nice one. It does give you a prime number straight away. If the number's prime, we'll just circle that number so we know we're finished on that part of the tree, and we'll continue on the 8. So 8 is 2 multiplied by 4. Again, 2 is a prime number, so we will circle that. And because we've ended up with 4, that is just 2 times 2. And again, they are both primes. So we have got an answer here. We just need to put a multiplication symbol between all of those numbers. So to get to 56, you would do 2 times 2 times 2, and then as well times 7. Now you can write your answer in index form, so you can write this using powers. So 2 times 2 times 2, you can simplify that and write it as 2 cubed, and then obviously multiply by the 7. So either of those answers is absolutely fine. You wouldn't have to write one or the other unless it's specified in the question that you had to write your answer in index form, or it specifically asks for you to write it with a power of 2. So there we go, 2 possible answers that you could write for that one. For this question, we're going to be having a look at highest common factor, and it says find the highest common factor, or in brackets there, HCF, of 84 and 180. Now you can have some pretty horrible numbers here in order to find the factors of. So we need to think of a method that might help us to find the factors, and I would always write it in a table. So 84 and 180. Now completely up to you, but one of the numbers is normally slightly easier to find the factors of. Now in this particular example, I don't think necessarily either of these are easier. 84 isn't the nicest of numbers to be finding factors of, but you just need to look at the two and have a think about which one you prefer. Now if we go for the 84, I'd always write my factors in factor pairs. So 1 times 84, 2 times 42, and then I need to try and figure out the other numbers that maybe don't quite as obviously fit into 84. So without a calculator here, because this could be either type of question, it could be with or without a calculator. If we do have a calculator, we'll just do 84 divided by some numbers and see if they fit in, but we want to follow a nice logical strategy. So the next number I would want to test is if it divides by 3. So I'm going to do that to the side. 3 goes into 8 twice, remainder 2, and it goes into 24 8 times. So 3 does fit in, it fits in 28 times, so 3 times 28. I'm pretty confident that 4 fits in. If you don't know again how many times, we can do this to the side. 4 fits into 8 twice and into 4 once. So it goes in 21 times. I know that 5 doesn't fit in. I'm not overly sure about 6, so we should probably test that as well. So does 6 go into 84? Well, it goes into 8 once, remainder 2, and it goes into 24 14 times. So yes, 6 times 14. 7, does 7 fit in? Let's do it to the side. So 7 into 84. 7 goes in once, remainder 1, and it goes into 14 twice. So 7 goes in 12 times. I know that 8 doesn't, because 8 would go to 80 and then to 88. I know that 9 doesn't, because 9 goes up to 81 in the 9 times table. I know that 10 doesn't, I know that 11 doesn't, and then I'm back to the 12 on the other side. So as you can see, that is possibly one of the worst type of numbers that we can have, just because the sheer amount of factors that are in that number. But now we have all the factors for one number, I just want to test to see if any of them fit into 180. And I can kind of do a process of elimination here. I know that 84 doesn't. I'm pretty confident that 42 doesn't, although you might want to test that if you're not 100% sure. 28, it possibly could. So the only option it could be is if it was 28 multiplied by 5 potentially. That might give you a 0 at the end, because obviously that number on the right there has a 0 on the end, 180. So if you're not 100% sure, you could obviously test it. We could do 28 multiplied by 5 to the side. 5 times 8 is 40, carry the 4. 5 times 2 is 10, plus the 4 is 40, 14 there, well 4, but obviously adding the 1, adding the 4 on, 10 adding the 4 on. So it makes 140. So 28 doesn't fit into 180, so we can cross that off. 21 definitely won't if you multiply it by 5 or 10, so we can cross that off. 14 isn't going to either. 12 potentially might though. Let's see if 12 fits in. Now, a couple of different ways that you could test this. It's going to have to be a multiple of 5 that we multiply it by if it's going to end in a 0, or we could just do bus-stop division. So I could do 180 divided by 12. 12 fits into 18 once, remainder 6, and then it fits into 60 5 times. So yes, it does. 180 is 12 multiplied by 15. So the highest common factor is 12. And there we go. Okay, so for lowest common multiple, I take a very similar approach to how I present it when I'm doing highest common factor, except obviously with multiples we are looking at the times tables of these numbers. So for the lowest common multiple, we want to write out the times tables for 40 and 56, and we will find the lowest number that appears in both lists. Now, because the lists can get quite long, I tend to do these going across the page just to give myself some more space to write out as many multiples as needed. And of course, we want to look at the numbers and think about which one is obviously going to be spottable for when they are a common multiple. So what I mean by that is 40, it's quite nice to spot if another number can divide by 40 because it ends in a 0. So if I go with the 56, if I add another 56, we get 112. If I add another 56, we get 168. And obviously then take your time moving between for the next multiple. So if I add 6, we'd get 174, and add the 50 would get us to 224. Now, as you can see, none of the numbers have ended in a 0 yet, but if we add another 56 now, we do get to 280. And this is what I mean by easily spottable. We can sort of see that 280 has a good possibility that it will divide by 40, and if you know sort of going up in 40s in a certain amount, you could sort of say to yourself, well, we know it's going to get to 200, and then we know that's going to go 240, and then 280. And there we go, we get our link there, we get our lowest common multiple, and our final answer would be 280. Okay, so looking at some laws of indices. Now there are a few rules that we need to remember. As long as the base numbers are the same, we can add powers when we are multiplying, and we can subtract powers when we are dividing. So when it is presented to you like this, where there is a fraction involved, we want to tidy up either the top or the bottom before thinking about that division indicated by the fraction line. So on the top, they are being multiplied, which means that we can add together those powers. So the powers that we have are 7 and -2, and we're going to add those together. Not forgetting that when you add a negative, that is the same as just doing a takeaway. So that is going to equal 5 as our power on the top. So if we tidy this up, we have 3 to the power of 5, and that is all over or divided by 3 to the power of 3. When you are dividing, you can subtract the powers. So here we've got 5, take away 3, and that would give us 3 to the power of 2. Now a question like this could ask you to write your answer as a power of 3. And if it did do that, our answer would be 3 to the power of 2. But this question here actually says to work out the value of. Now, because it says to work out the value, we would give our answer as a number, not forgetting that 3 to the power of 2 means 3 multiplied by 3, or multiplied by itself, and that answer is 9. So our final answer for that one would be 9. So there are a few other types of laws of indices that you can have as well. Here is one example where you have a fractional power. Now when you have a fractional power, the number on the denominator, which in this case is a 2, represents a root. So in the case of a 2, that represents a square root. So we would have a square root for a power of 1/2. If we had a power of 1/3, that would represent a cube root. But this one here just represents a square root. So the square root of 36, well, the square root of 36, definitely the most common one that we would give, would be 6. Of course, when you square root a number, you can have the negative version as well, so you could say -6, but here we'll go for the most obvious answer. The square root of 36 is 6. For part B here, it says to write down the value of 23 to the power of 0. Now the power of 0, that occurs when something has been divided by itself. So for example, if we had something like 23 to the power of 4 divided by 23 also to the power of 4, you would subtract those powers, and that would equal 23 to the power of 0. So that's a scenario where a power of 0 can occur. And we know that when you divide anything by itself, you get the answer 1. So anything to the power of 0 is just the answer 1, and that is our final answer. So when we are simplifying expressions, there are a few different types of expressions that we can have to simplify or collect like terms or multiply, and there's a good variety here to look at. So not forgetting, when you are given a letter in an expression, if there is no number in front of that letter, you can put a 1 in there if it helps you just to collect them up. So here we have 5f take away 1f. Now just doing that part to start with, 5 take away 1 would give you 4f. We then have to add an additional 2f, and together that would give us 6f. And there we go, that's our final answer. Not forgetting, when we simplify this, we are looking to fully simplify it. So writing 4f plus 2f and leaving our answer just like that would not be fully simplified. We are looking to get rid of as many symbols as we possibly can. And in this type of question, they can all disappear, just leaving us with 6f. Now for the next question, we are asked to multiply some pieces together, and this is a good one because we have a number here and a number at the end. So when you are multiplying here like this, we can multiply them in any order. We can do 2 times 8 to start with, which would give us 16. We then have two different letters, so we have an M and we have an N. Now of course, if those letters were the same, so if it was an M times another M, well that together would give us M squared. But this is an M multiplied by an N. An M multiplied by N, we can't make any fancy expression with it, we just write those letters M, N next to each other. Of course, when you don't write any symbols between them, the symbol which is actually in there is a multiplication sign, so this does mean 16 times M times N, which was exactly how the question was given to us, except we have simplified the 2 and the 8 and written that as 16. So our final answer is 16mn. For part C here, we are asked to add together t squared and another t squared. Now, a lot of the time, people will give the answer t to the power of 4, but that would only happen if it was t squared multiplied by t squared, as we know that you add the powers when multiplying. Now, of course, here we are not multiplying, we are adding them together. So this is 1t squared plus another 1t squared, and in total that is 2 lots of t squared. So our final answer for that one is 2t squared. Okay, so we've got two different types of brackets to expand here, one with a letter on the outside and one without one. So when you're expanding brackets, it just means to multiply whatever is inside the bracket by whatever's outside the bracket. So in the first question here, we have 5 lots of and then 2m minus 3. So we multiply them separately. 5 lots of 2m would give us 10m. 5 lots of 3 would give us 15, and we'll just keep the subtraction symbol there. So here, you can think of it as 5 times negative 3, which is negative 15. Then, of course, you don't have to worry about putting the symbol back in because you get the negative 15 anyway. When we have a letter on the outside, you need to be a little bit more careful because it tends to be that the same letter is inside the bracket, like in this case. So we'll start the same, 2x times 3, or 3 times 2x, however you prefer to read it, and that is 6x. Again, the symbol is going to stay the same, so I can put that in to start with, and then I have to do 2x multiplied by x. Now in this case, don't forget it is 2x multiplied by 1x, even though we don't write the 1. 2 times 1 will give us 2, and the x multiplying by another x, as we talked about in the last question, will increase the power, and we'll get x to the power of 2. So there we go, not forgetting when you have similar letters multiplying by each other, you will increase the power, as the power of the x's there are both 1, and those powers get added together to make a power of 2. Okay, so we can have some slightly more complex brackets as well, where we have 2 sets of single brackets, and we're being asked to add or take them away from one another. Now, it doesn't matter on the scenario, we're still going to want to expand these brackets as normal. So I'm going to start by expanding the first bracket. 5 times p would give us 5p. And then we also have 5 times 3, which is equal to 15, and that is a plus 3, so plus 15. For the next bracket, you have 2 different ways of doing this. You can either expand the bracket or multiply the bracket by 2, and then take them away from one another, or you can actually save yourself a bit of time and just use this number as negative 2. So to start with, we would do negative 2 times 1, which is negative 2. And then we would have negative 2 times negative 2p. And you can write that to the side if you sort of prefer to look at it like this. So negative 2 times negative 2p. Well, we know a negative multiplied by another negative is going to make a positive number, so we can put the plus in. And 2 times 2p will equal 4p. Now, of course, if you didn't take that approach, multiplying by negative 2 at the start, you would have got negative 4p. And then you would have to remember that you are taking away negative 4p, and that would then change the sign to an add. So be very careful with these ones, because that particular part in the middle there is what can make a lot of mistakes happen. So just be very, very careful, particularly when these are a takeaway in the middle. So now we can collect like terms, as it does say to simplify as well. So if we look at the like terms, doesn't matter which one we start with, I'm going to go with the 5p and the 4p, as the p's are written first, and that would give us 9p in total. And then I'm going to look at this plus 15 and a take away 2, and 15 take away 2 would give us positive 13. So there we go, our final answer would be 9p plus 13. When we are factorising expressions, this is the reverse essentially of expanding a bracket. So in these particular questions, when factorising, we're looking to put them back into a bracket by taking out a factor. Now, if the question just says to factorise, we only have to spot any factor, but typically if it says factorise, it's because there's only one factor. Whereas you can see in part B, it says to factorise fully, which normally indicates there's more things that can go on the outside of the bracket. So in the first question, 5 and 10, well, the only number that goes into 5 and 10 other than 1 is 5. So 5 would go outside the bracket, and then we just have to think to ourselves, what do we times 5 by to get this 5? Well, that would be 1, and keeping the symbol the same, so take away. And what do we times 5 by to get to 10m? Well, we're going to have to multiply by 2 to get to 10, and in order to make sure that that m is there, the 2 will have to have an m with it. There we go, we can close the bracket, and that is factorised, and we have taken out a factor of 5. For the question below, we have a little bit more to think about, because we have 2 and 6, which we're going to find a factor or a numerical factor, and then we also have the a's and the b's. I'm going to think about whether they can go outside the bracket as well. Now you could factorise this by just taking out a factor of 2, which is a number that goes into 2 and 6. And if you did do that, you would get a squared b, plus, and then to get to 6ab squared, you would get 3ab squared. And that is factorised, but it's not factorised fully, because you can also take out a's and b's. So let's think about how much we can take out altogether. We can definitely take the 2 out. There's an a squared here and just 1a there, so we can definitely take out 1a. And then we have a b here and a b squared here, so we can definitely take out 1b. So if we have 2ab on the outside of the bracket, what would go inside to make these? Well, that says 2a squared b on the first one. We already have the 2, we've got the b, we just don't have a squared. So we'd have to put another a in there to make sure that a turns into an a squared. We'll keep the symbol the same, plus, and now we'll look at the 6ab squared. To get to 6, we are going to need a 3, otherwise that 2 won't turn into 6. We already have an a outside the bracket, and it's an a in that particular piece there with the 6ab squared. And we don't have a b squared, we just have a b on the outside of the bracket. So we'll have to put another b in there to make sure that when we multiply that out, it turns into a b squared. And there we go, that's our final answer. We obviously don't want this one on here, although normally you do get more marks for these factorised fully questions, so taking out any factor is going to get you a mark, but obviously we want to secure all the marks and take out all the possible factors that we can. Okay, so for some substitution. So essentially we are just going to replace the letters with the numbers. Now obviously thinking carefully about what that expression or that formula up there actually means, it means 7 times r plus 3 times q, or 7 lots of r plus 3 lots of q, and that's what p is equal to. So to find the value of p when r equals 5 and q is equal to -4, we're going to want to do 7 lots of r, which is 5, so 7 lots of 5. Add to that, we are going to want 3 lots of q, which is -4. So 3 times -4. We can now look at each of these separately, so 7 times 5 and 3 times -4, well 7 times 5 is 35, 3 times -4 is -12, so we have 35 add -12. And again, we've got the add a negative symbol next to each other, so that is just a take away. So we have 35, take away 12, and that would be 23. So our final answer, the value of p, would be 23. So here we've got some algebraic laws of indices, quite similar to ones that we've looked at before. We have the same base in part A, and those being an m. And here we have a power of 3 and a power of 4. So if we are multiplying, we can add together the powers, so that would be m to the power of 7. For part B, we are actually cubing everything inside the bracket. Now, when you have that going on, you could write this out in the longest way you possibly could, which is 5np cubed multiplied by itself 3 times, so np cubed times another 5np cubed. Now, we know you could do 5 times 5 times 5, which is essentially 5 cubed. You could do n times n times n, which again is n cubed, and then p cubed times p cubed times p cubed, which again you can add together all the powers. So that is a long way of writing it out, particularly if the power outside the bracket was a 4 or a 5, you'd start to have quite a lot written out. So all you need to actually do is cube the pieces individually. So we have 5, which we're going to cube. We have n, which we are going to cube. And then we have p cubed, which we are going to cube. So the quick way of doing this, obviously thinking about the fact that if in the long way we would literally just add all of these numbers together, that is essentially just multiplying those powers together. So p cubed, if we do the powers, it'd just be 3 times 3, which would make p to the power of 9. Now you can think about all of these as already having a power of 1 in those earlier numbers, and again we have just multiplied those by 3. So 5 to the power of 1 times 3, n to the power of 1 times 3, and p to the power of 3 times 3. We obviously need to simplify this a little bit because we do have a number here which can be written as an actual value rather than 5 to the power of 3. So we'd want to work that out. 5 times 5 is 25, times 5 again is 125. So we get 125 n to the power of 3, p to the power of 9. And that there is our final answer. Now the one on the bottom, I think this one's possibly a little bit easier because we have a division. So numbers will always just divide as normal, and the powers we will subtract when doing a division. The bit we need to watch out for is that r on the bottom that doesn't have a power written with it. So we can put a power of 1 in there just to remind ourselves to make sure we actually do that subtraction. So 32 divided by 4 to start with, well that is equal to 8. We then have the q's, we have a power of 9 and a power of 3, and we can subtract those, so q to the power of 6. For the final powers, we have r to the power of 4 and r to the power of 1, and subtracting those gives us r to the power of 3. So there we go, 3 answers where we were adding powers, we had some multiplication of powers, and we've got some subtraction of powers in the last one. Okay, so making a subject of a formula. It says here to make t the subject of the formula, and currently w is the subject of the formula. So what we want to do is have a look at what is next to the t and how we would do the inverse of that to move everything over to the other side. So at the moment, t is being multiplied by 3, and then we are adding 11. So first of all, we can get rid of the add 11, we can take away 11 from both sides. If we do that on the right hand side, the 11 will disappear, getting us closer to just saying equals t, but on the left we can't actually subtract 11 from w to write any sort of number, so we just write w take away 11. We're almost there, we only have one thing left to do, is to get rid of this 3, which is almost stuck onto that letter t, and not forgetting 3t means 3 times t, or you could say t times 3, even though the 3 is written first, and to reverse timesing by 3, we would want to divide by 3. Now we don't want to write this as w minus 11 divided by 3, because we don't ever really see it written like that using a formula. The divide symbol just doesn't ever appear. So when we are writing a formula and we want to do a divide, we will just write it as a fraction. So w minus 11 all divided by 3 is equal to t. So there we go, we don't need that division symbol, we can always write it as a fraction, just remembering it's all being divided by 3 there. Now you could rewrite this formula as well, you could write it as t equals and just switch them over, so w minus 11 all over 3, but it is fine to leave it in either form, just depends on what the question asks you to do. Obviously if the question on the dotted line says t equals like this, then you are obviously forced to write that in. You don't need to write the t equals again, you would just write w minus 11 over 3 as your final answer. And there we go, so that is some subject of a formula. Now you can obviously have much harder subjects of formulas as well, where you have squares and square roots involved. So this is one particular example which we can have a look at. Now it says here, make S the subject of the formula. Thankfully, we don't actually have to undo the squaring here, but we can talk about what we would have to do if we did. So here, first of all, we can get rid of this u squared, okay? But the sort of the difficult part when looking at this is there's no symbol in front of u squared. Now, if there's no symbol, that means it's a positive u squared. And to reverse or get rid of a plus u squared, we can subtract u squared from either side. If we take away u squared, on the left we have v squared, take away the u squared, and that's going to be equal to 2as. Now this is very similar to the last question where we had a 3 in front of the letter we were trying to make the subject. In this case we just have a 2a in front of the s. We can treat it in exactly the same way though. We can just divide both sides by 2a, and we can do that in one jump. So all over 2a, and that is equal to s. And there we go, s is the subject. Now it could say in a question like this to have made u the subject. And if we wanted u as the subject, then instead we would have first subtracted the 2as. So we'd have v squared minus 2as, and that would be equal to u squared. To make u the subject in this scenario, to get rid of squaring, the opposite to that is square rooting. So if we square rooted both sides, we could square root the left and square root the right. The square root on the right hand side would remove the squared, leaving us with u, and the square root on the left we would have to leave as a square root, so we would leave it as v squared minus 2as. And there we go, just an idea if we had to also remove a squared. Okay, so with these types of questions where we are given a lot of information, and normally it splits it into things like males and females or the choices that these particular people make, it can tend to ask us either to find a certain amount of people that sort of, in this case go to a certain place, or it might ask us the probability. Now there's a lot of information to decipher in these questions, so you can actually figure these out by using one of two methods. We can use either a two-way table or potentially a frequency tree, although I do tend to avoid using a frequency tree if I have the option. So in this question we're going to use a two-way table. Now reading the first line, it says 60 people were asked if they prefer to go on holiday in Britain or in Spain or in Italy. So straight away I can see there's a lot of information that I need to figure out. So I'm going to start drawing a table. I'm going to have a column for Britain, a column for Spain, a column for Italy, and then a final column there for the total. So you can label that, you can put all the words in you want. I'm just going to put Britain, Spain, and Italy, and I'm going to have a total at the end. It then starts talking about whether they were male or female. So I need male, row, a row for female, and again a total. So male, female, and total. So we'll go through line by line, filling in all the boxes that I can do within my table. It does say 60 people were asked in the first line, so if I tick that off and I put 60 in my overall total. 38 of the people were male, so that's the total males, so the first row, and 38 in the total. 11 of the 32 people who said Britain were female, so in the Britain column, we've got 11 that were female, and it says that's 11 out of 32. So 32 in total. We can tick that off. 8 males said Italy. So Italy column for males, we have 8. And then 12 people said Spain. So that's a total of 12 for the Spain column. One of the females is chosen at random. What's the probability this female said Spain? So we want to know how many females went to Spain, which is this box here. So we can go about filling in anything until we get there. We don't have to complete the table, but we just need to fill in anything we can until we get to that particular square. So if we go through, you can see in the final column, we have 38 males and a total of 60 people in total. So that has to be 22 in order for that to add up to 60. We can also have a look across the bottom row there as well. They've got to add up to 60 at the moment. 32 and 12 add up to 44. So that's going to have to be 16 more to get over to 60. We can now go down the Italy column. So 8 males and 16 in total, so we must have 8 females. And now we can actually go across finding that row there for the females. So 11 and 8 that we have just here and here linked together, those add up to 19. We need to get to 22, so that would be an additional 3 people. Now, based on the way that I've done it, I don't necessarily need to fill in any of the other boxes, but you could obviously go to that Britain column. They have to add up to 32, so that would be 21. And of course, as well, next to that now, we could go along to the 38. We have 29 in total in that row, so that'd be another 9 people, or you could go down as well, 9 and 3 make 12. The important part is that that final number that you put in works in both the row and the column that it was in. So you can see if I go down, 9 add 3 is 12, that works, and 21, 9 and 8 adds up to 38, so it works there as well. So I know that I've done my two-way table correctly. In terms of a probability then, we have 3 people that are females that went to Spain. So we have 3 out of, and this is the important part here. Now it says here, one of the females is chosen. So that's really important. It doesn't say one of the people are chosen, or one of the 60 people are chosen. It says one of the females are chosen. Now if you have a look, the total females is 22. So if we are only selecting from the females, and there are 3 of them that said Spain, then that is 3 out of 22. Now that would be our final answer. That fraction doesn't simplify, but even if it did simplify, in this particular type of question, we don't need to. It doesn't say give your answer in its simplest form, so even if it did simplify, we could leave it unsimplified, and that there is our final answer for this two-way table. Okay, so looking at a frequency tree, this one here, we don't have an option. We are given a frequency tree and we have to fill in this particular tree. So we can't use this information and try and sort of draw a table. We do need to fill in the frequency tree. It says each worker in a factory is either left-handed or right-handed. 22 of the 45 workers are male, 16 of the 34 right-handed workers are female. Complete the frequency tree. Well, we'll start with that first line. We are told here that there are 45 people in total, and that's drawn in the tree for us. It says 22 of them are male. So 22 go into the male circle there. We can tick that off. It doesn't give us any more information as the 45 is already in, but we know it adds up to 45, so we know that the females have to be 22 and 23 will add up to 45. We can then go to the next piece of information. We're only given one more. 16 of the 34 right-handed workers are female. That does give us 2 bits of information. It tells us that from the right-handed workers, 16 of them are female. So that would be down here in the female right-handed workers. So that deals with the 16. It says of the 34 right-handed workers though. So it does tell us that these 2 circles here, both the right-handed workers, has to add up to 34. So straight away we can work out the right-handed males. We just need to take away 16 from 34 and that would leave us with 18. So 18 right-handed males, and then we can fill in the remaining boxes because these 2 here have to add up to 22. At the moment we've got 18 in, so that would have to be an extra 4. And down here, these have to add up to 23. At the moment we've got 16 down the bottom, so that would have to be 7. So there we go, that is completing the frequency tree. Again, you could be asked a probability from one of these. It could say what's the probability if you pick a male that that person is left-handed, or out of those people, what's the probability of picking a left-handed person? So you could be asked all the types of questions that we just talked about in terms of the two-way table, but just from the frequency tree. And of course, if you were asked to write the probability that if you pick a male, what's the probability they are left-handed? That would be 4 out of 22. Or if it said what's the probability you pick a left-handed male out of all the people, that would be 4 out of 45 people. So lots of different questions you could be asked, but there we go, just an idea there for some of those questions. Okay, so onto a pie chart. Now a pie chart does require you to use a protractor in order to draw these angles, so we are going to switch and start using a protractor for this. Okay, so when it comes to drawing a pie chart, we need to make sure that all of the angles for the pie chart add up to 360. Of course, a pie chart is in the shape of a circle, and angles in a circle, we want to go up to 360. So if we look at what we have at the moment, if we look in this table, you can see if we add these up, we have 11 plus 17, which is 28, plus the 8, which is 36. 6. That's quite a nice number because that can nice and easily turn into 360 degrees. So if I put the angle to the side, so this is just the angle that each one will be represented by, we need to think about how we get to 360. So to do this, now hopefully you can spot what we're going to have to do here to get from 36 to 360. But if you are not sure, you can do 360 divided by the 36, and in this case it does come out as 10. So we need to multiply all the numbers in the table by 10. So 11 multiplied by 10 will give us an angle of 110 degrees. 17 multiplied by 10 will give us an angle of 170 degrees. And 8 multiplied by 10 will give us an angle of 80 degrees. Obviously just double check those, add them up, make sure they do add up to 360. In this case they do, so we are perfectly happy with that one. We now want to get our protractor and line it up so that the crosshair there is on the centre of the circle. We want to rotate the protractor so that 0 is pointing up our starting line. In this case the starting line is going right up to the top. So I'm going to use the numbers on the outside of the protractor going clockwise. I'm just going to put a mark down here by the 110 degrees. I then want to pull the protractor out of the way and join that up from the centre to that mark there using a ruler. So once you have joined that up, it's going to look something like this. And then we want to just label that. So that particular section was to do with the burgers. So we'll put burger. And also you can put the degrees in there, you can put the frequency in there, it's up to you there, but as long as we've labelled it. Now we can put the protractor back onto that central spot, and we want to rotate round to our new starting line, the one that we've drawn. So once we are round to that line, which we've joined up with a ruler, we can then draw the next angle on. Now in this case it's 170 degrees. It can be a little bit awkward here, particularly if it's out the way or on the side of the page somewhere, but we'll mark this on. 170 degrees is just there. There we go, and then pull the protractor out the way. Join that up, obviously using a ruler to the centre, and then again we'll label that. So that was for pi, and that was 170 degrees. Now of course we need to label the final section, which is for hot dog, so we can label hot dog and then put our 80 degrees in there. And a good thing to do at this point is just to check that final angle. So pull the protractor back over, put the central point back on the crosshair and start from 0 and measure it out. Make sure it's pretty close. You can see the line goes up there. It's just here, it's pointing right on the 80, just here. So I'm happy with that. That final angle is 80 degrees. The pie chart is drawn, we've labelled it up, and there we go, that is drawing a pie chart. Okay, so looking at a frequency polygon. Now, in a frequency polygon, these are really nice and easy to plot. It's obviously just remembering what you need to do for one of these. So with a frequency polygon, we are going to plot for these intervals here that you can see. So for the first one, we have 10 to 20, and we're going to plot that on the midpoint. So to find the midpoint, it might be nice numbers. So I'd hope that you could spot that in between 10 and 20 is 15, but if you're not sure on finding those midpoints, you can add those two numbers together at either side of the interval and then divide your answer by 2. So for example, we would just do to the side 10 plus 20 and then divide that answer by 2, and that's 30 divided by 2, which gives us a midpoint of 15. So we can fill in all of these midpoints, so 25, 35, 45, 55, and 65, and then we are just going to plot them against the frequency. So obviously look at the axes. We have our height down the bottom and the frequency going up the side. So we're going to go to 15, which is in between 10 and 20, and then go up to 7. Now obviously read the scale carefully. You can see here between 5 and 10, where I'm trying to find 7, there are 10 squares. Obviously with a gap of 5, that means that every square is 0.5. Okay, you can just do 5 divided by the 10 squares, which is 0.5. Or in other words, that means every 2 squares goes up by 1. So I'm going to want to go 4 squares up from 5 on the 15. So 2, 4, obviously you can't see where I'm counting there, but there we go, that would be 7. We can then just move along, going across through every midpoint up to each number. So I'm going to go to the 25 and then go up to 13, which is here. And then we can go to 14, which is a nice one to find next, as it's just going to be 2 squares above the last one. So 2 squares above that would put me here. We can then go to 12 for the next one, which is just here. And then we have 16 and 18. 16, not too bad to find, 2 squares above 15. And then 18 on the last one, which is going to be 4 squares down from 20. There we go, and there is our frequency polygon. Now, the way that you join a frequency polygon together, we don't join anything to the axes or to the origin. We simply, with a ruler and a pencil, join these points together with nice straight lines. So I would get my ruler, join the first two with a nice straight line. Don't then immediately connect it to the next point. You want to then obviously move your ruler. So we are drawing perfectly straight lines between these 2 points, between the next 2 points, and then between the final 2 points. And there you go, that is your frequency polygon drawn, plotting them on the midpoints. So in this next question, we're going to be having a look at a scatter graph. And it says here, one of the points is an outlier. Write down the coordinates. So an outlier is a point that lies away from what we would draw onto here, which is the line of best fit. So when you are drawing a line of best fit, you look at the general trend of all of the points. Here we're going to be looking at these points here, which do follow a trend, and we're going to draw a line of best fit that goes around about through the points with around the same amount of points above and below. So if I draw a few examples on here, because there are a few different ways that we could draw a line of best fit. So that there would be one example, and that would be absolutely fine to use. You can see that I have about 4 points below or to the right of the line, and a few more just above or to the left of the line, however you look at it. I could also re-angle that, and if I draw a second line on here, I could draw a line which looks something like this, possibly not as good, but it's absolutely fine as well. We are not computers, we are not able to plot these absolutely perfectly, we are just drawing it as best as we can. So I would get my ruler and draw a line that pretty much goes nicely through the points with around about the same amount on either side of the line. Now you can see there is one point here which lies away from those points. So this one here, it's the furthest away from the line of best fit. So that one there is the outlier, and this question has asked us to actually give the coordinates of that. So with a ruler, really carefully, you can trace down to the axes to see what that coordinate is. That lands perfectly between 9 and 11, so that is an x coordinate of 10. And going to the left, you can see it lies nicely between 18 and 20, so that is a y coordinate of 19. So our answer for that one would be 10 and 19. It says for all the other points, write down the type of correlation. Now the correlation just means the relationship between two things. So in this case, it's asking for the correlation between the maximum temperature and the number of hours of sunshine. Now when it asks for a correlation, we're going to give one of two words. So if the line is sloping upwards, as one goes up, the other goes up, that is said to have a positive correlation. If the line is sloping downwards, as one goes up, the other goes down, that's said to have a negative correlation. And of course, if it didn't follow either of those, you would say it had no correlation, but that's quite rare for that to ever be asked in an exam, because we do tend to use the graphs here that do have one form of correlation. So here the line is sloping upwards, so we would say that that has a positive correlation. You could also be asked in that particular type of question to describe the relationship between the two things. So in this case, if we had to describe what's going on here, we would say something along the lines of, as the number of hours of sunshine goes up, the maximum temperature also goes up. Or you could say on days where there is a higher temperature, there is more hours of sunshine. So either of those descriptions would be good if it said to describe the relationship, but here it said to write down the type of correlation. So we had a positive correlation for that one. Of course, it would be negative if it was sloping down. So on the next question, it says here, on the same day, in another British town, the maximum temperature was 16.4 degrees Celsius. Estimate the number of hours of sunshine in the town on this day. So this word here is important where it says estimate, because we are going to be using our line of best fit. And as we talked about, that line can be at slightly different angles depending on how you draw it. So anyone's answer here could be slightly different, although as long as we've drawn this line relatively accurately, we will get very similar answers. So 16.4, again I need to look at the scale here. So 17 is in the middle, so every square, we only have 5 squares between 16 and 17, so every square goes up by 2, or 0.2. So here 16.4, well we've got 16 on the line, then we have 16.1, 16.2, sorry 16.2, 16.4, 16.6 and 16.8. So 16.4 is that second line up, so you would get your ruler, draw across very carefully, make sure you go across that line and show this on the graph, and then we can go down really carefully and read that number. Now if my line had been slightly different, look, my answer could probably be on 13, maybe it'd go just over 13, just depending on the angle that I've drawn. This one is just before 13, again I need to read the scale very carefully. So we have in the middle 12, and that's 1, 2, 3, 4, it's just to the side there, 5 squares along. So it's 5 squares between 12 and 13, which means each one's 0.2 again. So if I count along, that's 12.2, 12.4, 12.6, 12.8. And you can see I'm reading that really accurately there, and I'm giving the exact answer that I've got off the graph, so that would be 12.8 hours. There we go, and that would be our final answer. Now again, you could be given one along the bottom and have to go up and across to read the maximum temperature, so just read the question carefully and obviously apply that to the axes that has that label on. So another variation of a scatter graph question, you can see here it says Sean has the information about the height and weight of 10 rugby players and he's asked to draw a scatter graph. On the scatter graph you can see he has also drawn a line of best fit. So it says here, Sean has plotted the points accurately. So all of those x's that we can see, they are all accurate points, but write down 2 things that are wrong with his answer. Now, straight away, hopefully, especially based on the last question, you're looking at this and thinking, well, the line of best fit should be following the general trend of the points. It should be drawn somewhere like that. So here you can see that all Sean has done is he has connected the origin to the top of the graph and joined that together. And that is not a line of best fit. That is just going to be exactly the same no matter what points are plotted on the graph if we join it up like that. So here we would say the line of best fit has not been plotted correctly. Is not plotted correctly. There we go. It's not plotted correctly. And you can also back that up by drawing one on. In a question like this, you can plot the correct version and use that to back up your explanation. For the next part, well, there's only one other thing that could go wrong with a graph. If the points are plotted correctly, then it must be something to do with the axes. So if we look at the axes, we'll make sure that it's all scaled properly. So let's just have a look. It goes from 85 to 90 here. So that goes up by 5. Then it goes up to 95, 100, 105. So happy with those. They look good. This one goes from 140 to 160, so it goes up by 20, and then it goes to 170. So here we've got plus 20, and here that's only plus 10. So the axes are not scaled correctly. So again, we could put the correct answer on, and you could just write down here that it is not scaled correctly. And you could say more to that, you could say from 140 to 160 goes up by 20 and then the rest go up by 10. Anything along those lines, but as you can see with a scatter graph and any of these graph questions where it does ask you to see what's gone wrong, quite often it's to do with the scales on the axes or the way that the actual graph has been drawn. But there we go, just a little bit of a different scatter graph type question. So moving on to fractions of an amount. This question here is a slightly different one. It does say 4/5 of a number is 32. Find the number. Now questions like this can be incorporated into larger questions, but this is just a skill-based question looking at how to go about figuring this out. So if 4/5 of a number is 32, you could imagine this by using a bar model. We could sort of visualize what this actually looks like. So we don't want to get confused between fractions of an amount and this here, which is more of a reverse fraction of an amount. So here I've split my bar up into fifths. I've got 5 pieces, and this is saying that 4/5 of the number is 32. Well, if we looked at 4/5 of the number, that would be only that much there of the bar, just those 4, which would add up to 32. Now, if those 4 add up to 32, we can figure out what number has to go into each box. As there's 4 of them, we would divide by 4, and that would give us 8 that goes into each box. So if we were to now fill in 8 into every box, let's have a look. What we have, a total there of 40. So the number must have been 40, and that is how we go about finding a reverse fraction of an amount. Normally when we are finding a fraction of an amount, quite a common way to remember how to find a fraction of an amount is to divide by the bottom and times by the top. But in this scenario here, we're actually doing that in reverse, as it's actually given us the answer. So actually we divided by 4, and then, although I counted up the 8s there, I did 8 times 5, because there were 5 of them, which gave me my answer of 40. So a little bit different, we were doing the opposite there, because again we had been given the answer. We weren't being asked to find 4/5 of 32, we were asked that 4/5 of 32 was the answer, find that number. So just thinking about these logically in terms of the way you'd approach it, rather than remembering a trick. When we are converting fractions, decimals and percentages, if we want to make any sort of comparison, and in this one it's asking us to order them in size and to start with the smallest number, so we are actually going to have to compare them, we are going to want all of them in the same form. Now it's up to you which form you put them in. Typically it's quite nice to turn them into percentages, or of course you could write them all as fractions. If you do write them as fractions though, you need all the denominators to be the same, which can cause a few issues with some questions, but we'll have a look and have a think. So here we could write them all as percentages. Percentages are quite nice to look at and think about which one's bigger or smaller. So 3/10, we can convert that into a percentage in lots of different ways. The easiest way is to make the bottom number 100. So we would times the top and bottom by 10, and that would give us 30/100. Not forgetting that a percentage literally means per 100. This is 30 per 100, so that is 30%. The next one, the decimal, to turn a decimal into a percentage, you just multiply that by 100. So that would become 32, which is 32%. For 2/5, again, we want the denominator to be out of 100. We could times the top and bottom by 10, make it out of 10 first, or you could times the top and bottom by 20, and we would get 40/100, which again is 40 per 100, which is 40%, so 40%. And the last one again, timesing that by 100, would give us 25%. We can now put them into size order, not forgetting it says write these numbers in size order, so not our new converted forms, we want to write the originals in size order. So the smallest there is 25%, that was the decimal 0.25, so that would go first. You can tick them off as you go if that helps as well, just to make sure you definitely write them all down. The next one was 30%, which was the 3/10, so that would be our second, and we can tick that off. Then we've got the 0.32, we've got the 35%, and then we have the 40%, which was 2/5. So 2/5 would be last, that's our largest there, and we've put them in size order. Okay, so when finding a percentage of an amount, we're going to take a similar approach with pretty much any of these questions. I would always recommend finding 10%. You might be more confident finding 1%, but particularly without a calculator, we just find 10%. So 10% of 80, we divide it by 10, we get the answer 8. Now this particular question does have a multiple of 5 in it, so we're going to want to halve that in order to get 5% as well, and half of 8 is 4. Now this is quite a nice one because it is just 15%, so you can add those two together, and our answer for this question would be 12. But of course we could be given any form of percentage. So for example, if we were asked to find 35%, you would want to find 3 of the 10%, so times that by 3, and just 1 of the 5%. So you can add those together, that would help you find 35%. There are other percentages you can go to without a calculator, so things like 2.5% can be found from the 5% as well. You can divide 5% by 2, so 2.5% here would be half of 4, which is 2. And of course from 10% you can also find things like 1% by dividing by 10 again. Now this is the number 8 that we've got as 10%, so if you divide that by 10 again you do get a decimal, you get 0.8. But using these percentages you can pretty much find anything. You could find something now like 23% because you could do 3 of the 1% and 2 of the 10%. So you can build things up however you want, but I would recommend starting with the 10% and then finding 1% from there, or if it's a multiple of 5, sticking to the 5%. Now with percentages, there's lots of different types of questions that you can have. This one in particular is looking at a percentage increase. It says Asmol is paid $1,500 per month and he's going to get a 3% increase in the amount of money he is paid. Work out how much money Asmol will be paid per month after the increase. So obviously an increase means that he's going up in value, he's getting a pay rise. So we just need to be able to work out 3%. Now the most important percentage, particularly when we are looking at non-calculator methods, the most important percentage to be able to work out is either 1% or 10%. So if you go with 10% first, 10% you just divide this by 10, which hops the decimal in, which would be 150. Could have worked out 1% first as well, which is dividing it by 100, but we can always get to 1% from 10% by dividing by 10 again. So 1% would be 15, and hopefully you can see the pattern between those three numbers. So for 3%, we are going to want 3 of these 1%, so timesing that by 3. Take your time with that. 15 add 15 is 30, add another 15 is £45. So Asmol is getting a pay rise here of £45. So after the increase, he will have 1,500 plus this new £45 that he's getting, so £1,545 will be the amount that he gets after the pay rise. Now, of course, we can always have a percentage decrease as well. So a percentage decrease just means that it's going to go down in value. This could be a calculator or a non-calculator question, but typically these percentage questions, they're okay to do without a calculator. We'll have a look as we go through and we'll think about whether this would definitely be a non-calc or a calculator question. Now, if it's going to go down by 32% and its starting value is £675, we'll try and work out what that 32% is. So again, I'm going to start with 10%. So 10% of £675, again, dividing by 10 to get 10% would give us £67.50. So £67.50. At some point, we're going to need a 1% as well, because we're going to have to get to 32. So if we divide 675 by 100, which gets us 1%, that would give us £6.75. So that is £6.75. Now the numbers here are not awful, but straight away it does stand out to me that this is more likely to be a calculator style question. But nevertheless, we can do this without a calculator. We just need to add up a few of these to get to 32%. So we would have, there's quite a lot of numbers here if we did do it without a calculator, because we've got 3 of the £67.50s. Of course, you could multiply that by 3 if you like, but I just think adding them up here isn't too awful. We've also got the £6.75 and another £6.75. I probably wouldn't want to go beyond this many if I'm doing column addition, because it would start to get a little bit messy. But let's work this out. So we have 0.0055, that adds up to 10, so carry the 1. Then we've got 15, 22, 29, 30, so then carry the 3. 7, 14, 21, 27, 33, plus the 3, 36, so carry the 3. And then 6, 12, 18, plus the 3 is 21. So that adds up to £216. So actually, once we've added these together, that's not actually an awful number. And to be fair, we could actually have done this without a calculator. So maybe this doesn't have to be a calculator question. So going for this, we've got £675. We need to subtract this £216 as the sale price is being reduced by 32%. So we can do this as a subtraction. Typically when these come up, it does involve some form of carrying. The questions are structured in that way to force you into doing some carrying. So we can't take away 6 from 5. I'll have to borrow from this 7. So that'll be 15 take away 6, which is 9. 6 take away 1, which is 5. And 6 take away 2, which is 4. So there we go. The final cost here of the television would be £459. And that is the price after a 32% sale. Now, when we are calculating percentage changes, there is a calculator and a non-calculator method. So we're going to have a look at a non-calculator method for this one, but we'll also talk about what you would do if you had a calculator as well. So it says here Renee buys 5 kilograms of sweets to sell. She pays £10 for the sweets. She puts all the sweets into bags, and they're going to be 250 gram bags. She's going to sell them all for 65p, and she sells all the bags of sweets. Work out her percentage profit. Now, percentage profit is a nice one to work out without a calculator, because we know, particularly with £10, that we can find some relatively nice percentages of that. So if we have £10 over here and just think about some of the percentages, well, 10% of £10 would be £1, just dividing it by 10. You could also find things like 5%. 5% would be half of a pound, that would be 50p, or you could write that as 0.50, like that. We can also multiply the 10%, so maybe something like 20%, which would be double that, which would be £2. Or you could times it by 3, you could get something like 30%, which would be £3. Now, if it's non-calculator, it's going to be something that links nicely to the ones that I've drawn there, but we'll have a look and see. So, if they buy 5 kilograms of sweets, but 250 grams for the bags, we're going to want to convert that 5 kilograms to see how many bags of sweets we've got. So 5 kilograms is 5,000 grams. There are 1,000 grams in a kilogram, and we are going to put them in 250 gram bags. Now, I wouldn't really want to do 5,000 divided by 250. So I'd probably think about another way of doing that, but we could actually divide it. When you are doing a division like this, we can get rid of a 0 top and bottom, and it's 500 divided by 25. That's not too bad to do. 25 fits into 50 twice, and there is an additional 0 there. So it is actually 20. But you could count up in 250s, 4 of them will fit into 1,000, and you've got 5,000, say 4 times 5, which is also 20. So different ways that you could go about that. Of course, you could do bus stop division as well. 500 divided by 25, 25 goes into 50 twice, no remainder, so 0. So a couple of different ways that you could actually do that division without a calculator. So if we've got 20 bags, we're going to sell them all for 65 pence. And we obviously need to multiply that by 20. So however you want to line that up, I'm going to do 65 times 20 this way. There we go, 0 times 5, 0 times 6. Placeholder for the 2. 2 times 5 is 10, so carry the 1. 2 times 6 is 12, plus the 1 is 13. So adding that together, we don't really need to because we've got the zeros above, but that is 1,300 pence. We can convert that into pounds as well, as our £10 was given to us in pounds. If you want, you can write them both. So that would be £13. So you can see here, we bought the sweets, or Renee bought the sweets for £10. She sold them for £13. Now in terms of profit, that means her 13, take away the 10 that she spent, has left her with £3 in profit. So if she has made £3 in profit, what is that as a percentage, or what is her percentage profit? Well, we got one of them at the start, and it's this one here, isn't it? So they've made £3 profit, and that equated to 30% in terms of a percentage profit. Now, if you are doing this with a calculator, there is also another way of writing it. So if you have a calculator and the numbers aren't quite as nice, obviously we could have used a calculator here for all of the calculations along the way, but you do the profit, which is 3, over the original, which was 10. We could write this as the profit or the change, because this also works if you have a loss. So a profit over the original, and then times that by 100, and the only reason you're timesing it by 100 is that will give you a decimal or a fraction when you do profit over original, so it gives you 0.3, which is a decimal version of 30%, and when you times it by 100 it gives you 30%. Of course, if you get a nice fraction, so 3 over 10, you might be able to convert that into a percentage anyway using your conversion methods. So there we go, there is a calculator method as well for this topic. So on to some algebra when we are solving equations. Now this particular equation does have a bracket involved as well. So when you have any brackets involved, or you see a bracket in a question, it's always good to just expand it. It's very unlikely that we're going to deal with this while the bracket's there. Now for this particular type of equation, you can actually solve this without expanding the bracket, but I would always encourage you just to expand the bracket first. So that would be 3m, just multiplying by 3. 3 times 4 gives you 12, and keeping the symbol the same, so that equals 21. Now, I'm not going to go into the method of how you solve this without expanding the bracket, because typically it's not too difficult to expand the bracket there, so I probably wouldn't look at using varying different methods, but completely up to you if you can spot how to solve that without expanding the bracket. So here we do the inverse. So here it's 3 times a number, take away 12 is equal to 21. Well, what was the number before we subtracted 12? Well, to find that out, we can add the 12 by doing the inverse. So if it's a take away 12, we would add 12 to reverse that. So 3 times that number would have equaled 21 plus 12, which is 33. So in other words, before 12 was taken away and we got the answer 21, the answer would have been 33. So now we've got 3 times a number is equal to 33. And that's 3 times a number. The opposite of timesing by 3 is dividing by 3. So we'll divide both sides by 3. And we get that that number m must have been 33 divided by 3, which is 11. And of course, in these scenarios, you can sometimes get, and quite often get, non-integer solutions. So in other words, you don't get a whole number. For example, it could have been something along the lines of 2m is equal to, and let's just imagine it's something relatively nice like 15. Now that doesn't divide perfectly by 2 to give you a whole number, so if it doesn't, you can just write it as a division, as a fraction. So 15 divided by 2, you could leave as 15 over 2. And of course, if it's a non-calculator question and you want to convert that, you can do. I know that 15 divided by 2 is 7.5. So you could write your answer as m is equal to 7.5 or 7.5, however you choose to write your answer. But it is fine to leave your answer as an improper fraction if this scenario does occur. Unless, of course, it says in the question, solve it and give your answer as a decimal or something along those lines, which is very rare. So you can get non-integer solutions as well. Now, when we have an x on both sides of the equation, it's essentially the same as what we did in the last one. We have a bracket involved here, so before we talk about it, let's straight away expand this bracket and rewrite this equation. So we have 5x minus 6 on the left. On the right, 3 times x is 3x, 3 times 1 is 3, and there is a takeaway in between. So now we don't have any brackets to worry about. All we need to think about is how do we make it look like the previous equation? We want equations to look like this. 3x plus 2 is equal to 5, something along those lines. Now at the moment, the only thing that's stopping it from looking like that is this 3x here on the right hand side. So we need to get rid of the letters from one side of the equation. Now you don't have to get rid of them from the right or from the left, you can do either. So I always look to find the smallest coefficient of x, coefficient being the number in front of the letter. So in this particular question, 3 is smaller than 5. So all I'm going to do is I'm going to take away 3 x's from both sides of the equation. So 5x take away 3x is 2x. And nothing else changes other than the fact that we're removing these 3 x's from both sides. We still have this minus 6. We still have the equal sign. The 3x is gone, and this is a really good one because you've got to remember here, this is actually a negative 3. So we need to pay attention to the symbol there because it's still equal to negative 3. We've not got rid of a negative from the right, we've just got rid of 3 x's. So as it's equal to negative 3, this obviously does make it a little bit trickier because we are dealing with negative numbers, but this is a minus 6 here, which we're going to get rid of. Just like before now, it looks like what we wanted it to look like. We can add 6, doing the inverse there of taking 6 away, and that leaves us with 2x is equal to negative 3, add 6 is going to be positive 3. And here's that scenario that we just talked about where we get a number on the right there that doesn't perfectly divide by 2. So in this scenario, we do need to divide by 2 because we don't want to know what 2x is equal to. We want to know what 1x is equal to. And if we divide by 2, we can write that as a fraction, 3 divided by 2. Now, obviously, different ways that you could write your answer here. We could write that as, let's have a look, 3 goes into 2 once with a remainder of 1. So you could write it as 1.5. Or you might just know that 3 divided by 2 is 1.5. And you can write it as a decimal. So any of those answers is fine. You wouldn't obviously give the variations, you'd only give one of them. So we could just say down here, x is equal to 1.5 or any of the other variations, but we wouldn't give more than 1. There we go, x is equal to 1.5. So when we've got some inequalities, typically it is the same as equations. Now this inequality in particular is quite a nice one because although there are unknowns on both sides of the inequality, there is only 14n on the left, which does make it look a little bit strange in comparison to quite a lot of the ones that you'll see normally. So this one is a little bit different. So if I rewrite this, we've got 14n is greater than 11n plus 6. Now you can, if you like, because you tend to deal with equations more so than you deal with inequalities, you can, if you like, rewrite this as an equal sign until you've solved it. I don't necessarily recommend doing this because what you don't want to do is get to the end of the question and leave the equal sign there. But some people do like to change it for an equal sign just because you're more used to dealing with equations. I would, however, advise to keep the symbol in there and just know that you can treat this in exactly the same way to an equation. So here we have n's, or coefficients of n, on both sides. So again, I'm going to look for the smaller coefficient, and that is 11. So we're going to take away 11n from both sides. When we take away 11n's from both sides, we get 3n is greater than 6. And then we don't want to know the value of 3n, we want 1n, so we'll divide by 3. And we're going to get n is greater than 2. And there we go, that would be our final answer. For part B here, it says on the number line below, show the set of values for x which represent this inequality. Now the problem here is that in the middle of the inequality, we've got this plus 3. And we can only really represent this inequality if it's just x or any other letter in the middle, but this has added 3 to both the numbers. So to take this back to a normal inequality that just has x in the middle, we're just going to subtract 3 from both the numbers, as 3 has been added to both of them. So negative 2 take away 3 would be negative 5, and 4 take away 3 is 1. So the inequality that we can plot is there. We just need to remember whether there are symbols on the inequality. Now on the left it had a symbol without the equal sign. On the right it has the equal sign. So we need to keep that included in the inequality as well. That's going to help us then to draw it on a number line. So what we're going to do is put circles above any of the numbers. So here it's negative 5, so we'd have a circle above negative 5. And for a joint inequality, we're also going to put a circle above the other number. We're then just going to connect them together and decide if either of these circles need to be coloured in. And to figure out if they're coloured in or not, you just look at the inequality, and if it has extra ink on the inequality, like this one, then we put extra ink inside the circle. So for this one, we're going to colour in that circle on the right, and that is our number line completed. And if that's coloured in, all it means is that there was extra ink on the inequality itself, which just means it can be equal to that number as well. Now if you only have one inequality, like the one above just here where we had n is greater than 2, you might be asked to plot that on a number line. Now if we would have put a circle, I'm going to do it below, but you'd put a circle above the 2, and then we would point it in the direction of either what the inequality means, or if you actually look at the inequality itself, n is greater than 2, if you put this line in to make it look like an arrow, it points in a direction you need to point the line. So we need to point the line to the right, and that represents numbers greater than 2, and hopefully you can see here that that end of the inequality matches this one just here. They look exactly the same, they're pointing in the same direction, and there you go, that's your inequality drawn. So there we go, that is how you would draw that inequality, and one where you have a joint inequality with numbers on both sides. So when we are looking at error intervals, there is a big variation of numbers that we can have to round or have been rounded in these types of questions, and sometimes you are given extra information in terms of how the inequality looks, but this one here doesn't really give you anything. It just says a number y is rounded to 2 significant figures. The result is 0.46. Write down the error interval for y. Now with significant figures, again significant just meaning important, figures just meaning numbers, so 2 important numbers, we can have a look here. So the 0, when it's at the start, doesn't count as a significant figure. It's more about the first whole numbers that come up. So here, the first whole number is in the first decimal place, that's the 4, and the second is in the second decimal place. So another thing you could say is that this has been rounded to 2 decimal places. Now, if we think about a number line, so 0.46 being in the middle of that number line, the next number, if we were looking at just 2 decimal places, we'd have 0.47 just above it and 0.45 just below that. When we are looking at an error interval, we're looking at what the boundaries are that could have rounded to 0.46. And the rules of rounding is that when we have a 5 or above, it rounds up, below that it rounds down. So we need to figure out what that midpoint is there, and it is linked to that number 5. We also have another one on the right, and we kind of call these the lower bound and the upper bound. Lower being the lower number on the left and the upper being the upper on the right. Now it can help when you're finding these, just to find these midpoints, you can add zeros onto the end of these numbers, and then you can sort of just read this part of the number here to think about what's in the middle. So in between 450 and 460 is 455. Obviously it is 0 point that, but that means it's 0.455. Obviously that's 0.455. In between 460 and 470 is 465, so that's 0.465. Now looking at those numbers there, particularly if you've not seen these in a while, you'll obviously know that this number does round to 0.46. Okay, it's a 5 after the 5, so it rounds up to 0.46. The problem is though, this one on the right actually rounds to 0.47. So it wouldn't actually round to 0.46. Now when we write our error interval, we obviously have to include that when we write it. So this is talking about the number y. So we put a y in the middle. We have both our arrows pointing to the left. We put the lower bound on the left, so 0.455, the upper bound on the right, 0.465. And we obviously need to put on the symbols there that it can be equal to the number on the left. So this one on the left has the equal to symbol, but the one on the right does not, because that number does round to 0.47. So that means our number can be anywhere between 0.455 and 0.465, but it cannot include 0.465 because that would round up. And there we go, that's an error interval. Another topic which is very similar to error intervals is truncation. Now truncation is a very strange way of rounding. It's just when you chop a number off. So for example, if I was to truncate, let's go for this number here, so 0.437. If I was to truncate that to 2 decimal places, I'd get a very different answer than if I was to round it to 2 decimal places. If I round it to 2 decimal places, then we would chop after the second decimal, apply the rules of rounding, so 7 after the line, so the 3 rounds up, we'd get 0.44. But if I truncate the number, truncate just means to chop it off and completely ignore any rules of rounding. Essentially, this 7 just disappears and we are left with 0.43. So truncation is a little bit strange, particularly when the majority of the time we actually look at rounding. So something slightly different here. It says Kira used her calculator to work out the value of a number x. She wrote down the first 2 digits and she wrote down 7.3. So if she only wrote down the first 2 digits, it means that whatever was after that, she didn't even take into consideration. It could have been that it was a 9 after the 3, which we know in terms of rounding, we would want to write that as 7.4. But if she's just written down the first 2 numbers, it means that she has truncated the number, even though this question doesn't say it's been truncated. So when we are writing down the error interval, we're going to write it down in the same way. We've got an x with our same symbols as before. We just need to write down what's the smallest and biggest it could have been. Now this one doesn't really help to write down any form of number line, because we know the smallest number that it could have been is in fact just this one here, 7.3. It couldn't have been any lower than 7.3, because if she wrote down the first 2 numbers and it was 7.2, for example, well, she'd have written down 7.2. So the smallest it could have been is the actual number that we've been given, so 7.3. Of course, it might have just said 7.3 on the calculator, in which case, if she wrote down the first 2 digits, it would say 7.3. Now, the number that it can't be is just the next number up. So she couldn't have had 7.4 on the calculator, because if she wrote down the first 2 digits, she'd write down 7.4. So the very next number that goes up would be a 4. It can't be 7.4, and that would be the error interval. So if she wrote down the first 2, and she wrote down 7.3, that number can be anywhere between 7.3 and 7.4, but of course it cannot include 7.4 because that would be written as 7.4. And there we go, that's how we would approach it if we are truncating rather than rounding. So when we are looking at sequences, we are going to normally be looking at writing the nth term. Now a sequence can be given to you as a picture or as a number sequence. So this one's given to us as a number sequence, but of course they could draw a pattern. So for 5, it could be like something like 5 dots, and then the next one adds an additional amount of dots on. Now, if you are given it as a picture, you just count how many are in the picture and write it as a number, and write your number sequence like we're doing here. So the first thing we want to find is what's the difference between each number. So from 5 to 11, that goes up by 6, and 11 to 17 also goes up by 6. Always check at least 2 of them, but once we've got 2, we're pretty confident there it goes up by 6 each time. Now if it goes up by 6, it means that our sequence is related to the 6 times table. Now the mathematical way of writing the 6 times table is you write 6 with, and it could be any letter, but it says here an expression in terms of n. We do call it the nth term. We tend to use this letter, so we write 6n. 6n means the 6 times table. N is the position in the sequence, so for the first number in the 6 times table, we get the answer 6. We know from times table, 6 times 1 is equal to 6. That's what 6n means, 6 times n. 6 times 2 is equal to 12, and so on. 6 times 3 is equal to 18, and that forms the 6 times table. Now this sequence is linked to the 6 times table, but it's not exactly the 6 times table. If we write those numbers above the sequence, you can see 6, 12, 18 is definitely different to the sequence that we have been given. The sequence that we've been given is smaller than the 6 times table. So from 6 to 5, you would have to subtract 1. The same as from 12 to 11, the same as from 18 to 17. Each number you are subtracting 1. So this sequence that we've been given is the 6 times table minus 1. And that there is our nth term. Now that is what the term, or the nth term here, actually means. It means it's the 6 times table take away 1. But you might have also applied a little trick, and I know a lot of students do this. They sort of go back from the first to see what would have been before 5. To do that, you take away 6. 5 take away 6 is negative 1, and that negative 1 is obviously the number at the end there after 6n. So it's fine to use that little trick if you are confident and you understand this topic well, and if that's a little bit faster for you to find the number, you can do that as well. But I prefer to actually understand what I'm writing down. But there we go, that's how we go about finding the nth term. Now you might also be asked to use an nth term in a couple of different ways. So we'll look at this one and have a think about the other ways we could be asked to use it as well. This one says write an expression in the first part. We've just done that, so we can find the nth term pretty quick. This one goes up by 4, so that would be 4n. The 4 times table is 4, 8, 12. This particular sequence is bigger than the 4 times table. 6 is 2 bigger than 4, so it'd be 4n plus 2. So that would be our nth term for the sequence. It says here the nth term of a different arithmetic sequence is 3n plus 5. So that means it's the 3 times table plus 5. You could actually go about working that out. So the 3 times table is 3, 6, 9. If you add 5 to each of those, we would get 8, 11, and 14. So you can see there, it's quite quick to actually find what that sequence is. But it says here, is 108 a term in this sequence? Show how you get your answer. Now you can find, and I'm going to use both the methods here that we could be asked in terms of a question. Now it might say to us, what is the 20th term in the sequence? Now if it did, if you want to find the 20th term, we can find the 20th term by doing 3. That's not a 3, let's write an actual 3. So 3 times 20, which is 60, and then add 5. So 3 times 20, 60, plus 5, that would give us 65. So the 20th term is 65. Now we could keep going up in the sequence to see if we get to 108. So I could instead maybe try 30. I could go 3 times 30, which is 90. Add 5 is 95. So that's the 30th term. We're getting pretty close. Maybe go a slightly bit higher. Maybe 3 times 33. 3 times 33 is 99. Plus 5 is 104. And I know each term in the sequence goes up by 3 because it's the 3 times table. So I could add 3, or I could do 3 times 34. I'm starting to get more complex sums here. So that would be 90 plus 12, which would be 102, plus 5, which is 107. And the next term is going to be 110. So you know here that 108 isn't in the sequence, because you can see there it goes 107, then 110. So that's one method that you could use, although you can see that's going to take quite a bit of time. You need to know that method though anyway, because if it said find the 20th term, we very quickly do 3 times 20 and add 5, and you'd say the 20th term is 65. So you need to know that method anyway in case you're asked that. But if you are finding if a term is in the sequence, you can use a method that we've already looked at. You can make it as an equation. So we can say, does 3n plus 5 ever equal 108? To solve that, like we've done before, it says plus 5, so we'll take away 5. We get 3n is equal to 103. And then you just need to see if that divides by 3. So we would do bus stop division, or of course if you have a calculator you can just type it in. 3 goes into 10 3 times, remainder 1, and then it goes into 13 when it goes up to 12, which is 4, and then we would have to carry over a remainder of 1. And as soon as we get this remainder here that we have to carry over, because that fits in 3 times, again remainder 1, and it carries on going. So we do not get a whole number. So here we would say no, it's not in the sequence because it's somewhere between the 34th and 35th term, which we can see here anyway, because the 34th was 107 and the 35th was 110. So our answer, we would obviously write in words no, and then obviously depending on which method you used would be how you describe it. On the left there we would say no because it's not a whole number, the position is not a whole number, or on the right there you would say no because it's somewhere between the 34th and 35th term. So with a Fibonacci sequence, a Fibonacci sequence is just where the number before is added to the current number to find the next number. So just say here, the rule to continue a Fibonacci sequence is, the next term in the sequence is the sum of the 2 previous terms. Find the 9th number. So the sum of the 2 previous, so if we look at the 2, which has 2 terms in front of it, 1 plus 1 is equal to 2. And you can apply that anywhere else. So for the 8, 3 plus 5 is equal to 8. So all we have to do is take the 2 terms before, add them together, and it'll find the next one. So we currently have 6 terms here, so we need to find 3 more. I'm going to put these in place so I don't forget which one I'm getting to. So 5 plus 8 is 13, 8 plus 13 is 21, and then 13 plus 21 is 34. So there we go, the 9th term is going to be 34. For the next part here, it says the first 3 terms of a different Fibonacci sequence are A, B, and A plus B. Show that the 6th term of this sequence is 3A plus 5B. So show that means we absolutely need to show our working out. So for the next term, I'm going to do these 2 added together. And if I'm going to show that, I'm going to show some working out. So A plus B, which would give us A plus 2B. For the next term, we're going to now add together these 2. And again, you could either write that down in terms of a long bit of working out, or we could sort of just add them together. You can see there we have 2 A's, so 2A, and then you've got the 1B and the 2B, so that's going to be 3B. So adding those together. That's on the 5th term at the moment, so we have 1 left to do, and that's going to give us our 6th term, which should match the next one. So 2A and 1A is 3A, and 2B and 3B is 5B. So we get 3A plus 5B, which matches what we were given in the question. So there we go, some Fibonacci sequences with numbers and with algebra. Moving on to some angles, we have angles in quadrilaterals. Now it says here WXYZ is a quadrilateral, which we can see. So you can see just here that we have W, X, Y and Z that form this shape. So we know that angles in a quadrilateral add up to 360 degrees. So I'm going to put here 360 degrees. It then also says XYV is a straight line. And we can see that straight line as well. XYV makes this straight line here. And angles that are together on a straight line add up to 180 degrees. Now on that straight line there, you can see that there are 3 angles. You've got this one here, you've got this one here, and this 147. Now the only ones that add up to 180 are where they are together and form this almost semicircular shape on the straight line. So this one over here is nothing to do with our 180. So if we want to find anything here, we've got to just remember that, and also remember that the angles in a quadrilateral add up to 360. Well, if these 2 together here add up to 180, we can find the angle marked A, which is our first question. So we would do 180, take away 147, and that leaves us with 33 degrees. So our first answer would be 33 degrees, and it says give a reason, and our reason is that angles on a straight line add up to 180 degrees. And you have got to write the whole thing out, so don't write it in any shorthand. Angles on a straight line, you can write sum to or add up to 180 degrees. And there we go, that's our reason. For the next part here, it says angle ZWX. Let's find that. Z to W to X makes this angle here with W in the middle. And then you've got WXY, where X is in the middle, is this one here. And it says that those angles are equal. Work out the size of angle ZWX, so one of those two angles. Well, this is the point now where we are looking at the quadrilateral. We know that angles in a quadrilateral add up to 360. We currently have 2 of the 4 angles in the quadrilateral, and the other 2 are equal. So if we add together the 2 that we've got, 145 at 33, that adds up to 178 degrees. So what's left over to make that add up to 360? Well, 360 take away 178 will tell us what's left over. We're going to have to borrow here. So 10 take away 8 is 2, 5 take away 7 we can't do. So 15 take away 7 is 8, 2 take away 1 is 1. We have 182 degrees left over that's split between these two. So that's 182 degrees. If they are equal, we can just divide that by 2. So 182 divided by 2. Of course, if you're not using a calculator, we would use bus stop for that. So 2's into 18 go 9, 2's into 2 go once. So our answer would be 91 degrees. And there we go, we've got 33 degrees for the first one, angles on a straight line, add up to 180. And for the second one, 91 degrees. Didn't ask for a reason there, but our reasoning was that angles in a quadrilateral add up to 360 degrees. Okay, so for this question we have something a little bit more unique. We still have angles in triangles and quadrilaterals, but you can see here that we have a parallelogram involved. Now it says here ABCD is a parallelogram. It says that E to D to C is a straight line, and F is the point on AD, so that BFE is a straight line. It then tells us some angles, which we can see in the diagram, and it says to show that ABF is equal to 70 degrees. Now A to B to F is the angle made down here from going from A to B to F. It makes this angle just here. Now where it says to show that it is equal to 70 degrees, that doesn't mean that we can put 70 degrees in here and then work away from it. We have to essentially find out what that angle is. Imagine it's just an unknown angle, and as long as we find that that angle becomes 70, we will have actually shown it along the way. So we'll work around this question based on it saying find the size of angle X. Now there are a few different ways of getting to this. First of all, knowing that opposite angles in a parallelogram are equal is going to help us out in this question. Obviously, line by line, it tells us these things for a reason. So here, where it says it's a parallelogram, we know that the total angle down here with the B is equal to this total angle up here where the D is. Likewise, the opposite angles where A is and where C is, they are also opposite angles which are equal. So that means this angle up here is going to be 75 degrees. Now it says to give a reason with each stage of your working. So you can either do sort of a bullet point sort of format to the side. You can say that angle BAF is equal to 75 degrees. And you can say opposite angles in a parallelogram are equal. Now you can just label that on the diagram as well. But I do like this way of writing it, putting them to the side. So opposite angles in a parallelogram are equal. Now there we go, we found a missing angle and we have given a reason. We just need to find something else. You can already see that I now have one of the angles within the triangle. So I'm sort of looking at this triangle here because I know that angles in a triangle add up to 180. So now that I've got one of them, I just need to think, can I find another? Now if we have a look, we can actually see that that 35 is given to us as well. Now that is an opposite angle. We have two straight lines that are intersecting here, and we're given the angle on the other side, and these angles are equal. So this terminology here for those type of angles, they are called vertically opposite angles. So that is the angle AFB. So AFB is equal to 35 degrees, and we would say that vertically opposite angles are equal. There we go, so vertically opposite angles are equal. Now we are pretty much there because we now have two angles within that triangle. Again, the triangle that I highlighted earlier, so this particular triangle here. So when we have two of the angles within a triangle, we can add those two together. So 75 add 35, which add up to 110 degrees. We know that angles in a triangle add up to 180. So if we take away the 110 that we already have there, we end up with an angle of 70 degrees. So therefore, x equals 70. And that's exactly what the question was asking us to show. Now we might want to add another reason there as well, because it does say give a reason for each stage of your working. So at this point, we've got the 70, and the reason being there, angles in a triangle add up to 180 degrees. And there we go, that'd be all that we'd need to write for that particular question. So when we have angles in polygons, sometimes we'll be given a full polygon, sometimes we will have a regular polygon, sometimes we will also have irregular polygons. This question here is showing us a 12-sided regular polygon, but it's only showing us part of it. So you can almost imagine if it had 12 sides, the full shape is going to continue round here. We're going to have a nice big polygon there all the way round, but it's only showed us part of that polygon. Now the part of the polygon it has showed us is just the two sides and it's been connected together. So it has formed almost this triangular shape. Now as it is a regular polygon, that means the sides of the polygon are all the same length. So R to S, this line here, is the same length as this line here. And that means that that triangle there is also an isosceles triangle. And within an isosceles triangle, hopefully we are aware of isosceles triangles, the base angles are equal. So here, before I even start the question, I know that these two angles are equal, but this particular question says work up the size of angle STR. And if I put an X in that angle, that's this angle just here. So it's one of those two base angles. Now when it comes to a polygon, we can find the size of the interior angle, this one just here, by using a formula. So for the formula that we look at for working out the interior angle in a polygon, we take the amount of sides, which we tend to call n. We take away 2 from the amount of sides, which tells us how many triangles it's made of. Then we times that by 180 and divide it by the amount of sides. Now the formula can sometimes look a little bit complex, so it does help to understand why the formula is made the way it is. So if we think about a pentagon that has 5 sides, if we split a pentagon up, it forms 3 triangles, of course just going from one of the points. But it can never connect to, and I'm going to join these up now, it can never connect to the points that it's already connected to. There's always going to be 2 of those. So it always makes 2 less triangles than the amount of sides. Here the shape has 5 sides and it makes 3 triangles. So this part of the formula here is just looking at the amount of triangles that it makes. We know that triangles add up to 180 in terms of their angles, so we times it by 180. That tells us the total that they all add up to within that polygon. And then to split that equally among all the angles, we divide it by how many angles there are. So that's all that the formula actually represents, and understanding that formula can just help just to remember it. So here, if we have a 12-sided polygon, we would do 12, take away 2, which tells us that there are 10 triangles. And you can label that 10 triangles if it helps you to remember it. We know that angles in a triangle add up to 180, so our 10 triangles multiplied by 180 gives us a total of 1,800 degrees. And that's the sum of all of the interior angles in a polygon. Now a 12-sided polygon, of course, has 12 sides. So we would divide that by 12, and that would tell us the size of the interior. Now without a calculator, and of course this could be a calculator question, but without a calculator we're obviously going to have to just do some division. So 12 goes into 18 once, remainder 6. It goes into 60 5 times, and then 0 at the end. So the interior angle that we have found just here is 150 degrees. And if we had the rest of the shape, obviously if this carried on, the full angle there would also be 150 degrees. But we don't need that one. So here, very similar now to our previous question. We have a triangle involved with two missing angles, but this time those two angles are equal. So we can take this one angle that we have away from 180. That leaves us with 30 degrees. That 30 degrees is the total of these two. So to split that as they are equal, we can do 30 degrees divided by 2. And that tells us that each angle is going to be 15 degrees. And that would be our final answer. So 15 degrees would be the size of that angle, STR. So there we go, that is using the process of finding the interior angles. If you don't remember the formula, you can always remember a little pattern. So a shape with three sides adds up to a total of 180 degrees. Every additional side, so for a quadrilateral, we know that goes to 360. It actually just makes a pattern going up 180 degrees each time. So a five-sided shape, you can add 180 degrees again, and that takes you to 540. I don't know why I've written 180 there, let's change that. So that is adding 180, and we get 540. And you can just keep following that pattern, adding 180 each time until you get to the amount of sides that you need. Then, of course, you can divide it by how many angles there are to split it up equally among all the angles. But there we go, that is angles in polygons. So when we have angles in parallel lines, there are a few rules that we need to remember. So we have alternate and corresponding angles, and we also have co-interior angles. Now for the large majority of questions, you can actually get by using alternate angles. But you do need to know all three of those rules. So alternate angles are equal, and they make this almost Z-looking shape. Okay, so when you can spot one of those, you can see that there's alternate angles in these places just here. You also have corresponding angles. Now, corresponding angles occur when you have a line which is more extended through the two. So if this line was extended a little bit, you actually have these corresponding angles that occur that make this almost F shape, where you get these angles here along with that 142. And you also have co-interior angles as well, which make an almost C shape, and co-interior angles are inside the two lines just like so, and they add up to 180 degrees. So there's quite a lot of things that we can look at in this diagram. We don't have to use all of those rules, but when we have parallel lines involved, we are going to be using at least one of them. So it says here we've got the parallel lines, and it says we have an isosceles triangle. And you can see the isosceles triangle is here within the shape just there, as indicated by those lines there showing it's an isosceles. So here then, we can start by just looking at the shape and thinking, is there any angle I can find? Well, we've got 142 that's given to us up here, and that makes a straight line onto there. And we know that angles on a straight line add up to 180 degrees. So we can find this one by doing 180, take away 142, and that leaves us with 38 degrees. So that'll be 38 degrees in the top of that isosceles triangle. Now it does say in the question, give a reason for each stage of your working. So make sure you read the question carefully, because at this point now we would want to say angles on a straight line equal 180. So angles on a straight line add up to 180 degrees. And there we go, that's our first reason. We can then think about how to find somewhere else, and there's two specific directions that we could go in here. We could either find the base angles in the isosceles triangle, so we know that these are the base angles here underneath those lines that indicate the same length. So we could find those two, or we could look at the parallel lines and either go this way and hook in and find that that is 38 down there, because that's an alternate angle and alternate angles are equal. Or we could actually use this 142 and we could go that way. The only problem with this way is it is two angles and it's split in the diagram, so it's not the nicest to look at, but we could go that way as well and write that that full angle is 142. Now I'm going to go the other way, so I'm going to use alternate angles. I'm going to go down this way and I'm going to say that that angle down here is 38 degrees. And my rationale behind that, and I'll give my reason, I'm going to label it on the diagram this time. So I'm going to say here, alternate angles are equal. So there we go, alternate angles are equal. There we go. So we're almost done. We just need to obviously find now that missing angle in the triangle, which we could have done just before. So we'll find these two angles here. By finding both of them, obviously we'll find that one there, which is going to help us get to that x. So to find the base angle in an isosceles, we know that angles in a triangle add up to 180. So we do 180, take away the top angle of 38. And once we've got the answer to that, we can divide it by 2 because base angles in an isosceles are equal. Now we know that that is going to total 142 on the top because we've already done 180 take away 38, or 180 take away 142 in the first step. So that's going to be 142 divided by 2, which is 71 degrees. So both of these angles in the base of the triangle are 71 degrees. And again, we would want to write our reasoning for that. I'm going to label it. I'm just going to label it like this by drawing an arrow. And I'm just going to put base angles in an isosceles are equal. So base angles in an isosceles are equal. There we go. Right, we've got one more step, and the final step here is quite a nice one. We just have 3 angles there that are on a straight line. So the straight line that I'm looking at is this straight line here along the bottom. And we have 2 of the 3 angles. We've got 71, 38, and our missing angle. So I can do 71 plus 38, which is 109, and then take that away from 180. And we have already said in the first step, angles on a straight line add up to 180. So there we go, that is equal to 71 degrees. And you'll probably notice 71 is the same as the angle in the isosceles triangle in the base of the triangle. And that's because as well, you could, or you might have already spotted that this angle here is another alternate angle as well, obviously pointing the other direction to the other, but that is 71 degrees as well. So we could have, in the final step there, said that that was 71 because it was an alternate angle. So lots of different ways of moving around this shape, but the important part there is we got to the answer, and for every step we give our reasoning based on the actual steps that we took through the question. So when it comes to a reverse mean, we have questions that look very similar to this. It says that there are 10 boys and 20 girls in a class, and the class has a test, and then it gives us this sort of information where it gives us a mean. So it says the mean mark for all the class is 60, the mean mark for the girls is 54. Work out the mean mark for the boys. So when we are told a mean, this is what a reverse mean is. We are going to essentially do the reverse of what we normally do when we are working out a mean. So when we normally work out a mean, we get the total, we divide by how many there are, and it gives us the mean. So for this question here where it says the mean mark for the whole class is 60, well, let's see what piece of information we have. So we take the total score for the whole class, which has currently not been given to us. So let's just call that X. We divide it by how many there are. Now in this case, it's the whole class. So that's the 10 boys and the 20 girls. So in total, that's 30 people. So that's the calculation we would do to work out the mean, and it's telling us the answer to that is 60. So what we can actually do is we can reverse the process here to figure out what the total is. So if something divided by 30 is 60, well, if we multiply by 30, that will tell us what that total must have been. So 3 times 6 is 18, add the 2 zeros, so that's 1,800. So in other words, the total score for the whole class is 1,800. We can take that approach with the next line as well, because it says the mean mark for the girls is 54. Now again, we don't know the total, but something divided by and it says that there's 20 girls, so something divided by 20, that has to equal 54. Again, we can take the same approach now to work out the total, so timesing by 20. There we go, and we can do that relatively easily as well. Timesing by 20, we just need to times by 2 and add the 0, so 54 times 2 is 108. So 108, add the 0, 1080. So that is the total mark for the girls. So now we have the totals. If we imagine we'd been given that in the first place, if it had just said the total score for the whole class is 1,800, the total score for the girls is 1,080, work out the means mark for the boys. Well, to start with, we'd need to take those away from each other to see what the actual total for the boys is. So 1,800, take away 1,080, and 80. Arguably, you might not need to do column subtraction for that. It's not too awful to work this out. So 0 take away 0 is 0. We will have to borrow for that. So 10 take away 8 is 2. 7 take away 0 is 7. And 1 take away 1 is 0. So the total score for the boys is 720. And as you're going along, you can label these things if it helps as well. We had the whole class at the top there, 1,800. We might have labelled the 1,080 the girls, and then we could label this the boys. So to work out the mean, we already know, as we've discussed it, we know in this section here, we take the total, divide by how many there are. Well, in this case, we know the total, 720. We know that there are 10 boys, so we would divide by 10, and that would give us a mean mark of 72. And there we go, that's our final answer for that one. And again, just remembering that you multiply the mean that you are given by how many there are essentially in these questions. If you look at the first one, we took the mean of 60 and times it by 30. And for the second one, we took the mean of 54 and we times it by 20. So all we really did was take the mean, times it by how many there were to find the total. Okay, so when we're looking at averages from a table where we have grouped frequency, like the one that you can see, we are asked to work out an estimate for the mean. Now, if it wasn't group frequency, we could actually work out an actual mean if we knew the actual amounts, but here they've been grouped. So this is about some weekly earnings. Now here you can see with the first group is if they earned 150 to 250 pounds, and there was one of those people. Below that, you've got 250 to 350, and there were 11 of those people. So the reason we would be asked to estimate this is because we don't know their actual weekly earnings. They've been put into groups, but we can make an estimate. And a good mathematical estimate here would just be to take the midpoints of those numbers. So that's what we do. So in between 150 and 250, that is 200. Between 250 and 350, we have 300. Between 350 and 450, we have 400, then we've got 500, and then we have got 600. So for the one lot of the 200, that's a total of 200 for that row. For the 11 lots of 300, well, we'd have to count up 11 300s, but there is a quicker way of doing this. All we have to do is multiply how many there are by that amount that we're using. So one lot of 200 gives us a total of 200. 11 lots of 300 gives us 3300. 5 lots of 400, 5 times 4 is 20, add the 2 zeros is 2000. 0 lots of 500 would give us 0, and 3 lots of 600, well 3 times 6 is 18, and 2 zeros there. So that is the total earnings now, or estimated earnings, of everybody in this table. Now, in order to find the mean, like we've discussed before, you take the total of everybody and divide by how many there are. So we would need to work out the total of everybody by adding all of that together. So if we do that to start with, we've got 1,008. In fact, it would probably be easier, particularly if we're not using a calculator here, to either add pairs of them together or to put it all into one big column addition. So we could pair these up. That would add up to 3,500, and then you've got the 2,000 and the 1,800, which adds up to 3,800. That's a little bit easier then, just to quickly add them together rather than having one big column addition, which you could make a mistake on. So 0, 0, that is 13, and then 367, so 7,300. Now we've got the total, we just need to know what we're going to divide that by. Well, if it's to do with how many people there are, then we would divide by this total frequency. So if we add those up, we get 12, 17, that adds up to 20, so there is 20. So there we go, the calculation we need to do is 7,300 divided by 20. Now, of course, this can be a calculator question. It is quite a common question to be on a calculator paper, but it's not exclusive to a calculator paper, so we might have to do this without one. So here, we can cancel off a 0 top and bottom, and we just have to do 730 divided by 2. So it's not awful to do because we can set that up in a bus stop. 730 divided by 2. 2 goes into 7 3 times, remainder 1. It goes into 13, up to 12, so 6 times, remainder 1. And it goes into 10, 5 times. So £365 would be our answer, and that is our estimated mean for the earnings here, so £365. Now when you get your answer, do check to make sure it makes sense. If we look, £365 would be in this category here. It's somewhere in the middle. It's not the most popular, it's not the modal category. That would be this one with the 11 in between 250 and 350, but it is somewhere in the middle, relatively close to that category, only being £15 into the next category. So there we go. Obviously, as well, you've got some people here. There's 3 people here who are earning a lot more than everybody else. So that is going to skew the mean a little bit as well, because you've got those higher values in that final box there. But there we go. That's how we work out an estimate for the mean. Get the total of each row using the midpoints, and then do the total divided by the total frequency. Okay, so looking at a stem and leaf graph. Now here it says the table shows the heights of a group of students in year 9 and the stem and leaf shows the heights of some students in year 12. It asks us to compare the distribution of heights for the year. So when we are looking at this, there are a couple of averages that we can look at from a stem and leaf. Now over here in the table we are given the median, and then we are also given the least and greatest height. Now the median is already an average that's given to us, so we definitely going to want to compare the median when we are looking at this. When you think about the least and the greatest height, the only thing that you can find from those two is the range. So the range is obviously the biggest, take away the smallest. So from the table we could say 170 minus 150, and the range is equal to 20. So if we are looking at these two averages, they are the two that we can use to then look at this stem and leaf. So looking at the stem and leaf, we always need to look at the key first. Every stem and leaf, whether you're reading one or drawing one, needs a key. And this tells us here that the 15 line 8 represents 158 centimetres. So if we want to find the range from the stem and leaf, which is probably the nicest one to find here, we will find the largest and the smallest value. Now the smallest or the largest, it doesn't matter which one we find first, so we'll go for the largest. That one down there is 182. So we've got 182, the smallest is up here at the start, 158. So to find the range then we would subtract those away from one another. So if we take those away from each other, we get 24. There we go. So straight away you can see the range in the stem and leaf, which is the students in year 12, they have a larger range than the students in year 9 in the table. And that would be our first comparison. So obviously we want to mention the context here. We don't just want to say that range is bigger than that range or 24 is bigger than 20. We want to say the range of heights in year 12, there we go, in year 12 is greater than in year 9. There you go, or you could say that the other way around. There we go, greater than year 9. Of course, you could say the range of heights in year 9 is smaller than the heights in year 12. So that's number 1. We've made part of a comparison. Now we want to have a look at the median. Now the median's a little bit more awkward to find from a stem and leaf, but essentially all we need to do is cross off from either side until we get to the middle. You can apply a statistical method as well. You can count up how many there are, add 1/2 it to find the middle and stuff like that. But I think it's easier with the stem and leaf just to cross off some numbers either side from the start, and then the same amount from the end working backwards until we get to the middle. So I'll do 3 at a time until I can see that I'm getting close to the middle. I'm getting pretty close now. So I'll just do 1 more from the top, 1 more from the end, and that's my middle number or the median right there. So that median is 168. And we know the median from the table from the year 9 students is 165. So our second comparison, we would say the median height in year 12, there we go, is greater than in year 9. So it's greater than in year 9. There we go, there's our 2 comparisons. We have mentioned both of the averages and we have mentioned the context that it is about the heights. So there we go, that's how we would make a comparison, and that's how we would also find a couple of the averages from a stem and leaf diagram. Okay, so look at sampling and bias. Now here we are given a table. It says that Hannah is planning a day trip for 195 students. She has a sample of 30 students where they want to go. So we have in the table 10 students that want to go to the theme park, and then we have the theatre, sports centre and the seaside. It says work out how many of the 195 students you think will want to go to the theme park. Well, if we look at the sample, you can see that in terms of the theme park, we have 10 people that want to go. Now we know that that is also out of 30 students. So as a fraction, that would be 10 out of 30. Now, if we are looking at 195 students, we are going to assume that this proportion or this sample represents the rest of the people. So here we would assume that the fraction, percentage or proportion of the 195 will be the same. Now either we can have a look and think, can we make this fraction out of 195? So can you times 30 by anything easily to get to 195? If the answer is no, then more than likely we could have simplified this fraction. 10 over 30 does simplify, so it goes down to 1/3. You can divide the top and bottom by 10. So writing that in just to show what we've done, we've divided the top and bottom by 10. Now we can get 3 to become 195, otherwise we're not going to be able to actually do this, but we need to figure that out. So the best thing we can do is actually do a bus stop division. How many times does 3 fit into 195? Well, it fits into 19, 6 times remainder 1, and then 5 times into 15, so that would be 65 out of 195. So there we go, our answer for this would be 65 students, as it has gone to 65 out of that 195. Now our assumption here that we have made is we are assuming that the sample represents the rest of the students. So we go that it is a fair sample that represents the rest of the students. So I won't write that down there, so we've mentioned that a few times. But there we go, that's how we will approach these questions where we have a sample involved. So in this question we're going to be having a look at some functional maths where it involves the area of a trapezium. Now with the trapezium, and we are told here that this shape is a trapezium, we can always work out the area of a trapezium as long as we know the formula, which we'll discuss in just a second. But it says here John is going to paint the floor. Each 5 litre tin of paint costs £16.99 and 1 litre of paint covers an area of 2 metres squared. John has £160 to spend. Has he got enough money? And you must show how you get your answer. So if he's going to cover the floor with this paint, we are going to be looking at the area of the floor, how much paint he's going to need to use to cover that area. So to start with, what we're going to think about is how to find the area of this trapezium. Now it's told us it's a trapezium, and these sides here are those parallel sides. So we're going to be working out the area based on those. So the formula for the area of a trapezium is A plus B, which are the 2 parallel sides. You need to divide that by 2, and then times it by the height or the distance between the parallel sides. And you can write that slightly differently as well. You can say half of A plus B times the height. So here to work that out then we will do 10 plus 16, which is 26, divided by 2 is 13. I'm going to write that down straight away, and then times that by the height, which is 7. So we need to work out 13 times 7. We are going to be using a calculator for this question as well. So 13 times 7 comes out as 91. So the area there is 91. The units were metres, and this is an area, so metres squared. So there we go, that is the area of the floor. Now it says here each 5 litre tin of paint costs £16.99 and 1 litre of paint covers 2 metres squared. Well, if we figure out how many of those 2's fit into 91, then we'll know how many litres we need, and then we can figure out how many tins we're going to need. So for this step here, where it says 1 litre of paint covers 2 metres squared, we'll take the 91 metres squared and divide that by 2 and see therefore how many litres we need. Now when we do 91 divided by 2, we do get a decimal. We get 45.5. Now that means we need a decimal amount of litres, which is fine at the moment. We can stick with that, but we may need to adjust this to take into account the fact we might have to buy a little bit more paint if it doesn't fit perfectly into that 45.5. So here, that's 45.5 litres, and we know that 1 litre of paint covers 2 metres squared, so we're going to need 45.5 litres. Now, it says in the question here that a 5 litre tin costs £16.99. So how many of those tins are we going to have to buy? Well, we could count up in 5s, or we could do the 45.5 litres that we need divided by 5. So if we type that in, 45.5 divided by 5, it tells us that we need 9.1 tins. Now, you can't go into a shop and ask for 9 tins and a little bit. If you need a little bit more, you have to just buy an extra tin. So in this particular type of scenario, we would round that up, even though it doesn't follow the rules of mathematical rounding. This is a real-life functional scenario. So we would not be going in and buying 9 tins and then not having enough paint. We would just go in and we would buy 10 tins, and that would just cost us a little bit more. So there we go, 10 tins. Now, obviously, the question was to figure out whether they had enough money. They had £160 to spend. Each tin costs £16.99. We're going to buy 10 of them. So 10 multiplied by the £16.99. That's quite a nice one. We don't need to use a calculator for that. So 10 times 169, £16.99 is £169.90. There you go. So £169.90. That's the total cost. John only has £160 to spend, so does he have enough? So we would say no. John does not have enough. Or no, John does not. There we go. It does say you must show how you got your working, or how you got your answer. We've shown all of our working out. We've made it very clear that it's £169.90 that he needs. So everything is backed up and we have shown how we got our answer. Okay, so this question here is the area of a compound shape. Compound shape just being where two shapes have been put together. And I've also obviously highlighted here that we are going to be using Pythagoras' theorem. Now, it doesn't make that very clear in the question, but quite often when we have triangles involved somewhere within a question, we just need to have Pythagoras in the back of our mind, just thinking that we might actually need to use it somewhere, particularly when we are looking at lengths. So here it says work out the area of this shape, and it says it's a pentagon. It has got 5 sides. Now there's no formula for working out the area of a pentagon that we would use, so we need to think about how we can break this up into 2 different shapes or even more. Now there are 2 ways that you could break it up. You could split this down the middle, look, and it makes 2 trapeziums. The problem is we don't know the length of this side here. So let's have a think if there is another way that we could do it. Well, we could split it up this way. And again, that gives us a rectangle on the bottom that we can work out the area of, but the triangle on the top, we are going to struggle because we don't know this height here. And that's where Pythagoras is going to be involved. But let's start by working out the area of the rectangle. So we have a length of 4 and 8. So we would do 4 times 8, which is 32 centimetres squared. We can then think about how we are going to get that height there. The area of a triangle is the base times the height divided by 2, or half the base times the height. And we know that the base is 8 centimetres because the base is the same as this length down here. So if we think about the triangle, and specifically the triangle I'm going to be looking at is this one here on the left. We could look at the one on the right, but I'm going to look at that triangle there. And if I draw that to the side, there we go. We can see it's a right angled triangle. We have a hypotenuse, or the longest side there is 5 centimetres, and the base all the way along is 8 centimetres. So halfway along, which is what we're looking at just to here, will be 4 centimetres. So 5 centimetres, 4 centimetres, and we're going to work out this height. So Pythagoras' theorem is a squared plus b squared equals c squared. C being the length of the hypotenuse, which we know in this question. So we will do a takeaway instead. So we are going to do 5 squared take away 4 squared, which is 25 take away 16, which is 9. And then we square root our answer, and that tells us our length, so 3 centimetres. So there we go, the height of that triangle, which we can label over here on the diagram. Now that we know it, we know that that is now 3 centimetres. We can now use that to work out the area of that triangle on top. So if this is 3 centimetres, to work out the area of a triangle, base times height divided by 2, well, the base is 8, the height is 3, and then we are going to divide it by 2. So that comes out as 12, so that would be 12 centimetres squared. That is the area of the triangle. So now we have the area of the triangle, the area of the rectangle, and we can add those both together. So 12 plus 32 gives us a total area of 44 centimetres squared. And there we go, there is our final answer. That is working out the area of that pentagon. So on to some surface area of prisms. Now of course we can have the surface area of lots of different types of prisms. You could have a triangular prism, In this case, it is a cuboid, but we can have lots of different types. There's also the surface area of a cylinder. You could even look at the surface area of a cone or a sphere as well. So for this one, the surface area of a cuboid, it's not going to tell you necessarily in a question to work out the surface area. This one here is more of a functional question. It says a sofa has 6 identical cushions and each cushion is this cuboid. The cushions are covered with a protective spray and the spray is in cans, and the label on each can has the information that the spray in the can covers 4 meters squared. Work out how many cans are needed to cover the 6 cushions with protective spray. So this is a more advanced question than just working out the surface area. But to work out the surface area, which is the key bit that we need to do in this question, we just need to look at the different surfaces. Now with a cuboid, we have 3 that we could look at. We've got this rectangle on the front here, which is the same as this rectangle on the back. We have the rectangle on the side, which is the same as the rectangle on this side. And of course, finishing that, we also have the rectangle on the top, which is the same as this rectangle here on the bottom. So what you can do is you can label those 3 up. We've got the one on the front, we've got the one on the side, and we've got the one on the top. And I'm just going to work them out to the side. So for number 1, we have a length of 80 and a height of 18. We're going to be doing this on the calculator, so 80 times 18. Let's actually write that in properly. There we go, 80 times 18. That gives us 1,440 centimetres squared. Onto the one on the side, we have a length here of 95, and the height we already know is 18 because that's on the other side of the cuboid. So that one there, 95 multiplied by 18, and 95 times 18 comes out as 1,710. We're almost there, we've just got that last one to do. So the one on the top, we have this length of 80, and we've got this length here, which is 95. So for that shape number 3, 95 multiplied by 80, and 95 times 80 is 7,600 centimetres squared. Now at this point we have only worked out the surface area of one of each face, so you could either times them all by 2 and then add it all together. What I'm going to do is I'm going to add them all together. So let's add them up. There we go, which is 10,750, and then multiply that answer by 2 to take into account that we do have 2 of each of those faces, and that gives us a total surface area of 21,500 centimetres squared. So if the question just said to work out the surface area, that would be plenty and we would be finished. But this obviously does want us to work out how many of these tins of spray are going to be needed. So we have to go back to the question because it does say up here there are 6 identical cushions. So looking at that, we're going to need to multiply this surface area by 6. That'll give us the surface area of the 6 cushions. So timesing that by 6 gives us a total of 129,000 centimetres squared. And now we can go down and read the question right at the end here, because it says that the spray in the can covers 4 meters squared. So at the moment, this is in centimetre squared. So we need to think about our conversion between centimetre squared and metre squared. Now to get from centimetres to metres, not centimetre squared to metre squared, but to get from centimetres to metres, you divide by 100. And likewise, going back the other way, to get from metres to centimetres, you times by 100. Now, when we are looking at centimetres squared to metre squared, all you do is add squared onto that conversion. So we're going to divide by 100 squared, or times by 100 squared. Now in this question, we are going from centimetre squared to metre squared, so we need to divide that by 100 squared. We can do that on the calculator, and that gives us 12.9. So that's 12.9 metres squared. Now obviously it says the spray can cover 4 meters squared. So you can either divide that by 4, or you can count up in 4s. If we go 4, 8, 12, that would be 3 cans, but it wouldn't quite cover it completely. So we would have to get a 4th can as well. So you could divide by 4 if you wanted to. Obviously you want to show you're working. So if we divide it by 4, it gives us 3.225. 225 cans. We can't buy 3.225 cans, so we will have to buy 4 cans and round that up to make sure that we cover it. Obviously we'll have some left over, but we will have to buy just over to make sure that we cover it. So there we go, that is how you work out the surface area. We've already gone through area of a triangle, so if it was a triangular prism, you would very much take the same approach, but obviously using half base times height for the area of any triangular faces. So there we go, that involved a lot there with some conversions and that functional aspect of seeing how many tins would cover the shape. Okay, so in this question we are looking at volume. Now here we've got a diagram that shows a fish tank and it is in the shape of a cuboid. It says the dimensions of the tank are 50 by 32 by 20, which we can see is 3/4 full of water and sand. It says the ratio of the volume of water to the volume of sand is 5:1. Work out the number of litres of water in the tank. So we've got a lot of maths going involved in this question. We have to know how to do the volume of a cuboid, which is obviously the key skill here, but then we also have fractions and ratios, and also the issue there that it's talking about litres and everything's given to us in centimetres. So we've got a lot to get through in this question, but we're going to start by working out the volume of the cuboid. Now to work out the volume of a cuboid, it's a really nice process. All you do is multiply the 3 dimensions together. So we have 50 multiplied by 32 multiplied by 20. So if we type this into the calculator, we get 32,000, and that is going to be centimetres cubed this time, as we are looking at volume. Now we could have done this a slightly different way, but I'm going to take the approach of working out the overall volume, because it now says that it is 3/4 full of water and sand. Well, we can work out 3/4 of 32,000 to find out what the volume is just up to this point here. So to work out 3/4, we could first work out 1/4 by dividing this by 4. So if we divide that by 4, we get that the 1/4 is equal to 8,000 centimetres cubed. To get from 1/4 to then 3/4, we just need to multiply that by 3. So multiplying that by 3 is 24,000 centimetres cubed. So we now know what the volume is up to that point. We can then start to think about this part of the question where it says the ratio of water to sand is in the ratio 5:1. So sharing in a ratio, we want to know how many parts there are in total. So 5 plus 1 is equal to 6 parts. So we can split this up, this 24,000, into 6 parts so that we can get it in the ratio 5:1. So 24,000, if we split that into 6, just dividing by 6, that gives us 4,000. So each part in that ratio is worth 4,000 and the ratio is 5:1. So if we times them both by 4,000, we're going to get some quite large numbers here when we do this in terms of fitting it below the ratio, but that's going to give us 20,000 in place of the 5 and 4,000 in place of the 1 as we are just multiplying it by 1. So 20,000 to 4,000, and again that's the volume in centimetre cubed. So in other words, the sand here is 4,000 centimetre cubed, and the water just above that is 20,000 centimetres cubed. There we go. So it says in the final lines here, work out the number of litres of water in the tank. Well, we know the amount of water in the tank in terms of centimetres cubed is 20,000. So we just need to know what the conversion is between centimetres cubed and litres. So this is one that you do need to know. It is 1,000 centimetre cubed is equal to 1 litre. So if 1,000 centimetre cubed is equal to 1 litre, we would want to divide that by 1,000 to see how many litres it is. So 20,000 divided by 1,000 is quite a nice one. That just comes out as 20 litres. So there we go, our final answer for that is 20 litres. Now there are other ways that you could have gone about this as well. You could have actually found the height in terms of a fraction. You could have worked out 3/4 of 32. That would have given you the height of this part here. Then you could have split the height into the ratio 5:1 just to work out, and I'm kind of overlapping with the lines here, just to work out the height of the water just there. And then you could have worked out the volume of the cuboid there, which is in the sort of water shape inside the cuboid. or the actual just the water, which is in the shape of a cuboid. So you could have done it that way as well. I do prefer just working out the volume here, particularly as not all questions are, in the same functional sense as this one. You can just have a cuboid that you have to work out the volume of. So it's good for us to practice just doing it that way as well. But there we go, that's how we would approach a sort of more difficult problem here, where we do have this functional aspect and all that fractions and ratio work in between. Now with a distance time graph, you can have lots of different types of questions. You can have to complete the graph. You can have to talk about aspects of the graph in terms of flat lines and what they mean and all that sort of stuff in between. But this question here says, between which two lines does the car travel at its greatest speed? And give a reason for your answer. So we'll talk about that, but we'll talk about the whole journey because that'll explain other questions as well. So you have the car leaving here, where we start at a 0 distance, and it goes up at quite a fast speed there, and then it slows down. So it slows down for this part of the journey here, and then it stops and it just goes along here. Okay, so the distance doesn't change in that part. So you've got 3 parts here. You've got the fastest part of the journey where it's going up much faster. You can see the gradient of that line, or the steepness of the line, is the highest. Then it slows down for this part here. You can see the gradient changes, it's not as steep. And then it doesn't go any further distance for a period of time here where it has stopped. So that's how we would describe the 3 aspects of the journey. So in terms of between which 2 times does it go at its greatest speed, well, that's that first part of the line here, which we can trace down, and you can see it's between 0 and 20. So in terms of our answer here, we would say between 0 to 20 as the line is the steepest, or as the line has the greatest gradient at that point. Okay, as the line is steeper here. Okay, it does actually ask us in part B to work out the speed. So we are actually going to work out the speed of that point there, and there are a couple of ways that we could go about this. So that is a time of only 20 seconds in that particular point, and that is going up to, we're going to have to count this very carefully. So it looks like that's 300 there, halfway in between, and then it's 5 squares to get to 400. So there's a difference of 100. If we split that into 5, that means each square goes up by 20. So that would be 320, 340, 360. So that's 360 metres that it goes in 20 seconds. So if it goes 360 metres in 20 seconds, well, there's a couple of ways that we could give a speed. It doesn't say the units that we have to give a speed. We could give it in either metres per second, or we could give it in metres per minute. It doesn't actually say. So it's completely up to you at this point. If we want to find it in 1 second, which would be a speed in metres per second, then we would just need to divide both of these by 20, as that is in 20 seconds at the moment. So we could do 360 divided by 20, and we can obviously do that to the side. If you want to work that out, you can do 36 divided by 2 instead, which does make it a little bit easier, but that comes out as 18 metres per second. So 18 metres in 1 second would be written as 18 metres per second, and that'd be our final answer for that one. Of course, you can use a speed, distance, time formula as well. Speed is equal to distance divided by time. The distance was 360. We divided that by 20, and it's given us our answer of 18 metres per second. So there we go, 18 metres per second. If you wanted it, or wanted to work it out in a speed per minute, for example, you could have multiplied them both by 3. That would have got you to 60 seconds, which would then got you a speed in metres per minute. That would be fine as well, as it doesn't give us any units that we have to follow. But there we go, there is looking at a distance time graph. So when looking at linear graphs, we may or may not be given a table of values that we have to fill in as well. But this one here doesn't give us a table, and it says on the grid, draw the graph of y is equal to 3x minus 2 for values of x from -2 to 4. Now it may not even give you this, so it usually does, but where it says values of x, it might not give you that, and you have to find it from the graph over here, and we can see the graph goes from -2 to 4. More often than not, it does give it to us though, but if it doesn't, then we know where to find it. Now for this, I would always usually advise drawing a table of values. So we know our values of x, we know it has to go from -2 to 4, so we can draw all the numbers 1, 2, 3 and 4. We need to find the values of y, then we'll know the coordinates and where we can plot them. Now this equation here is just a code that tells us how to find y. It says that y is equal to 3x's take away 2. Well, if we don't have a calculator especially for this, I would always start over here with the positive number. Just it's easier to put the positive values into that equation. So 3x means 3 times x, well x is 4, so we would do 3 times 4 and then take away 2. 3 times 4 is 12, take away 2 gives us 10. And then we would just follow the same process for each number, just replacing the 4 here with our new x number. So for the next one, we would do exactly the same to find this position here, but we would do 3 times 3 and then take away 2. Well, 3 times 3 is 9, take away 2 is 7. We can then do the same for the next one, replacing the 3 again, but this time we are looking at where the x value is 2. So for this one here, 3 times 2, take away 2, well 3 times 2 is 6, take away 2 is 4. Now once you have done a few values for a linear graph where it is going in a straight line, we can actually spot a pattern. And you can see here that it is going down in threes. So if it's going down in threes, we don't need to continue doing our substitution, we can just start subtracting 3. So 4 take away 3 is 1, take away 3 is negative 2, take away 3 is negative 5, take away 3 is negative 8. So from there we can now just plot the points. Of course, if you did start on the left, you could follow the same pattern as well. You could spot that it's going up in threes this way and just continue the pattern. So if you can just continue the pattern, we can then look at plotting the graph. So plotting this graph, we have negative 2 and negative 8, negative 1 and negative 5, 0 and negative 2, and you might even be able to start spotting a pattern in terms of the coordinates. So the next one we have 1, 1, 2, 4, 3, 7, and 4 and 10. There we go. Once we have plotted all the points, you would get a ruler and a pencil and join these up using a perfect straight line, and that would be your graph drawn and that question finished. Now a few things to take note of. You can also see that this number at the end, this negative 2, is linked to this point here. That's called the y-intercept, so it's where it crosses the y-axis. That's going to help us if we're working the other way around. And also this pattern of plus 3s happens to be the number in front of x. Now that is called the gradient. It shows us how to draw these points as well. You can go 1 across and 3 up, and you can see there is a little staircase pattern that goes up by 3 each time. So we're going to have a look at a question like that as well, but that would be how we would go about plotting a graph using a table of values. Now when we are approaching one of these questions essentially in reverse, because this has drawn the line for us and it says to find an equation for L. Now when we are finding the equation of a line, it's important to take note that all the equations of lines are in the form y is equal to mx plus c. Now, like we discussed very quickly on the last one, c in this instance here is our y-intercept. And the y-intercept can be found really easily. You can see it's just down here where the line crosses through negative 6. So finding the first part of the equation, we know that y is going to equal something something minus 6. And that right there is our y-intercept. The only other thing we have to find is the gradient. Now the gradient we can find in one of two ways. We can either find two coordinates and calculate the gradient between them, or we can look at the pattern between those two coordinates. So if I pick two nice whole number coordinates, you can see that there's one there, one here, and one there. We're only going to choose 2 of them, so I'm going to select this one here, it doesn't matter which 2 we choose, and this one here. Now that coordinate there is 2 across, 0 up, so 2, 0, and this coordinate here is 1 across, 3 down, so 1, negative 3. To find the gradient between those 2 points, you do the change in the y coordinate divided by the change in the x coordinate, which you can also call the rise over the run. So if we have a look, we have a triangle here where our rise goes from negative 3 to 0, so that's a rise of 3, and the run goes from 1 to 2, so that's a run of 1. So the change in y is 3, the change in x is 1, and 3 divided by 1 is 3. And that is our value of m. So this value here is our gradient, so this would be 3x minus 6. So there we go, m is the gradient, and we use the formula, the change in y over change in x, to work that out. So our equation to finish this question is y is equal to 3x minus 6. Now, although I did that really nicely using this triangle here that only had a run of 1, you could actually have used the other coordinate and had a slightly larger triangle there, and that's where the formula really does help. So for this, we would now have a run of 2, and this would have a rise of 6. So if I did use those two coordinates, I would still have done the change in y 6, the change in x 2, and 6 divided by 2 is still 3. So it doesn't matter which ones we choose, as long as we use whole number coordinates. We wouldn't want to use one here where we can't quite tell what the rise or the run is from that point, so we do want to use those nice whole numbers to find it. But there we go, that's how we go about finding the equation of a line from a diagram. So we can also have some more complex problems where we are looking at gradient of a line. Here it says A is the point with coordinates 5, 9 and B is the point with coordinates D, 15. The gradient of the line AB is 3, work out the value of D. There's a couple of ways we could think about this, but let's try and think about what this might look like. So if we imagine this is coordinate A, and this has the coordinate 5, 9. Now we know the gradient is 3, so we know it's going to be sloping upwards. And it's going to get to this coordinate B. Now I know B is going to be up here because the y coordinate is 15, and the y coordinate was 9 on the previous one, so we know we're going up to get to point B. So this here has the coordinate D, 15. And we know from the last question, to find the gradient, we would find the rise and the run, or the change in y over change in x, and that would give us the answer here of 3. So can we work out either of those? Well, it goes from 5 along to D. So we don't know what the run is, but we can work out the rise or the change in y, which goes from 9 to 15. To get from 9 up to 15, that would be a rise of 6. We don't know what the run is, so let's call that x for now. But we do know what the gradient is. And we know that if we do 6 divided by x, whatever that x number is, that we would get the answer 3, as it's told us the gradient is 3. Now that's a relatively nice problem to solve. If you look at that, 6 divided by something is equal to 3, well we know that x will have to equal 2. 6 divided by 2 is equal to 3, so we know the distance there must be 2. Now, the not so nice part of this question is that kind of feels like you found the answer at that point, but not quite, because that is the run. The run here is equal to 2. So if we get rid of the x and we replace that with 2, we now know the distance that it goes across, and it started on 5, it goes 2 across to get to D. So to get from 5 over to D, that is a distance of 2 across, so we know that D will have to equal 5 plus 2, which is equal to 7. So the coordinate up there would be 7, 15, but the value of D is 7. So we go, we could write D is equal to 7, or we could just write 7, but we have found that using that idea behind the rise, change in y over change in x, or the rise over run. Now when we are looking at transformations, there are 4 main transformations that we need to look at. This one here says describe the single transformation that maps shape A onto shape B. Now this is a translation, which just means to move a shape. And when we are moving a shape on a coordinate grid like this, we write it using a vector. So here we're going to have a look at what the vector is and how we write it. So we need to pick a point on the shape. So to get from A to B, we need to also pick the same point. So in order for that shape to move, we don't want to be matching the top right there with, say, the bottom left, because that's not going to give us an accurate movement. If we matched it to the bottom left, actually the shape would be down here. So we do need to match up the perfect points, but from there, all we actually have to do is count how many squares across and down it goes. Now we could go down and across, or across and down. We're going to get the same answer either way. I'm going to go across. So 1, 2, 3, 4 jumps. Check the scale. That is going up by 1 each time, so I'm happy that that is a jump of 4 across. And it's going down by 1, 2, 3. Now when we go down, we do say minus 3. As you can see on the axes here, positive numbers go up and negative numbers go down. The same on the x-axis, positive numbers go to the right and negative numbers go to the left. So we tend to just give the same symbol in front of the number in terms of the direction we're going in. So down is negative and left is also negative. So as a column vector, in terms of the movement, the top number goes is the x movement, so the left and the right. So we have gone 4 across, and the bottom number on a vector is the y movement, or up and down, and we've gone down by 3. So that vector there in words means 4 right, and it means 3 down. And of course, if we change the 4 to a negative 4, that would mean 4 left, and if we changed the negative 3 to a positive 3, that would mean 3 up. So now we have the vector. The description here we would have to say is a translation, which is the mathematical word for moving. So a translation, ideally then say by the vector, and then write the actual vector. So 4 and negative 3. So that would be a full description there of what's happened. And of course you could be asked to describe that the other way around, so from B to A, and that would just be obviously slightly different because we would be going left and up, which would change the symbols to negative 4 and positive 3. Okay, so when it comes to a rotation, you are allowed to use tracing paper for these questions. So for a question like this where we are having to describe a rotation, it's a little bit trickier than if we are to do the rotation ourselves. So typically a question that's asking us to do it ourselves will tell us the point of rotation, in which case we can put the tracing paper over the top, we can trace the shape, we can put our pencil onto the point of rotation, such as the origin, and then we can spin the paper round, and obviously it will tell us whether to go 90 degrees, clockwise or anti-clockwise, or potentially 180 degrees. Now with this type of question, it's asking us to actually describe what's going on. So we'll do the same first step. We're trying to look from P to Q. So here, if we were to rotate the triangle, and hopefully you can see it's going 90 degrees anti-clockwise, but if we rotate it, it means we're going to have to find the point of rotation. So here, if we use the origin and we go 90 degrees anti-clockwise, you can see that it doesn't land on the shape. So what you have to do is you have to pull it back, you have to readjust your pencil, put it into a different position until you find the point, and once you've found the correct point, you'll notice that when you do your rotation, it does land over perfectly on top of the shape. So this one here, it went 90 degrees anti-clockwise, and you can see that my pencil is on the point 0, -1. So the way we would describe this, we would just say it's a rotation 90 degrees anti-clockwise about the point 0, -1. Okay, so in this one we have a reflection. So it says Kyle reflects triangle A in the axes to get triangle B. He then reflects triangle B in the line y is equal to x to get triangle C. Amy reflects triangle A in the line y equals x to get triangle D. She is then going to reflect in the x-axis to get triangle E. Okay, there's a lot of descriptions here. Amy says that triangle E should be in the same position as triangle C. Is Amy correct? Well, without actually going about doing these reflections, that's very hard to figure out. So we do need to actually go about doing this. So we'll start with Kyle. We'll do that in one colour. So Kyle is going to reflect it in the x-axis to start with. Now the x-axis is this line here. So when we reflect that, we're going to count each point and make sure we do that perfectly. So 1 square away is down there for that first point, and that's 3 squares away for the next point. And you can see then that that's going to line up, and it has reflected, and that is now triangle B. He then reflects triangle B in the line y is equal to x. Now y is equal to x is a diagonal line that goes perfectly through all of the same coordinates, so 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc. And that is our reflection line y equals x. Now reflecting in one of these lines is not very nice to do. What I would normally recommend doing is actually rotating the paper in front of you so that the line is pointing upwards, because in this particular reflection we are going to have to count diagonally along the squares. So that's 1, 2 diagonals along and a half. We want to go the same distance away, so the half first and then an extra 2 diagonals away, and gets us to there. We're going to do the same with the other points. I'm going to go for this bottom left one, so that's 1, 2, 3 diagonals. So 1, 2, 3 diagonals gets us to here. Obviously we've drawn all over the diagram now, so I'm going to get rid of some of these, just so it's going to help me to finish off this last one. And the last one is sort of overlapping the shape, which makes it even worse. So I'll do it in a different colour for this one. Let's go 1, 2, 3 and a half. And we'll do the half first, and then an extra 3. So 1, 2, 3 away. So that point gets us up to there. Now that is reflecting diagonally in a line y equals x, which isn't very nice to do at all. Some people don't like the way it looks, it doesn't quite look right, but just trust the process. You are reflecting the perfect distance away at the perfect 90-degree angle to the reflection line. But to us it's almost at a 45-degree angle, which is very strange for us to actually visualise. But there we go, that is triangle C. So that's the first one done. We are now going to look at the next one where Amy is reflecting. So Amy reflects triangle A in the line y equals x to start with. Well, that's much nicer than that last one because it's already connected to the line y equals x. So at least one of those points isn't going to move anywhere. We've got this point here to reflect, half a square away. So half a square away gets us to there. And then this point, which is 1.5 diagonals away, 1.5 diagonals away gets us to there. So there we go, that is the one in the line y equals x, and we can join that up. And we're going to call that triangle D. And there we go. And then it says she's then going to reflect triangle D in the x-axis to get triangle E. So again, the x-axis is down here, and we're going to reflect that in the x-axis. So we'll start with that bottom point, which is 3 away. 1, 2, 3 gets us to here. The next one's 4 away, so that gets us to there. And then the top left point on that triangle is also 4 away, which gets us to here. So there we go. It's very close to triangle B, but triangle E is not in the same position. So we have shown how we've got our answer, because we have done all the reflections on the diagram, but we just need to answer, is Amy correct? So we would say no, Amy is not correct. There we go. So no, Amy is not correct. And we've shown all of our reflections on the diagram, including one on a diagonal line. Now looking at an enlargement. Now typically exam questions tend to be a little bit easier than this one when we are looking at enlargements, but this is quite an interesting one when we have a scale factor of 1/3. Typically exam questions just sort of ask you to expand or enlarge the shape by a factor of 2, sometimes not even from a particular point, so they can be a lot easier than these ones. But if we can do this one, then we can both enlarge by a integer scale factor and we can work in reverse as well. So this one says to enlarge it by a scale factor of 1/3 from the centre 0, 1, which is just down here. Now to do an enlargement, all we actually have to do is count the vector to a particular point. So to get to that point there, thinking about vectors again, we go 3 across and 3 up. Now, if we are going to do a scale factored version of that, all we have to do is apply the scale factor to that movement. So if it is 3, 3 to get to that point, well, 1/3 of that, so if we do 1/3 of that, we would get 1, 1. So our new shape, all we need to do from that centre of enlargement that we've already got, we'll get rid of this, we just need to do the vector 1, 1. So 1 across, 1 up, and that takes us to here. Then we just have to draw the shape in 1/3 of the size. So you can see if you look at this shape, it goes up by 6, while 1/3 of that is 2. So we'd go 2 up, and I might do this in a different colour, just to differentiate that from that vector. So we would go 2 up. The line along the top there is 3 along, so we would go 1 along. The same for here, 3 along, so we'll do 1/3 of that, which is 1, and then we can join it up. And there we go, there's our new shape. Now you can see from this as well, and this is why I like this question, we could also think about this in reverse. So if that was the shape that was given to us, the one that we have drawn in, it might have said enlarge the shape by a scale factor of 3 from the point. And it's basically just the reverse of what we've done. So if we pick a point, we go across 1 and 1, that is the vector 1 and 1. If we want to do a scale factor of 3, we would just multiply them all by 3. Actually, I better not write it like that because it kind of looks like a power the way that I've written it, but I'll write it more like this. So timesing by 1/3, and here we are going to be timesing by 3. So when we times by 3, our vector is going to be 3, 3. And we already knew that, so going back to our original position, we would go 3 along, 3 up, and then we would draw the shape in 3 times the size. Again, just counting the sides, this is a length of 2, timesing that by 3 gives us a length of 6. So this is a really good question for looking at it in both ways. But it is quite rare for a fractional scale factor to come up on one of these ones, but you can get some nice questions where it does just ask you just to enlarge a shape and put it anywhere on a grid. But there you go, this is a great question to have a look at just for thinking about how you would approach it using a vector. Now we've already looked at a little bit of sharing in a ratio, but ratios are a standalone topic as well that can come up just as a ratio question. This is a really good one. It says the perimeter of a right angled triangle is 72 centimetres and the lengths of its sides are in the ratio 3, 4, 5. Work out the area of the triangle. Now, as it is a right angled triangle, if we were to draw a sketch of a right angled triangle, which is going to help a lot with this question, we know that the area of a triangle is the base times the height. So essentially we want to know what's this length here and what's this length here, and for working out the area of the triangle, that hypotenuse there, or that longest side, doesn't really interest us. So we'll have a look and we'll share this in the ratio 3, 4, 5. We should already hopefully remember from earlier as well, we've got a total there, so that adds up to a total of 12 parts. So to figure this out, we'll start by doing 72 divided by 12, which tells us each part is worth 6. Well, our ratio is 3 to 4 to 5. Each of those numbers we will need to multiply by 6 to get to each part. So 3 times 6 is 18, 4 times 6 is 24, and 5 times 6 is 30. Now we know the longest side there is going to be our hypotenuse, that's the one we don't need, but we don't actually know where 18 and 24 go. Now because of the way we work out the area of a triangle, it doesn't actually really matter. Now because of the way that I've drawn it, the base looks bigger, so I'll put 24 there and 18 here, but essentially we are just going to multiply those numbers and then divide our answer by 2, so it doesn't really matter what order we put them down in. So to work out the area of a triangle, we'll do 18 times 24, then we're going to divide our answer by 2, and that's our area of the triangle. So let's work this out on a calculator. We've got 18 times 24, that gives us a total of 432 that we need to divide by 2. So dividing that by 2 will give us a total area here of 216 centimetres is our units, squared as its area, so 216 centimetres squared. These questions where we have fractions, percentages and ratios are relatively common questions, and we already saw one earlier where we did have fractions and ratios involved, but this has all 3. It says Daniel bakes 420 cakes. He bakes only vanilla, banana, lemon and chocolate. 2/7 of the cakes are vanilla, 35% of the cakes are banana, and then lemon and chocolate are in the ratio 4 to 5. Work out the number of lemon cakes Daniel bakes. Well, to start with here, it does give us that 2/7 are vanilla. So straight away we can ignore the other 2. We can kind of work through these in stages. We've got 1, 2, 3 things to work out, and the lemon cakes that we're looking for are in that very last piece of information. So we will get there, but we'll start by working out 2/7. So starting with number 1 there, we could work out 1/7 to start with. 1/7 of 420, that's a relatively nice one to work out because 42 divides by 7, that's 6, so that would be 60. Okay, just dividing by 7. We want 2/7, so to get from 1/7 to 2/7, we just need to multiply by 2, so 2/7 is going to be 120, and that is vanilla. So we've got 120 vanilla cakes. The next step, we've got the percentage, we've got the 35%, so we'll label this over here, so step 2. 35%, well, if we are going to work out a percentage of an amount, we'll always start with 10% or 1%, but I like to start with 10%. So 10% of 420 would be 42 cakes. We are going to want to get to 35%, so getting 5% is going to be helpful as well. So half of 42 is 21. And now we can use that to get to 35%. So we're going to want 3 of the 10%, 1 of the 5%, and that's going to get us to 35%. So it doesn't matter how you work that out, you can do multiplication. I'm just going to add 3 of those together. So 42, 42, 42, and the 21. That gives me 35% in total. So 2, 4, 6, and 7, 4, 8, 12, 14. So that's 147. And there we go. So that's 147, and that was for the banana cakes. There we go. Right, so we're almost done. We now know how many vanilla and banana cakes there are, but now it says the ratio of the number of lemon cakes to the number of chocolate cakes is 4 to 5. Now it's a little bit of a different explanation here, because previously it said 2/7 of the cakes, 35% of the cakes, so that was referring to the total. But here in this third step, it's only referring to the lemon and the chocolate cakes. It's not referring to that as a ratio of 420, it's a ratio of the lemon to chocolate. So we need to actually work out how many lemon and chocolate cakes there are in total. So we're going to have to add together what we've already worked out, 120 and 147. That gives us a total of 267 cakes. We've got 420 in total, so taking away what we already have, so taking away 267, let's see what that gives us. We're going to have to do some borrowing, so 10 take away 7 is 3, borrow again, 11 take away 6 is 5, 3 take away 2 is 1. So we have 153 cakes, and they are going to need to be split in the ratio 4 to 5. So again, thinking about sharing in a ratio, that is 9 parts in total, so 153 divided by 9, let's work that out. So 9 goes into 15 once, remainder 6. So 9 goes into 63 7 times, which means each part in the ratio is worth 17. So from here, we've got the ratio 4 to 5. Each part we've just worked out is 17. So 17 times 4 would give us 68, and 17 times 5 would give us 85. Now, of course, we only need one of those because it says work out the number of lemon cakes. That was the ratio of lemon to chocolate. So lemon is our number on the left, and our final answer is 68. So there we go, a lot to work out there. We had a fraction of an amount to start with, a percentage of an amount, and then what was left over was split in the ratio 4 to 5. So you might need to read through that one again, but a lot of the worded questions like this are very similar, where we have to work out a ratio, a fraction, and a percentage in order to solve a problem. Okay, so when looking at combining ratios, it doesn't necessarily say in the question that you need to combine the ratios. Sometimes it can say two separate ratios and ask you to write a 3-part ratio, or sometimes in a question it might just give you 2 different ratios and expect to know, or you to know, that that's something that you're going to need to do. So this one here says the number of houses and the number of flats are in the ratio 7 to 4, and then it says the number of flats and the number of bungalows are in the ratio 8 to 5. It then says there are 50 bungalows in the village, how many houses are there? Now there are a couple of different ways that you could use to work this, and you can actually just about get there without actually combining these ratios. But whenever we see something like this, where we have 2 ratios where we have the same thing in both, in this case we have flats in both, we are going to take an approach where we combine those ratios. Now the way that I approach them is I tend to write the 3 things out. So we've got houses to flats, and then the other one is flats to bungalows, so we can put the bungalows after the flats there. But because these 2 separate ratios, we can't combine them straight away. Now the scenario where we could combine them straight away is if this number here for the flats and this number here for the flats in the other ratio, if they were the same, we could combine these straight away, but in this case they're not, they are different. So houses to flats, it says is 7 to 4, and then flats to bungalows is 8 to 5. Now what we need to do is look at these 2 middle numbers, so we have a 4 and an 8, and think to yourself, what can we do to make that number the same? Now it might be that you have to change both of the ratios, but in this case we can actually make the 4 become an 8 by multiplying that ratio by 2. So if we do multiply this top ratio by 2, the 4 would become an 8, and the 7 would become 14. Now that all the numbers are the same, they can, or all the numbers in the middle are the same, they can actually just be combined. So we can just write 14 to 8 to 5. And that's our new 3-part ratio. So from here, we could, if we were told the total, we could actually share in that ratio now. If we were told the difference between some of them, we could obviously find the difference between them now. But this question here says that there are 50 bungalows in the village, which is this number at the end, which is a 5. So to get from 5 to this new amount of 50, we just need to think what we have to multiply by. Now, hopefully you can spot that that is timesing by 10, but if you're not sure, you can always do 50 divided by 5, which tells us that we've multiplied by 10. So as with all ratios, we're now just going to multiply each of the numbers by 10, and we get 140, 80, and 50. We can now answer any question. So this particular question says, how many houses are there in the village? Well, houses is the number at the end here, so that would be 140. So again, just combining the ratios there by making sure that the overlap number, in this case, which was the flats, the thing which is in both of the ratios, making that number the same, and then essentially just sort of squeezing that ratio together and putting them as a 3-part ratio. So there we go, that was a bit of combining ratios. Okay, so when it comes to direct proportion, all we need to remember with these types of questions is that as one goes up, the other goes up as well, or as one goes down, the other goes down. And that's just what things in direct proportion mean. So here it says we're building a wall which is 5 meters long, and the complete wall is going to be 8 meters long, and wants to know how many bricks we need. So it's going to go up proportionally in the same way that we use the bricks for the first 5 meters. So we can write this out thinking about this in a sort of table way, although we don't need to draw a table. We can say that 5 meters is going to need 300 bricks. So in order to figure out how many bricks we're going to need for 8 meters or for anything else, we want to go down to how many bricks we're going to need for 1 meter. So to find the amount of bricks we need for 1 meter, we can divide this by 5. If we divide the 300 bricks by 5 on the other side as well, that's going to tell us how many bricks we'll need. So 300 divided by 5, you can do bus stop division to the side if it helps, but that's going to be 60 bricks. Now, because we need now 60 bricks per meter, we can pretty much answer any question for however many meters the question is asking about. We need to read this carefully though, because it says how many more bricks does Jack need? So we don't necessarily need to jump now down to 8 meters, because we only want to know how many more that we need. So to get from 5 to 8, that's going to be an additional 3 meters. So we only really want to know how many bricks we're going to need for 3 meters. To get from 1 meter to 3 meter, we multiply by 3. So the exact same on the other side. To get from 60 bricks to our new amount of bricks, we're also going to multiply by 3. So 60 multiplied by 3 gives us 180. So our final answer would be 180 bricks. So you can see there, all I've done is I've made a comparison to the side where I have done the same to one side as I have done to the other. So as the meters went down, the amount of bricks is obviously going to go down. It's quite logical. And then as the amount of meters goes back up, the bricks go up in the same proportion. So that's going to be really helpful, because when we look at inverse proportion, we're going to do something very similar to this, but in a slightly different way, because with inverse proportion, that's the opposite. It means as one goes up, the other goes down. But that's what we're going to have a look at now. So when it comes to inverse proportion, when we are looking at these, we can take exactly the same approach, but it's understanding that this is about inverse proportion. It says here it would take 120 minutes to fill a swimming pool using water from 5 taps. How many minutes will it take to fill the pool if only 3 taps are used? Well, hopefully it seems quite logical here that if we were to use less taps to fill up a pool, then the amount of time it takes to fill it up is going to go up. So you can see there straight away that as one goes down, the other goes up, and that's what makes it inverse proportion. So we can do the same thing with a kind of almost table. We can say here, and I'll put some titles for this one this time. I'll say here, over here we'll put the minutes, and over here we'll put the taps. So at the moment we have 120 minutes, and that is for 5 taps. Now, just like before, we want to figure out how long it would take for 1 tap. So over here, again, we would just divide by 5, and that's going to take us down to 1 tap. But we don't want to divide the minutes by 5, because if we're using 5 times the amount of less taps, or 5 times less taps, then the time is going to be 5 times more. Or in other words, we're going to have to actually multiply by 5 on this side. And 120 times 5 is going to be 600 minutes. And if you think about that logically, it makes a lot of sense. If we use 5 taps and that takes 120, well, it would take 5 times longer if we are only using 1 tap. So it makes sense that as we divide down to 1 tap on the one side, we would multiply by that same number on the other side for the amount of minutes. As well as that then, if we're going to go to 3 taps, because it does say how long will it take if only 3 of the taps are used, well, to get to 3 on the right hand side, we're now going to multiply by 3. So on the other side, it's going to be 3 times faster, or in other words, we're going to divide by 3. So that will give us an answer of 200 minutes. So our final answer for that question is 200. And hopefully you can see the link between what we've done on either side of the table, and it's quite logical there that as one goes up, the other goes down. Now, of course, any of these questions, we are assuming in our working that the taps are running at the same rate. And that leads us into part B, because if one of the taps was running faster than the other, then obviously the time could change. It could be more or less. Our working out could be completely wrong. If we turn off the best tap, the one that fills up with the most water in the fastest amount of time, then obviously it's going to make a big impact. So in terms of our assumption there, we would want to say something about the rate of the water. So we could say we assume the taps run at the same rate. There we go. And that same rate can be used in quite a lot of these questions to do with inverse proportion, particularly when it's talking about workers or builders and how long it takes them to actually complete a job. So we do assume in those scenarios that the workers are working at the same rate as well. So there we go. There is a bit of inverse proportion. Okay, so when we are looking at best buys, here's another example of where things are in direct proportion. So here, milk sold in 2 sizes of bottle. So 4 pints cost £1.18 and 6 pints cost £1.74. Now these are 2 different deals, but the amount of pints in the bottle is proportional to the price. So in other words, it means that in the first option there, we are paying a certain amount for 1 pint. Obviously we're buying 4 of them, but the price for 1 pint is the same for all the 4 that's in there. The same as the 6 pints, each pint costs the same, but it's broken up into 6 pints for this one. So when we are looking at which is the best value for money, we want to know which we are paying the least for that 1 pint. So for the one on the right, if we start with that one, we could actually just divide that by 6. So there are 2 different ways of doing this, and we will talk about both, but we could do £1.74 divided by 6, and that's going to tell us the cost for 1 pint. Typically these are calculator questions. There is a non-calculator method as well, but we'll do the calculator method to start with, so we'll just type that in and we get 0.29, which is 29 pence per pint. For the one on the left, the 4 pints, we'll take the same approach. This will be £1.18 divided by 4. Again, just typing that in on the calculator, £1.18 divided by 4, it comes out as 0.295. So you can see straight away that these are relatively close to one another, and they typically will be on these questions. It's also getting us to have a look and see if we understand decimals. So you could balance them both out with zeros at the end of a decimal if you need to, so that they both have 3 decimal places. Or you might just be able to recognise here that this one on the right has a 0 at the end, and the one on the left there has a 5 at the end. So the 6 pints is better value, and we would say 6 pints is better value, and that finishes it off, and we have shown all of our working like the question has asked there. So we've got clear working that shows why it's better value. So there we go. The other method that you could take to do this as well, you could actually look at which is the lowest common multiple. So here we've got 4 pints and 6 pints. The lowest common multiple of 4 and 6 is 12. So you could say, well, if we buy 12 pints of this, that's multiplying it by 3 lots of 4, or if we buy 12 pints of this one, which would be multiplying it by 2, which one do we get for the cheaper price? And that's something you can do quite nicely without a calculator, because you can just add them up using column addition, particularly when it's only 3 and 2. So there we go, 2 different methods that you could do, both absolutely fine, but we are then looking at the better value by either comparing the cost of 1 unit or the same amount of both in a different form, like here where we could have 12 pints. Now when looking at exchange rates, it's really important that we just understand how to move between one currency to another. This is quite a long question because it has 2 different exchange rates in, so we just need to match them up carefully. But it says Gina pays or finds out the price of a CD box set in 3 different countries, or a CD box set in 3 different countries. The price is £98 in the UK, $134.99 in the USA, and €139.99 in Germany. It says the exchange rates are, and then we've got the pounds to dollars, and we've got the euros to pounds. And we've got the exchange rate here shown in two different ways. One where it's £1 to the currency in dollars, and the other one where we have the euro currency as 1 and the exchange rate into pounds. So we need to think logically about these exchange rates, because typically with exchange rates you just multiply by the exchange rate to go abroad and divide to come home. But this here has given us an exchange rate as if we were already abroad. So that's the exchange rate you'd get if you were actually in Germany. You would have the exchange rate coming back to pounds. So here, when we are looking at which is the cheapest price for the box set, we actually need to put them all into the same currency. Typically in these questions we can move them all back into pounds. So when we are looking to move them back into pounds, let's start with one. We'll start with this one here, and we'll change the dollars amount first. So you can see in the actual exchange rate that the pound number, not the value, but the number itself is smaller than the dollar number. So if it's smaller than the dollar number, we know if we take 134.99, we only have two options. We can either multiply by 1.43 or we can divide by 1.43. Now, you can type them both in on a calculator, but you will see the one that gives us the logical answer that takes us back to a smaller number in pounds is if we divide by 1.43. So if we do that, divide by 1.43, that takes us back to, in pounds, £94 and 39 and a bit pence. I'll put it to three decimal places, 398. It's very unlikely that these are going to come out to four decimal places to the same value. They could, but it's very unlikely. So I'm going to leave it like that because we should be able to make a comparison. You can see that that is cheaper than in the UK, so we already have one option that might be the better one. Now for the next one, we are given euros as 1 and then pounds as the smaller number again this time. So we know that the pound number is going to be smaller than the euro number. Again, they have the same value, but the actual number itself is smaller. So here, when we are actually going from our 139.99 euros down to pounds, this time if we divided by the exchange rate, we'd actually get a larger number. So because it's the sort of exchange rate that we would get when we were abroad, we kind of have to do it in the opposite way. So here we do have to multiply by the 0.73. That is going to give us the smaller number that we are looking for. So 139.99 times 0.73, and that gives us £102. And I'll keep it to three decimal places. We've got 19, and this sort of rounds to a 3 because it's a 7 after the 2. So there we go. We didn't actually really need to write it to as accurate amount of decimal places because you can see here it's very clear which is the cheapest. We have this one in the USA, which has given us a £94 price compared to the £98 in the UK and £102 in Germany. So in terms of buying the box set, we would want to buy the box set from the USA, and we've shown how we got our answer because it's all up here and it's all nice and clear in terms of our working out. It says here though that Gina lives in the UK. Why might your answer to A not be the best country for Gina to buy the box set from? This is an interesting question because there's not really any maths that we need to do for this. It's more just a logical question in terms of why it might not be the best idea if we want a box set that's only £3.70, £3.60, 70 different to buy from the USA. Why might it not be the best place to buy it from? Well, if we are living in the UK and we want to buy a box set, that's going to cost money to be shipped over to the UK. And it might be that that postage price is pushing it over the top of the price in the UK. It might be that it's free, but it might be that that postage does actually cost money. It does say why it might not be the best place. So you could give any options here that are logical and reasonable. I think the best option in this scenario, though, we would just say that the postage prices might make it more expensive. Okay, so there we go. There is a question looking at exchange rates. Okay, so moving on to some recipes. It says here Dion needs 50 grams of sugar to make 15 biscuits. She also needs 3 times as much flour as sugar and 2 times as much butter as sugar. Dion is going to make 60 biscuits, work out the amount of flour she needs. Well, it says here in this first part we need 3 times as much flour as sugar. So if we need 50 grams of sugar to make 15 biscuits, how many grams of sugar are we going to need to make 60 biscuits? Because straight away we obviously have different amounts there. Well, if we go up in 15s, you've got 15, 30, 45, 60. So to make 60 biscuits, we're going to need to use 4 lots of that amount of sugar. So the first thing to do is 50 grams multiplied by 4, which would give us 200 grams of sugar for the 15 biscuits. So we need 200 grams of sugar, and it says obviously just here we need 3 times as much flour as sugar. So we'll take the 200 grams of sugar, we need 3 times as much, so multiplying that by 3, and that gives us 600 grams of flour. So there we go, that's our final answer for that one, 600 grams. For the next part, it says Dion has to buy all the butter she needs to make 60 biscuits. She buys the butter in 250 gram packs. How many packs of butter does Dion need to buy? Well, up here, it says that we need 2 times as much butter as sugar. So if we needed 200 grams of sugar and we need 2 times as much butter as sugar, we would times that by 2. And that comes out as 400 grams of butter that we are going to need. But of course, we have to buy this in 250 gram packs. So if you were using a calculator, you could do 400 divided by 250, and it's going to come out as 1 point something. But thinking logically here, if we buy the first pack of butter, we'll have 250 grams. If we add another pack of butter, because obviously we don't have enough, we get to 500 grams. Now that's enough butter now to actually make this. Obviously we have 100 grams more than we need, but we're not going to be able to make it with only 250 grams. So we will have to buy 2 packs here, and there we go, that would be our final answer, 2 packs of butter, and that's going to allow us to make this recipe. So there we go, that is a little bit of recipes, but typically with recipe questions, you are looking to see how much is needed to make one. And we can apply a direct approach or a direct proportion approach in order to do that. So here, if this 15 biscuits at the top needed 50 grams of sugar, well, what we could have done is we could have done 50 grams, divided it by 15, and that would have told us how many grams we needed for one biscuit. From there, we could have multiplied that by 60, because we were making 60 biscuits, and that would have also got us to that 200 grams of sugar. So we can also take that approach, but this was quite a nice one as it did tell you exactly what proportion you needed, and to get from 15 to 60 was also quite a nice version because it was just a multiple of 4. But if it wasn't one that you could jump to straight away, for example, if we had to go from 15 biscuits down to, and this said 70 biscuits, that would have been a lot more complicated for us to do. So we would have probably taken that approach there by doing 50 grams divided by 15 to see how much we needed for one biscuit, and then just multiplied it to whichever one we needed. But there we go, one variation of a question looking at recipes. Now we've already looked at a bit of Pythagoras theorem within this video, but this is an interesting question here as we move more into Pythagoras and trigonometry. So it says triangle ABC has a perimeter of 20. It says AB is 7, BC is 4, and by calculation deduce whether triangle ABC is a right-angled triangle. Now, if we actually draw a triangle and we label it ABC, so we imagine a right-angled triangle, we don't really know where the numbers are just yet, but we can call it A, B, and C. Now here it says A to B is 7. So that's actually a longer length than the length of 4, but we don't actually know which is the longest length on this triangle. So before we put any of these letters on and just start putting the numbers anywhere, let's think about what the other length is as well. Because it does say here that the perimeter, which is all of the lengths on the outside added together, is 20. Well, if we do 7 plus 4, that equals 11. And therefore, 20 take away 11 would tell us that the final side that's not been given to us is 9 centimetres. Now that is the longest side, so we would say this is 9 centimetres. We could say this one's 4 centimetres, just because of the way that I've drawn it, it does look like it would be the shorter of the sides, and this one would be 7. So it says A to B is 7 centimetres, and B to C is 4 centimetres, so we'd have to have this one as B, this is A, and this is C. Just based on the way that I've drawn it, of course you could draw this in lots of different ways. You could put the 7 on the left, the 4 on the bottom, but that matches up with what they've given us in the question. So it says, by calculation, deduce whether triangle ABC is a right-angled triangle. Well, to know if something is a right-angled triangle, we can use Pythagoras' theorem, because we know with Pythagoras' theorem that a squared plus b squared is equal to c squared, and we have been given the values of the shorter sides. So because we've been given those, we can have a look and see, well, does 4 squared plus 7 squared, does that equal c squared or 9 squared? Is it equal to 9 squared? Now if we test this out, we'll see what we get. Well, 4 squared is 16, 7 squared is 49, and 9 squared is 81. So what's 16 plus 49? Well, add the 6 is 55, add the 10 is 65. So does 65 equal 81? Absolutely not. They are not equal, so we would say that that is not a right-angled triangle. So just say deduce whether it's a right-angled triangle. So we would want to give a description here to say no, it's not a right-angled triangle because that is not equal. You could also have said, in other words, like if we were working out the length of this one here, we could have actually done the square root of 65 and see does that equal 80, or so does it equal 9, and of which case it doesn't. Okay, so two different ways that we can obviously show that final step there, but that was using a little bit of Pythagoras in a slightly different way. Now this has some Pythagoras theorem which is almost hidden within the question. It tells us here that we have a trapezium. A square has the same perimeter as this trapezium. Work out the area of the square. Give your answer to 3 significant figures. Well, if we knew all of these lengths, we know a square has equal side lengths. So for example, if they all added up to 40, we would know that all of these were 10. And then we could obviously work out the area of that square by doing base times height or length times width. We don't actually know what the perimeter is though, because we are missing this side here. So we have a missing side on a trapezium. So this is similar to a question that we've looked at before, but we have to split this up to find a right-angled triangle. Now obviously it doesn't say in the question that we're going to be using Pythagoras anywhere. This is one of those questions where you just have to spot that, oh, actually there's a right-angled triangle that's connected here that I could perhaps use Pythagoras on. Now we know that this 5 here is the same as the height over there because that's now just a rectangle and a triangle put together. So that is 5 centimetres, and for this length down here, that's going to be the difference between the top of the rectangle, which is 7, and the full length along the bottom here, which is 9. So the difference between those is going to be 2 centimetres, and now we have a right-angled triangle that we can use Pythagoras for. So now we can use a squared plus b squared is equal to c squared. We've got a or b, we can use in either order. So 2 squared plus 5 squared, which is 4, plus 25, which is 29. And the final step now, we are actually going to have to square root this time. So the square root of 25, this would be a calculator question. So we're going to type it in. The square root of 29, is 5.38, and a lot more decimals. So 5164807. Now at this point in this type of question, you might think that you've made a mistake there, because that's going to be quite a horrible number now to add up and get a perimeter for. But it does give us a massive hint in the question that we are going to get quite a long decimal. It says just here, give your answer correct to 3 significant figures. That gives us a massive hint that there are going to be some long decimals involved. So now we can actually work out the perimeter of this shape, which is going to be the same as the perimeter of the square. So if we add them all together, 5 plus 7 plus 9 plus this number 5.385164,807. Let's add those all together on the calculator. So add 5, add 7 and add 9. That gives us an answer of 26.38516,481. So that is the perimeter of the square. The square has 4 equal side lengths, so we can actually divide that by 4, because that perimeter, which we can write up here, 26.385, and some more decimals, we can divide it by 4. That'll tell us each of the side lengths, as the square has equal side lengths. So divide by 4, and we get a side length of 6.596, and some more decimals, but I'm just going to write a few of them down, because to find the area of a square, we're just going to times those two numbers together. Or in other words, I could actually just put squared with it on my calculator rather than typing it all in again. So I'm actually just going to press answer squared. But you could just do, obviously write the whole number down and make sure you times them both together. So I'm going to do 6.596 and the rest of the decimals, and I am just going to square that. So I'm just going to press the x squared button on my calculator, and that gives me an area of 43.51105. There are some more decimals, but I know in the question it only wants my answer to 3 significant figures. So if it wants my answer to 3 significant figures, I can go 1, 2, 3, chop it off after that, and then just apply my rules of rounding. So I didn't need to write all of those decimals out. So it's a 1 after the line, so that's going to be 43.5, and the answer there is in centimetres squared. So again, there you go, using a bit of Pythagoras, but also involved in a problem there where we had to find the overall perimeter. We had to split that then into the perimeter of a square and work out the area of that square. So a lot of maths going on in that question, but hopefully a good problem there involving some Pythagoras. Okay, so when it comes to trigonometry, obviously with trigonometry there are different ways that you can learn this. Now, what a lot of people do like to do is use a formula triangle. So regardless of which method you use, you will be okay using a formula triangle if you know the actual trigonometric ratios. But for the purpose of everyone here, I will use a SOHCAHTOA formula triangle. There we go, just writing them all out. So we have SOH, CAH and TOA. So to determine which one we're going to use, we need to label the sides. We know already from Pythagoras that this side here is called the hypotenuse. Opposite the angle in the question is called the opposite, and the other side is called the adjacent. You don't need to label up all 3 sides, you only actually need to label the side that you've been given and the side that you're looking for. Now this question here is asking us to work out the length of AB. And the length of AB is this length just here on the left of the triangle. So we have that as the opposite. We are given the hypotenuse, so actually we didn't need to label the adjacent. We've got the 2 sides in the question, O and H. So we look at our formula triangles, we can see that the O and the H is in the sine triangle. So we don't need this one and we don't need this one. So as we are looking for the opposite, if you're using a formula triangle, you cover that up. And we know there that it is S times H. Now S stands for sine, and we put the angle with that. In fact, when you press it on the calculator, most calculators will open a bracket for you to remind you to put the angle in with that. So when we put 38 in, we also need to close the bracket, and then we're going to multiply that by the H, which in this case is the hypotenuse. So we just need to type in sin 38 multiplied by 16. There we go, and we have our answer, and this one comes out as 9.8505, a few more decimals after that, but the question does say to give your answer to 2 decimal places. So again, we'll chop this off after the second decimal, and we get an answer here of 9.85, as it says 0 afterwards, so 9.85, and the question's in centimetres, so that would be centimetres. Now obviously there are 6 different variations that you could have for working out a side length. In this question, if it had have asked us to work out the adjacent, well in that case we wouldn't have needed the opposite. And to work out the adjacent now we would have A and H is in our cos triangle. So instead we would have used this formula up here. We would have been looking for the adjacent, so in that case we would have still covered up the top there and it would have still been a multiplication. If in either of those scenarios though we were looking for the hypotenuse, then we would have had to have done a divide. And the good thing about the formula triangles, it does show you which goes on the top and which goes on the bottom of your divide. So there we go, lots of different variations of trigonometry there. If you're not sure about all of them, obviously you can check out the full video on that, but that is just a reminder there for one version of a trigonometry question where we are looking at side lengths. Now when we are looking at angles, we still use a very similar process. We just do a slightly different button on the calculator, which allows us to find an angle. So I'm still going to write down my SOHCAHTOA triangles, so SOH, CAH, TOA, and I'm still now just going to label up the triangle. So in this particular question where we are looking for an angle, and it has been highlighted for us, it's the angle ABC, we're going to label up the sides. So this is our hypotenuse, opposite the angle's not given to us and we're not looking for it, so we don't need to label the opposite, we're just going to label the adjacent. Now for the adjacent and hypotenuse, that is in our centre triangle there, A and H, and we are not looking for the A or the H. This time we are looking for the angle. So we cover up the C and it tells us that we need to do A divided by H. Now looking at the numbers we've been given, A is 7 and H is 11. But of course if we type that into the calculator, that's just going to give us a decimal. So in order for the calculator to know that we are looking for an angle, we do the inverse operation, or in terms of the reverse. This time we're looking for the angle rather than the side length. So all you have to do, and you should hopefully be able to see it on a calculator, just above the cos button, there is a little cos minus 1. And to get that, you normally have to press shift or some form of button that allows you to access that. So once you've done that, you will have cos minus 1 on the calculator, and it will open up a bracket to remind you to put something in there. So we're going to put the fraction in. You can write that as a divide as well, and then close the bracket. So you can either write it as a fraction, or you can put 7 divided by 11. But if I press shift cos and then put the fraction in, 7 over 11, close the bracket, and we get an angle now, which has come out as 50.478 and a few more. I'm not going to write them all because this question does ask us to round it to 1 decimal place. So if I cut it after the first decimal, this time we have a 7 after that first decimal place, which is going to round it up. So it is going to go to 50.5, and this question is asking for an angle, so we would give that as 50.5 degrees. So our final answer would be 50.5 degrees, and of course there are 3 variations of this question where you could be given either the opposite and the hypotenuse, in which case you'd use sine, the adjacent and the hypotenuse where we use cos, and you could be given the adjacent and the opposite, in which case we would use tan. Now moving on to some probability. Probability from a table is always quite a nice one. Probabilities have to add up to 1. 1 meaning absolutely certain, and then anything between 0 and 1 being somewhere in between. So here it tells us that we have some cubes. It tells us that there are blue, red and yellow cubes, and we can see that in the table. It tells us the probability of blue is 0.2. It says the number of red cubes in the box is the same as the number of yellow cubes in the box. So we know here that these two are going to be the same. So to find out what we're missing, because we know these have to add up to 1, we would do 1 take away 0.2, and that leaves us with 0.8, which is going to be split between those two boxes. As they are equal, that makes it nice for us to do, we can just divide it by 2. Of course, that could be split in a ratio. It's not in this case, but it could be split in a ratio as well. For example, it might say it's in the ratio 1 to 3. In which case you'd have to share in a ratio like you normally would. We'd add them together, we'd have 4 parts, so we'd divide it by 4 and then split it by 1 and 3, or multiply it by 1 and 3. So here both of these probabilities are 0.4, so completing the table there, quite nice for us to do. Now, just because this is written in decimals, don't forget that these actually are just percentages or fractions as well. So 0.2 is the same as 20%, or you could write it as 2 over 10 or 1 over 5. I'm writing it as 2 over 10 because it's 2/10. We don't necessarily need to write it in its simplest form, but there we go, different ways that you could write this. It's going to help us potentially with a part B question. So here it says there are 12 blue cubes in the box. Work out the total number of cubes in the box. It could be asked one of 2 questions here. Sometimes it can say, you know, we're going to pick a certain amount of cubes out, or there are a certain amount of cubes in the box. What's the probability of picking a blue, or how many blues are in there? So, but this has actually told us specifically that there are 12 blue cubes. So we know, and you can either use a decimal percentage or a fraction here, but we know that 20% of the cubes is equal to 12, because blue is 20%, and that is also 12 blue cubes. So to work out the total number, well, the total percentage is 100%. So how do we get from 20% to 100%? Well, we times by 5. Of course, you could write that as 0.2 and think, how do we get from 0.2 to 1? And that would also be timesing by 5. But here we go, we can actually just times both sides by 5. That will give us the total, and 12 times 5 is 60. So our final answer here is 60. Now, of course, that question could be given to us in reverse. It could say there are 60 cubes in the box. how many blue cubes are there? And in that circumstance, if it had told us that there was 60, we would want to work out what 20% is, which is the blue cubes. To do that, we'd start by working out 10%, so 10% is 6, and then we could times that by 2 and get that 20% is 12. So two different ways that you could do it. I do like that percentage method more in that scenario because you could probably get from 0.2 to 1 relatively nicely. But there we go, two different options that you could have in a Part B question similar to this. So when looking at probability on a tree, it's very similar when we are thinking about probability from a table, except instead of the table adding up to 1, we sort of have these pairs of branches that add up to 1. So we've got one pair of branches there, we've got another pair of branches here, and another scenario where we have a pair of branches there. So read the question carefully. It says here we have a round pencil case and a square pencil case, and we have the titles up here as well where the round and square pencil cases are. It says there are 4 blue pens and 3 red pens in the round pencil case. So for the first one, the round pencil case, we have 4 blue and 3 red. So we can write the probability on those branches here where it's asking us to complete the probability tree by writing them as fractions. You can write them as decimals as well. I wouldn't recommend decimals if you can write them as fractions, because fractions is a lot easier just to sort of write them down here rather than trying to convert them into a decimal. So for blue, we have 4 blue pens, and that's out of 4 plus 3, which is equal to 7. So that's going to be 4 out of 7. For the red pens, they have to add up to 7 anyway, but it tells us that there's 3, so that's going to be 3 out of 7. Now that's the round pencil case done, because on the second part of the tree, these are both to do with the square pencil case. We just have two different scenarios. So this scenario over here is if we chose a blue pen out of the round pencil case, and this scenario here is if we chose a red pen out of that pencil case. So when we are drawing the next probabilities on, we have got 3 and 5 pens. 3 plus 5 is equal to 8, so there's 8 pens in that pencil case. 3 of them are blue, so 3 out of 8, and 5 of them are red, so 5 out of 8. Now it doesn't matter which one we pick out of the round pencil case, the square pencil case doesn't change, so down below here we have the same two probabilities, 3 out of 8 and 5 out of 8. And that is our probability tree constructed. We can now calculate probabilities of roots on this. So for this one, it's asked us work out the probability that the pens Samina takes are both red. So taking both red ones would be taking a red one out of the first pencil case and then taking a red one out of the second pencil case. So we almost go on a little journey through the tree, and all we do is take the probabilities that we've passed through, so 3 out of 7 and 5 out of 8, and multiply those together. So the calculation we need to do is 3 out of 7 multiplied by 5 out of 8, and multiplying fractions is one of the nicest topics that we can do because all you do is multiply the top. 3 times 5 is 15 and 7 times 8 is 56. So our final answer for this probability is 15 over 56. You don't have to worry about simplifying a fraction in these types of questions. It doesn't say to write it in its simplest form, and actually not simplifying it is more useful because it tells us there that there are 15 different ways of doing this because there are 3 reds and 5 reds in the other one. So there's 15 different combinations out of a total possible combination of 56. So here we don't need to simplify, and nice and easy there just to multiply those fractions. Now of course you could get a slightly more complex question. It could actually ask you to work out the probability of both blues. That would be the same, but if it said different colours or the same colours, that could potentially be a little trickier because in that scenario you could have multiple branches that you need to work out. So for example, if it said different colours, you could take out a blue and then a red, and likewise you could take out a red and then a blue. And in that scenario, you would need to work out both of those roots and you would add your answers together. But quite nice because they both would have 56 on the bottom. In fact, if we did that scenario, this one we would get 20 over 56 as it's 4 times 5 on the top. This one's 3 times 3 on the top, so we'd get 9 out of 56. And all you would do is combine those two, and that would be 29 over 56. And that would be the probability of getting different colours. And likewise, you could do that for the same colours as well. If you had 2 blues and 2 reds, you could also do that. So there we go, that is some probability trees. Now, probability trees can also have decimals on. We treat them in exactly the same way, but this question is actually asking us something that's gone wrong with this probability tree. So it says here, when a biased six-sided dice is thrown, the probability it will land on a 4 is 0.65, and the biased dice is thrown twice. Amir draws this probability tree, but the diagram is not correct. Write down 2 things that are wrong with the probability tree diagram. Now, there's only a couple of things that can go wrong. As we've already mentioned before, these branches here have to add up to 1. So we can have a look at these and we can see if they add up to 1. Let's look at the first one. We have 0.65 and 0.25. You might be able to spot already, but if we add those two together, let's see what we get. 10, 6, 7, 8, 9, that only adds up to 0.9. So this probability here is incorrect. It tells us in the question that the probability of landing on a 4 is 0.65, so this here should be 0.35. So that is the first mistake that we can see. As well as that, the only other thing that can go wrong on a probability tree is that these ones could then be potentially misdrawn. Now you can see they've got the 0.35 in both of these, but they've been switched around. It says in the question the probability of land on a 4 is 0.65, but here it says the probability of landing on a 4 is 0.35, and the 0.65 has been put down here. So these have been switched around. On that part of the branch, they've got it correct on this side of the branch, but here they have been switched. So we could say 0.65 and 0.35 are switched or in the wrong positions, and that would be our second reason there in terms of what's gone wrong here. Now, if you were working out probabilities from this type of tree, obviously if we had the correct numbers, so 0.35 here instead, you could also do this with decimals. So it might say what's the probability of it not landing on a 4 twice. So here we would go, well, that would be going down this route and down this route. That passes through 0.35 on both routes. So to work out that probability, you do 0.35 multiplied by 0.35, most likely on a calculator, and obviously giving your answer to that. Obviously this didn't ask for that, but you can actually do the same process that we've just looked at, but with decimals. Okay, so looking at a Venn diagram where we have some set theory involved, we just need to get all of these numbers in the correct place. So it says here at the start, and we have that symbol there which just refers to the universal set, or in other words, all the numbers that need to go into our Venn diagram. It says odd numbers less than 30. Now that gives us quite a lot of options. We've got 1, 3, 5, and I would recommend writing them out, but this one is a bit of a pain because we have a lot of numbers to write out, but I would recommend it even if there's a lot of numbers there, because the worst thing you can do is do all of this and then miss some numbers out. So there we go, that's all the odd numbers less than 30. It tells us that in A we have 3, 9, 15, 21 and 27, and in B we have 5, 15 and 25. Now the first thing you want to look for is there a number that's in both, and you can see here 15 is actually in both of them, and 5 and 25, which are in B, they're just in B. So in the intersection, in the middle of the Venn diagram, we can put the 15. We can then cross that off from our main list because we're not going to need to use that again. And we're going to take this similar approach as we go through them. So in A, we can put the remaining numbers, so 3, 9, 21 and 27. We can cross them off from our main list, 3, 9, 21 and 27. Then put the numbers that were in only B, so 5 and 25. Again, crossing those off the main list, 5 and 25. And then all of those remaining numbers need to go on the outside, inside the box, but outside of the circles. So we have 1, 7, 11, 13, 17, 19, 23, and 29. And then go through and cross them off, make sure you've not missed any. So 1, 7, 11, 13 are all in the diagram, 17, 19, 23, 29, they're all crossed off, quick double check, and they're all done. For part B here, it says a number is chosen at random from the universal set, so from all of these numbers in the Venn diagram. What's the probability that the number is in set A, U, B? Now we've got two things that we need to really know when we are looking at set theory. So you've got the U, which refers to the union. Now the union, in terms of a Venn diagram, I won't draw the box around the outside, but the union refers to everything here, everything in the middle, and everything here. So we're just looking at the numbers that are inside the circles, including what's in the middle. You can have the symbol upside down as well, and that refers to the intersection. And the intersection, hopefully that seems quite logical with the language, but the intersection is only referring to the numbers in the part that's where it's crossing over. So in this question here, it is looking at the union, and the union we have got, and if we go through, we can count them up, 1, 2, 3, 4, 5, 6, 7 numbers that are in the union. So we know that as a probability, that will be 7 out of, and then we can count how many numbers there are in total, either from our list or we can count from the diagram, 8, 9, 10, 11, 12, 13, 14, 15. So that is going to be 7 out of 15. Again, if it did simplify, we wouldn't need to, but that would be the probability that it is in the union. If it had asked us the probability of A and B in terms of the intersection, well, there's only one number in the intersection, and that would be 1 out of 15 instead, as there's only one number there. But there we go, that is a bit of Venn diagrams and set theory. Okay, so moving on to some compound interest. Now here it says that Katie invests £200,000 in a savings account for 4 years, and the account pays a compound interest rate of 1.5%. Calculate the total amount of interest Katie will get at the end of 4 years. Now when we are looking at compound interest, it means that the interest we get after the first year is going to be added onto the total, and we're going to get a new amount of interest in the second year. Obviously that makes sense in real life. We want to gain interest on the money that we've already earned in our bank account. So here, what we are going to do is use a calculator method for this one. Now, if we think about how we would approach this, well, let's think logically about what we have. So at the moment, in the bank account, we've got £200,000. And let's think about that as being 100% of the money that we have. After the first year, we are going to add on an additional extra amount, and that's going to be the extra 1.5%. Now, in terms of finding a number that we can multiply 200,000 by to increase by 1.5%, we call that a multiplier. And to find it, we just need to think logically about what this means. Now, if we gained 0% interest, so nothing ever changed, we just had the same amount of money, you could say that we multiplied it by 1. And that's what this 100% represents. Or in other words, if we do 200,000 and multiply it by 1, we still have 200,000. We just get the same amount, and that would be equivalent to a 0% interest rate. In other words, it doesn't increase by anything. Now, if we want to increase that multiplier, we can add extra bits onto the 1. So for this one, we want to increase by 1.5%. So we need to think about what decimal we would add after the 1 to increase by just 1.5%. And we can do that by turning this percentage into a decimal. Now it can help when doing this to think about some sort of easier decimal, maybe something like 1%. 1% as a decimal, remember you can just divide it by 100 on the calculator to convert it to a decimal, but you will get 0.01. Then the pattern for a 1.5% percentage becomes quite apparent, because if we have 1.5%, it would be 0.01 and then a 5 at the end. So we go right into that third decimal place for this percentage. So here, if we are adding on an additional 1.5%, we are adding on an additional 0.015. And if we add those two together, our multiplier becomes 1.015. And that's the number that you can multiply by to actually increase straight away by 1.5%. Now what you can do, you can obviously just add these together as a percentage. So that would be 101.5% that you have in the second year. And then you can convert that into a decimal by dividing by 1,000. So you can always convert a percentage to a decimal, by dividing by 100, definitely not by 1,000. So there, if we divide by 100, we get our multiplier anyway, or you can think logically in terms of adding the decimal onto 1. So here, if we were to do £200,000 and we were to multiply that by our multiplier here, 1.015, that's going to add on 1.5%. Now we have to do this for 4 years. So You could, if you wanted, write out the answer, repeat the process 4 times so that you have that answer at the end of 4 years. But if you have 4 years, there is a shortcut that you can take, and that is just putting in a power of 4, which of course just means to times by 1.015 4 times. So we'll do it all in one go for us basically on the calculator. If we can save a bit of time in the exam, then we definitely want to stick to that method. So I'm going to type it into the calculator, 200,000 times 1.015, use my power button and put a 4 in there, and we get a final answer here of £212,272, and then it goes 0.7101. Now our monetary system only goes up to 2 decimal places, that's to the nearest penny, so we can either round to 2 decimal places, or we can do something we looked at earlier, which is truncate it to 2 decimal places, essentially just delete anything that comes after that second decimal. It would be fair to use either method. This one here, it doesn't actually matter, because following our rules of rounding, it would be 71 pence anyway, but if it was a 5 after the line there, it wouldn't be incorrect for us to just round it down, even following those rules of rounding. Thinking logically why we might do that, and that's because we haven't actually hit 72 pence of interest, so we wouldn't expect the bank to give us money that we haven't actually earned. So that's the total amount of money in the bank at the end of the 4 years. Of course, this question though did say calculate the total amount of interest. And because we are working out the total amount of interest, that just means that we need to subtract the amount that we started with just to figure out what that extra amount of money that was that we actually got. So if we do that, we can do it on the calculator, take away 200,000, and it gives us our final answer here, which is £12,272, and of course that's 71 pence left over. So there we go, that is compound interest. If you had simple interest is a lot nicer than doing compound interest, because you can just work out the 1.5%, and then that's just what we get every year. So for example, we could work out 1.5% of 200,000, which we can do by using the multiplier here as well, 0.015, or you can work out 1%, 0.5%, and add it together. But if we do 200,000 times 0.015, that tells us that we would get £3,000 interest in the first year. Now, if it was simple interest, of course this is compound interest, but if it was simple interest, we would then just multiply that by 4 and we would get £12,000. So you can see with simple interest, we would obviously get less money there, only £272.71 less, but of course we are getting less there with simple interest. So there we go, there's a bit of compound interest and a little thought about if it did say simple interest. Now you can do compound interest without a calculator, so we'll have a think about how you would do this if you were to do it without a calculator. So it says here, Toby paid £7,500, or invested £7,500 for 2 years in a savings account. He was paid 4% per annum compound interest. How much money did Toby have in his savings account at the end of 2 years? Well, if we're going to do this, I like to split the page up. So here we've got 2 years, so it's not too bad to do without a calculator. So we'll first work out year 1, and then we'll work out year 2, and almost lay this out like a bit of a bank account. So we're going to start off with £7,500, and we are getting each year 4% interest. So we can start by working out some percentages. Now you can either work out 10% and then 1%, or you could just go straight to 10%. I'm going to work out, straight to 1%. I'm going to go for 10%, which is £750, and divide it by 10 again, which is £75. From there, we can get 4% really nicely, because we just need to multiply this by 4 to get from 1% to 4%, and that is going to be £300. So in the first year, 4% is £300, and if we add that on, that gives us a total of £7,800. Now, because this is compound interest, that now means that at the start of year 2, we now have £7,800, and we're going to earn the interest on that new amount of money. So again, I would take the same process, either working out 10% or 1%. So 10% is 780, 1% is going to be 78, and this time, again getting 4%. Obviously, it's going to be slightly higher than it was before, so we need to do 78 times 4. We can obviously do that to the side if we don't have a calculator. 4 times 8 is 32, 7 times 4 is 28, plus the 3 is 31. and then we have £312 that we are earning in interest in the second year. Finishing that off, we just need to add it on to 7,800. You might know what that is, but we can obviously just do that to the side, adding £312 onto that, and that gives us 2, 1, 11, and 8. So after 2 years, Toby is going to have in his bank account £8,112. And of course, if we had to go for a third year here, we would start to get decimals involved, but we would just follow the exact same process, getting 1%, timesing by 4, and then adding it on. So there you go, compound interest can be done as well without a calculator. Now, when it comes to depreciation, this is going to be approached in pretty much the same way that we approach compound interest. Except with depreciation, it's when it's falling in value. So rather than going up in value, it's actually going down in value. And again, we're going to use a multiplier method for this. So here it says Natalia pays £13,995, and then we have Lauren as well. But we have the rate of depreciation for Natalia being 12% and Lauren being 13%. It says whose car will have the greater value at the end of 3 years. So if we have a look at this, now if we think about depreciation, if our car is currently at its 100% of its value, and we're going to have a look at the Natalia's car to start with, which is 12% depreciation. Well, if it's losing 12%, or in other words, we're taking away 12%, we need to think about what percentage is actually going to be left over. So 100% take away 12 would leave us with only 88% of its value. Now, both of these percentages can be written as decimals. This one's 0.12 and this one is 0.88. So whichever one we want to use, we can actually just multiply again by that number, like we did with compound interest, except we multiplied by 1 point something. Here, because it's going down in value, we're taking it away from 1 and multiplying by this 0 point number. Now, if we were to multiply by 0.12, that would tell us what 12% of the car's value was. But we don't necessarily want to know what 12% is, we want to know what it's worth after 12% has been taken away. So if we multiply by 0.88, that will tell us straight away what the value of the car is after it's lost 12%. So we would take the value of her car, 13,995, and multiply that by 0.88. Now that would tell us the value after 1 year. But this question, of course, it says the value after 3 years. So just like with compound interest, we can add a power onto our multiplier, in this case a power of 3, and that will multiply it 3 times for us. So 0.88 to the power of 3, and that gives us a value of Natalia's car, which comes out as 9,537 and 20 pence if we round it to the nearest 2 decimal places. So that's that person's car done. We now need to have a look at Lauren's car. Now Lauren's car costs £14,495 and her car is losing 13% of its value. So 100% take away 13% leaves us with 87%, so very close to the other one. So we would times by 0.87. Again, we are looking at 3 years, so we would still use a power of 3. We just need to type that into our calculator, and then we're going to compare these values. So 0.87 to the power of 3, and Lauren's car is worth £9,545, and it's actually 0 pence at the end. So looking at both these numbers now, it says which car or whose car will have the greater value at the end of the 3 years. Well, we just need to write a conclusion here. You can see that although it's very close, we can see that Lauren's car has the greater value. So we would make the statement, Lauren, you could say Lauren's car has the greater value. You can write a little sentence to go with it if you like, but we've got all the working out there that backs it up, and we can see very clearly that Lauren's car has the greater value. Now part B here says the rate of depreciation assumed for Natalia's car was actually too low. How does this affect the value of her car at the end of 3 years? Well, with this sort of question here, if it's too low, or it's assumed that the depreciation rate was too low, well, let's just imagine, well, what happens if it was too low? What happens if it was actually 20%? You can pick any number, of course. Now, if we actually worked that out, and it was going to lose more value, then the value of her car at the end of 3 years would of course be lower. Now, of course, you can actually work that out on the calculator if you want. If we do that, we do 13,995. We can work it out down here if you want. 13,995 times taking away 20% would leave you with 80%, so 0.8 to the power of 3. And if we type that into the calculator, if that was the case, her car's value would be £7,165.44. So you can see, of course, the actual value of the car has gone down quite significantly. So in terms of how does this affect the value of her car at the end of 3 years, well, the value of her car would be lower. So that's all we'd need to say. You don't really need to give an example there, but the important part is the value of her car would be lower. And there we go, that would be a fine answer for that particular question. Now, when it comes to a reverse percentage, I tend to use what we tend to call the bar model, because I like to think about this visually. Now, it says here, it doesn't say anywhere that it is a reverse percentage. It says Jules buys a washing machine, 20% VAT is added onto the price, and then Jules has to pay £600. What's the price of the washing machine with no VAT added? Now, obviously, the price that we've been given is the current price of the washing machine after some money, or after that 20% was added on. Now, where it asks us what's the price of the washing machine with no VAT added, that's essentially asking us to go back into the past. And if we ever have to find a past price after a percentage change has already taken place, that's what we tend to call a reverse percentage. And drawing this as a bar model can kind of help to visualize that. So if we think about the price of the washing machine, which was originally 100% of its price, and then somebody came along and added 20% on. Well, this new price of the washing machine is now going to be, in terms of the original price, that's now 120% of its value. Now, in a question, it's not, well, this type of question, it's not going to give us the 100% because obviously that was the price with no VAT added on. But the question might have given us this part. It might have said what the VAT was, or it might tell us here the new price. And in this question here, it's told us that the new price is £600. So to find this out, we would want to write down that 120% is now equal to £600, or £600 is equal to 120%. Now, the whole aim of this is to try and get this percentage back to 100%. It's currently at 120. So if you have a calculator, then you can always divide by the percentage. That would take you down to 1%. So you could divide by 120, and then you can very quickly get that to 100 by timesing by 100. And you would just do that to the £600 on the right, and that would get us our price. But this could be a non-calculator question. So instead, we can also try and think about what we would do if we didn't have a calculator. Well, it's always usually quite nice to divide down to 10%. So just think to yourself, what do you have to times 10 by to get to 120? Hopefully you can see that that's timesing by 12. So we would have to divide by 12 to get down to 10%. It might be that we have to use some bus stop to do that. So 600 divided by 12, 12 goes into 65 times, and then 0. So 10% is £50. From there, we can turn 10% back into 100% really nicely, because we just have to multiply by 10. And multiplying by 10, really nice without a calculator, because we just add the 0 on, and the price therefore must have been £500. So our answer here is 500. Now, with reverse percentages, there's quite a lot of different scenarios that you could have. Obviously, we've mentioned two here, where money is added on and you're given the amount that's added on, or you're given the new price, which is the total after it's added on. But with a reverse percentage, you can also have a sale. So it might be that there is something like a 20% sale. And if there is a 20% sale, that's quite similar to when we were doing depreciation, because that's where money is getting taken off. And in a 20% sale, you could be given the 80% that's left, or the 20% that was taken off. So for example, this here, if they said the sale price was, then that would be our sale price, of course, if it's to do with a sale. And this would be almost what we would call the discount, or the money that was actually taken off the original price. Together, of course, they make 100%, just like our previous one, together made 120. So there we go, that would be how we would approach a reverse percentage if it was going up or if it was going down, and this little process on the left here where we are looking at how to break it down to a smaller percentage which can then turn into 100%. And of course, if you have a calculator, you can always divide by the percentage to get 1% and then just times by 100. Now, when it comes to density questions where we can see the word density involved, there are a couple of different ways that you can actually approach these. But as soon as we see that word density, we most likely want to write down our formula. Now, the formula is density is equal to mass divided by volume. And you may also use this in a formula triangle. So you might write this formula out as density is equal to mass divided by volume. Whichever one you use is absolutely fine. Of course, if you use the formula, you need to know how to rearrange that to find mass or volume as well. But let's read this question and see where we need to go with our formula. So it says a gold bar has a mass of 12.5 kilograms. The density of gold is 19.3 grams per centimetre cubed. Work out the volume of the gold bar and give your answer correct to 3 significant figures. Now, that 3 significant figures there does give us a hint that we may have some decimals involved, but we'll wait and see how the question progresses. Now, the first thing that stands out to me in this question, this is what you have to watch out for quite a lot with these density questions, is that the units are given to us in kilograms when it talks about the gold bar and grams when it talks about the density. We want these units to be the same, and it is much easier for us to turn the weight or the mass of this gold bar into grams than it is to try and change our density. So let's turn that into grams. There are 1,000 grams in a kilogram, so we would want to times this by 1,000, and if we times that by 1,000 we get 12,500, 12,500 grams. Now we can actually use our formula just in one go, because if we know that we now have the units all the same, well, to work out the volume, depending on which method you use, you can either cover up the volume on your formula triangle, which means that you know it is mass divided by density, or you can rearrange your formula to get volume equals, and you will see you get mass divided by density as well. So here, the only working out that we need to do is take the mass, which is 12,500, divide it by the density, which is 19.3. We've confirmed that it's all in the same units. So if we type this in on the calculator, divided by 19.3, we get an answer which comes out as 647.668. A few more decimals here, but it did want my answer to 3 significant figures. So here we've got the 6, the 4, the 7 is the 3rd significant figure. So we'll cut it there. So it's also going to be to the nearest whole number. After the line is a 6, so it's going to round it up. That would go to 648. Now, this question was talking about volume, so we need to know what units to give here, and the units are always given to you in the density. So here you are given that it's in grams and it's in centimetres cubed. So here our volume units would be centimetres cubed. And there we go, that would be our final answer, 648 centimetres cubed. Now, if you get one of the harder density questions, you can get something that looks like this, where things are getting mixed together. So here it says the density of apple juice is 1.05, we have the density of fruit syrup, the density of water, and then it tells us some volumes there that are mixed together. So it says we have 25 centimetre cubed of apple juice, 15 centimetre cubed of the fruit syrup, and 280 centimetre cubed of the water. This is a particularly horrible one because we have 3 things that are getting mixed together to make a drink. And it says work out the density of the drink, giving your answer to 2 decimal places. Now, when we have quite a large question like this, the first thing is it asks us to work out a density. So straight away, no matter which method you use, whether it's a formula triangle or the formula itself, we need to write those down so that we don't forget that we do have to use a formula. So density is equal to mass over volume, and we've got a lot of information that we need to sort of figure out here. Now, you could go line by line, trying to match everything up and figure it out, but when we have a mixture like this, I like to put all the information into a two-way table. So I'm going to give myself enough space to have the apple juice, the fruit syrup, the carbonated water, and the actual drink mixture at the end. And then along the side, I'm just going to list the densities, the masses, and the volumes. So I'm going to put here density, mass, and volume. You can, of course, write those in any order. Here, I'm going to put the apple juice, Here I'm going to have the fruit. Here I'm going to have the water. And then at the end, it's called a drink there, but you can put whatever. You can put the total or the mixture, whatever it is that you prefer to write. Now, if I go through, I can actually tick these off and start putting them in my table. So the apple juice, the density is 1.05. The fruit syrup is 1.4. The water is 0.99. Now, the only issue is here, we can't just add the densities together. All of these are getting mixed up and it's going to form a new density that's going to be somewhere in between all three of them. So density is going to tell us how dense that drink is, and each one is different. So depending on how much the volume of each that is mixed in is going to depend what the actual density comes out as. So we'll leave that for the moment and we'll put in some either the masses or the volumes. Now the next bit of information is given to us is volumes. We have 25 centimetre cubed of apple juice. So that's going to be 25 just here. We've got 15 centimetre cubed of the fruit syrup and 280 centimetre cubed of the water. Now, of course, if we pour a load of volumes into a cup or into a jug or something, they will all mix together and we will have a larger volume. And it does tell us that in the question here as well. It does say we've got 320 centimetre cubed. So how would we go about working out the density? Well, we are missing three items here. Now, of course, we know that to get density, you take the mass divided by the volume. Well, we have the total volume right here. The only thing that we are missing to work out the density is this total mass. So we can work out the mass for each of these three items here because we have the volume and the density. And to work out the mass, if we use our formula triangle, we can cover up the mass and it's just density multiplied by volume. So for the three boxes there, we have three things to work out. We have the apple, which is going to be 1.05 multiplied by the volume, 25. We have the fruit, which is going to be 1.4 multiplied by 15. And we have the water, which is 0.99 multiplied by 280. So if we work all of these out, and this is a calculator question, so 1.05 times 25, and that comes out as 26.25. The 1.4 multiplied by 15, that comes out as 21, and 0.99 multiplied by 280, and that comes out as 277.2. Now, of course, masses can all be added together. If you add these three things onto a scale, all of those masses will combine. So if we add them all together, plus 21 plus 26.25, we get a total mass of 324.45. So we're almost done. All we actually need to work out now is the overall density. We have the overall mass, we have the overall volume, and we know, of course, from our formula or from our formula triangle that density is equal to mass divided by volume. So here we want the density, so we would take the overall mass, 324.45, divide it by the volume, 320, and we'll type that into our calculator, and it gives us an answer here. And we're going to have to type that one back in again, so 324.45 divided by 320, and I get an answer that comes out as 1.0139, some more decimals, but again, I'm not going to write everything down because it does only ask for my answer to two decimal places, so we're going to chop there after the 1, and my final answer for this density would be 1.01. Check on the dotted line to see if it's given you the units already. This one hasn't, but check the question. It does say in each of these were in grams per centimetre cubed, so we can write that as grams per centimetres cubed, and that would be our final answer there for the density of the drink. Now, when it comes to speed, distance and time, we can take a similar approach. We can use tables as well to sort of keep all this information together, but you don't always need to. Now here, just to assess the question, it says Ollie drove 56 kilometres from Liverpool to Manchester. He then drove 61 kilometres from Manchester to Sheffield, and then it gives us a speed, a time, and says to work out the average speed for the total drive from Liverpool to Sheffield. Now for this particular type of question, as it is a combination or a mixture of journeys, we can actually draw this all in a table as well. So we can put a table in, we can put the journeys down, and we need to think about our formula when we are looking at speed. So speed is equal to distance divided by time. So distance divided by time. Again, that can be put into a formula triangle, and we can have speed, distance and time. There we go. And we can start putting the information into our table. So speed, distance and time down the side. We have Liverpool to Manchester for our first journey. We have Manchester to Sheffield for the second journey. And we have the overall journey, or the total, at the end. So we've got 56 kilometres from Liverpool to Manchester. That is a distance. So we'll put 56 in here. 61 kilometres from Manchester to Sheffield, another distance. And you can add those two together straight away, because if we've gone 56 kilometres and another 61, well, in total, we have gone 117 kilometres for the overall journey. It says Ollie's average speed from Liverpool to Manchester was 70. So for the speed in the first journey, we have 70. And for the second one, we have 75 minutes. Now, typically, when we are working out these speeds, you can see we have given them, or it's been given to us, in kilometres per hour. But this here has been given to us in minutes. So it is worth converting this straight into hours. That, if you were to write it out, is 1 hour, and it's 15 minutes above 60. So that's 1 hour and 15 minutes. And we need to write that as a decimal as well, so that we can actually type it into our calculator and use it. Now, 15 minutes is 15 out of 60 minutes in terms of an hour. And if we type that into our calculator, 15 divided by 60, that comes out as 1/4, or 0.25 as a decimal. 0.25 is the decimal for 1/4, so not to be confused with 0.15, because it's 15 minutes. Now, obviously, minutes are not out of 100, they are out of 60, as there are 60 minutes in an hour, so it's 0.25. So here, it's 1 hour and 15 minutes, so for that journey, it is 1.25 for the time. Now, we're trying to work out the average speed for the overall journey. Now, the average speed is just up here, and we can get the average speed as long as we have the distance and the time. We have the distance just below, we've got 117, but we are missing the overall time. So the problem here is actually to find that. Now we can find the time in this box just here because we have the distance and the speed. And if we look at our formula triangle to find time, we cover up time, and it's distance divided by speed. So the working out for this box would be 56 divided by the speed, which is 70. So we can type that into our calculator, 56 divided by 70, and that comes out as 0.8. So overall, we have 0.8 hours, 1.25 hours, and in total, if we add those two together, that gives us 2.05 hours. We now have all the information that we will need in order to get the overall speed. We know that speed is equal to distance divided by time from our formula. So here, if we are going to do distance divided by time, we have 117 divided by 2.05, and if we type that into our calculator, 117 divided by 2.05 gives us, and it's not the nicest number here, we get 57.07317. And make sure you look at this very carefully, because this is actually a recurring pattern of 03717. So that would be our overall speed, 57.07317, with a recurring decimal above those numbers. Now, at no point in the question does it say to give your answer to one decimal place or to any certain amount of significant figures. So if it doesn't, we won't round the answer. We'll write the answer as it is, 57.07317, and not forgetting our units, which may or may not be given to us on the dotted line here, but that is in kilometres per hour. And there we go, we would leave it like that, even though it looks a little bit strange. Obviously check through your working, but don't doubt yourself if you do get a strange looking number. As long as you're confident with the methods that you've used there and you've double checked your answer, we should be absolutely fine with that. Obviously take note of the question here, we didn't actually need the speed for this box here, so just because we've drawn a table doesn't necessarily mean that we need every box to be filled in, because for this one we only needed the overall distance and the overall time. But there we go, that's looking at a speed, distance, time mixture. Now if we are looking at speed, distance, time without a calculator, we can do that as well. So this one here says Gary drove from London to Sheffield, it took him 3 hours, an average speed of 80 km per hour. Lynn drove from London to Sheffield and she took 5 hours. Assuming that Lynn drove along the same roads as Gary and did not take a break, work out Lynn's average speed from London to Sheffield. Now here we can obviously think about this in terms of a use of a formula, or we can just think about how these are proportional to one another. So we can kind of do this in a bit of a table. We can have the time, and we can have the distance, and we can put our pieces into here to figure out anything missing that we don't already have. So here we are given a speed which is 80 kilometers in 1 hour. Obviously it took him 3 hours, but we know that in 1 hour he is going to go 80 kilometers. So whenever we see a speed, we can always input it into a table like this, and it's going to help us actually to find any distance in a particular amount of time. So here it tells us that it takes him 3 hours. So to get to 3 hours, we would just multiply each side by 3, and that's going to tell us how far he goes in 3 hours. So that comes out as 240 kilometers, and that's just 80 multiplied by 3. So here we know that Gary has done 240 kilometers. And of course, if you did use a formula triangle for this, you would do the same bit of working out, speed, distance, time, and we are working out the distance. So we would cover this up, and we would do speed times time, and the speed is 80, the time is 3. So it's 80 times 3, which is exactly what we've done. The next part, it says Lynn drove from London to Sheffield, she took 5 hours. Assuming that she drove along the same roads and did not take a break, work out her speed. Well, that means she's done the same distance, but it took her 5 hours. So again, if we were to draw a table, and of course you can use the formula triangle as well, but this is just something a little bit different for you, we can put these both into a table. We know that she did 240 kilometers and it took her 5 hours. To work out a speed, we want this down here to be 1 hour, as speed is given as a kilometre per hour. To get there, we just have to divide by 5. We would do the same to the other side, dividing by 5. And of course, we don't have a calculator for this, so we just need to do a bit of bus-stop division. So we've got 240 divided by 5. 5 goes into 24, 4 times up to 20, a remainder of 4, and then it goes into 40, 8 times. So her speed, she's going 48 kilometers in 1 hour, and that is a speed of 48 kilometers per hour. And there we go, that would be our final answer for that one, 48 kilometers in 1 hour, which is a speed of 48 kilometers an hour. Now, of course, you don't have to write those tables out. Hopefully that's just a nice visual way for you to see what we are doing. But of course, you can stick to using a formula triangle. And in that second step there, we had a time, we had a distance. So we're just doing distance divided by time, which was why we did 240 divided by 5. For part B, it says if Lynn did not drive along the same roads as Gary, explain how this could affect your answer to part A. Well, if she didn't drive along the same roads as Gary, we won't write this out onto the screen, we'll just talk about this one. If she didn't drive along the same roads as Gary, well, she could have driven a higher distance, she could have driven a lower distance. So in terms of our answer to part A, bearing in mind that our answer to part A was an average speed, well, we could say that Lynn could have driven a greater or a shorter distance, and therefore her speed could actually have been higher or lower. And the important part there is to say that it could actually be either. Of course, if she actually drove along more roads or more distance than Gary, then that would have meant that her speed was definitely not the 48 kilometers per hour that we've worked out as. The same as if she took a shorter journey, and of course it ended up taking her 5 hours rather than 3, then again her speed would not have been the 48 kilometers an hour. So it can change dependent. Either way, it could be higher, it could be lower. Okay, so when doing a perpendicular bisector, you do need to use a ruler and a compass for these. When we're drawing them, we are going to leave our construction lines in, but typically a question will say you must show all your construction lines. Now this is quite a unique perpendicular bisector because it's asking us to draw one that also passes through the point P. Typically, if we just have a line, we can do a perpendicular bisector and we don't need to worry about it going through a particular point because we're looking at halfway. But if we have a point P, such as this, we just need to make sure that that point is halfway through the line. So to do this, we would get the point of our compass and put it right on that dot there. So we're going to put that there, and then we are going to extend our compass so that our pencil is touching the edge of the line. If we now spin our compass through that up to the point of the line there, point P is now perfectly in the middle. So if we now construct a perpendicular bisector of our new point, so our new point now is looking at the line from there to there. So what we can do is we can now do a perpendicular bisector as normal. So the way we do a perpendicular bisector, we are going to put our compass point on one of the ends. I'm going to put it on the letter D. I'm going to extend my compass beyond halfway. If I go less than halfway, my arcs are not going to cross over. So I want to go past the point P, somewhere here, and then we're going to do a nice semicircle with both points of the compass, hoping it doesn't go off the paper there. Mine has, so I'm going to go a little bit shorter with mine. So we'll get rid of that one. We'll go a little bit shorter, so it's still past halfway, but hopefully we get a slightly smaller arc. There we go, and just a slightly smaller arc. Now I don't want to change the length of the compass, so I'm going to keep the compass exactly as it is. I'm going to pull it round to the other point, and then I'm going to continue and do a semicircle the other way. And what you'll see is we get these two crossover points. So here I've got one crossover point just here. I've got another one just above that. And then I'm going to get my ruler. I'm going to draw a nice straight line going through those 2 points. And that will go perfectly through the point at the top. Obviously we need to use a ruler and a pencil to do this. It's a little bit more difficult for me to draw a perfectly straight line. But I'm going to do it as best as I can. And that line should go perfectly up and through point P. So there we go, we have constructed a perpendicular line that goes perfectly up through the line CD and into point P. Of course, if you only had to draw a perpendicular bisector, then obviously we'd only do the second steps there. We wouldn't have had to have worried about this curve here, which was cutting the line down so that P was in the middle. Now, when we are looking at drawing an angle bisector, we are obviously going to be given an angle, and the angle may be on a slightly different drawing. It may be on sort of like sometimes quite a common one is like a drawing of a garden, and you have to split the garden sort of via an angle. So here we've just got an angle. It just says to construct a line that bisects angle A. And again, it shows you must show all your construction lines. Now this is probably the nicest construction to do. We just put our compass on the point. We're going to extend our compass. We're going to draw two curves. We're going to sort of draw one here, and we're going to draw a slightly bigger one as well. So bear that in mind. We'll try and draw a small one to start with. So we'll spin the compass round. We get a nice arc. We are then going to extend the compass slightly further. Obviously, I don't want it to go off the line, so just double check that it's not going to be too long there. And we'll draw another arc. We're now done with the compass, so we can pull the compass out of the way. And then we're going to get our ruler and we're going to join up what I call like a crisscross. So the top one there with the bottom one here. You're going to do that using a ruler and a pencil. I'm going to just join it up. And then we are going to join the lower one on the left with the upper one on the right. And we're going to join those up. So if I join those up, again, obviously you're going to use a ruler and a pencil for that. I've not drawn a particularly straight line. So we'll try and make it a little better. There we go. And where those lines cross over, so they cross over just here, that is going to be where we're going to join up to point A. So I'm going to get my ruler, I'm going to join those two together, draw a nice straight line, and that has now split the angle in half. So if that full angle, for example, was an 80-degree angle, we would know that on this side it would be 40 degrees, and on this side it would be 40 degrees as well. Now we've not been given an angle here, we don't have to measure it and get it perfect, we just need to do as best as we can when we are bisecting an angle, and that's the best and easiest process I think for constructing this particular bisector. Okay, so when we are constructing triangles, typically we will be given one length of that triangle. This one here says to accurately draw an isosceles triangle with side lengths 8, 7 and 7. It says one side of the triangle has been drawn for you. So here, the triangle has been drawn to 8 centimetres, or the base of the triangle has been drawn to 8 centimetres, which we can obviously check. Now sometimes, depending on when you print these off especially, depending on the size of the paper that it's been printed off on, the ones that you get might not be actually perfectly drawn to the 8 centimetres, just depending on the scale that it's been cut down to. But for here, when we are practicing, we will go by what the question says, and it's asked us to draw two other side lengths, which are 7 centimetres. If we need to do this, we need to get a ruler, we need to get a compass again, we need to put it on the ruler and measure out our compass perfectly to 7 centimetres. So you can see there the pencil is pointing right at the 7. We can then pull the compass down to one side. So I'm going to put it right on the left there of the triangle. And I'm going to spin an arc all the way up to the top, drawing almost a quarter circle. I'm then going to pull my compass without changing the length because I want it to stay as 7 centimetres to the other side of the line. And I'm going to draw another arc coming down. Again, you don't have to go all the way down to the line there, but you can if you like. So this point here, where they have joined up at the top, and I'm going to just draw a dot on that line, that is the point there that we need to join this up to. So we're going to join the bottom left right up to that point, of course, using a ruler and a pencil, drawing a nice line there. And then, of course, I'm going to do the same on the other side. So using a ruler and a pencil again, I'm going to draw a nice straight line coming up to the top of the triangle. To finish this off, I am just going to label those sides. So this one here is 7 centimetres, and this one over here is also 7 centimetres, and that there has drawn an isosceles triangle. Of course, if we had a different type of triangle, let's imagine instead it said it wanted this one to be 9 centimetres, then all you would have done is change the compass length to 9 centimetres when you were drawing one of the arcs, and then it would have given you one where it was 7 and 9 as the other two side lengths. But there we go, that's how we'd go about constructing a triangle. Okay, so when we are looking at plans and elevations, we are essentially drawing some of the faces or the views that we are able to see from particular directions. Now this is quite a complicated one as it does involve some scale drawing as well. But you can see that we have a 3D shape that's been drawn for us. It says on the centimetre grid, draw the front and side elevation of the prism and use a scale of 2 centimetres to 1 metre. Now we'll worry about the scale in just a second. But for starters, it says to draw the front elevation and the side elevation. And you can see that the front elevation has been given to us here, and also the side elevation has been given to us there. In fact, we'll keep these colour coded. So if we are going to draw the front elevation, it's essentially saying if we were standing perfectly on the side of this shape, what would we actually see? Well, we wouldn't see any of the sides or the top. We definitely wouldn't see the back or the base. We would only see this face here, which is in the shape of a trapezium. So we need to figure out what that's going to actually look like in terms of on the centimetre grid. Now you can probably see to the side it's going to be this sort of shape. We just need to make sure that it's the right size when we actually go about drawing it. So here, if we have been told that 2 centimetres is going to be equal to 1 metre, and we have a 2 or a 1 centimetre grid to draw on, then the 2 metres there is going to be 4 centimetres. Every metre is 2 centimetres, so this 2 metre height is going to be 4 centimetres. So we can start just by drawing that line. So 1, 2, 3, 4 squares, and there we go. Down at the base, that's also 2 metres. So each metre is 2 centimetres. So that as well is going to be 4 centimetres. So we can go 1, 2, 3, 4 along. And then it's hidden behind the lines that I've drawn now. But this little height here is only half of a metre. Every 2 centimetres is 1 metre. Well, this is only half of a metre. So that is just going to be 1 centimetre. So we're going to go 1 centimetre up, and that's that height there. And then that diagonal line, we are given the length of that, but actually we know that that is now just connecting those two together, so we can finish it off without worrying so much about the actual distance there. Now that is our front elevation, so we can label that the front elevation. We don't necessarily need to, it doesn't say to label them, but it does help, I think, just to label them so we know which one we're looking at. Now from the side, we will see this rectangle here, and we will also see, if we are standing over here, of course the height isn't going to just disappear. We will see some of this. We won't see the full length of it because we are not standing above and looking down on it, but we will see some of it above the height of the rectangle. So if we start by drawing the height of the rectangle, again it's 0.5 meters high, which is only going to be the 1 centimeter, just like before. So we can draw this centimeter in. It's a meter long, so that's going to be 2 centimeters, which perfectly fits our scale. 1 meter is 2 centimeters, so that's going to be 2 centimeters along, and then we can join that up and form our rectangle. Now the rest of the shape is going up to the same height. Okay, so obviously the height of our shape is going up to here, so this shape on the side is going to be the same height, reaching that 4 centimeter height. And there we go, that's what it would look like. Obviously taking note of the fact, and we'll label this side first, that we do have this line drawn here. Now that line indicates where there is a change of sort of direction of the shape or depth of the shape. So because the shape starts sort of curving back, it goes up in a straight line and then it curves backwards, sort of starts slanting backwards, we have a change of height there, and that's what that solid line actually represents. So there we go, that would be a front elevation and a side elevation, and that was quite a tricky one because we did have some scale drawing involved with that as well, and taking note of the fact that we had to convert between the meters on the shape to a different amount of centimeters on the grid. It would have been nice there if the scale had been 1 centimeter to 1 meter, then that would have been really nice for us to do, because we know that the 2 meters then would have just been 2 centimeters, and that would have been a lot nicer for us to draw. But for this particular question, we did have quite a nasty conversion there. But there we go, that is plans and elevations. Now, when it comes to bearings, there are a few rules that we need to know. So a bearing is always measured from north, we always measure clockwise, and we always give our answer as a 3-digit. So here, if something like 50 degrees, although that's not a bearing there, if we were to give a bearing of 50 degrees, we would write that as 050. That puts it into 3 digits, and that's what makes it a bearing. Of course, the bearing is measured from north, though. That's just an angle within the diagram, so that's not going to be our answer. But this question here says the bearing of B from A is 070. So if we were to draw that as an angle, well, to get to B from A, we are facing north, we're standing at A, and we would have to turn here 70 degrees. So if we label that on the diagram, that would just be 70 degrees. The question says that angle ABC is 50, that's given to us, and it says that A to B is equal to C to B. Or in other words, this line here, A to B, is the same as this line here, C to B. Which means that that triangle there is an isosceles triangle. So this has got a few bits of maths in here, particularly that part where we have an isosceles triangle involved. It says to work out the bearing of C from A. So again, C from A would be if we were standing over here at A, it's asking us what degree we would have to turn to go all the way down to here. So we should be able to find that out because we can use the idea of angles in a triangle. So with an isosceles triangle, if our top angle is 50 degrees, which is what's given to us in this question, and we know that in an isosceles triangle base angles are equal, well, we can do 180 degrees, take away 50, which leaves us with 130. And if both the base angles are the same, we can divide that answer by 2, and that would give us 65 degrees for each of those base angles. Now in terms of the diagram, that means this angle here is 65, and the total of this angle here, ignoring that north line, would also be 65 degrees. So for this question, it's asked us to find the bearing of C from A, which just means if you're standing at A, how do you get to C? Well, facing north and going clockwise, we would go 70 degrees to get to that first line, plus an additional 65, and that would give us a total angle of 135 degrees, and that'll be our final answer for this question. It's already a 3-digit number, so we don't need to worry about making it a 3-digit number. It's just 135 degrees. Of course, if the answer did come out as a 2-digit number, something like the 65 degrees, you would write your answer as 065. So when you are labelling it on the diagram, it doesn't actually matter if you write it as a 3-digit bearing, because we are just looking at angles initially, but then when we write the bearing, we do make sure we convert it to a 3-digit bearing if we need to, by adding that 0 at the start, unless of course it's already a 3-digit bearing. So there we go, there are bearings. Just remember, you measure from north, you go clockwise, and we always give 3-digit bearings as answers. Okay, so when we are looking at loci questions, we can be asked any of the construction questions that we've already looked at. So here it says point T is 250 metres from point A. It also says that point T is equidistant from points B and point C. On the map, show one of the possible positions for point T, and it says 1 centimetre represents 100 metres. Well, to start with, we'll deal with that first point. So if point T is 250 metres from point A, well, we need to find all of the points that are going to be 250 metres from A. The scale says that 1 centimetre is 100 metres. So 250 metres is going to be 2.5 centimetres. So I'm going to pull the end of my compass to the end of the ruler there, and we're going to measure this out to 2.5 centimetres, which is only going to make a small little jump there on the compass. So we have 2.5 centimetres, I can move the ruler out of the way, and we are going to draw a circle around A. I'm going to draw a circle for this because there's any point on that circle would be 250 metres away. So there we go, any of those points there are 250 metres away from point A. I now also have the problem here that I need to do the point that's equidistant from B and C. Equidistant just means an equal distance. So if I want something which is an equal distance from B and C, that's going to be one of my bisectors. Now, I'm not going to need to draw an angle bisector, because I don't have an angle involved here, but if we imagine that we did connect the lines B and C, the equidistant point is going to be somewhere in the middle, where we can draw a sort of line that goes through that, but we need to find exactly where the middle is. So we're going to draw a perpendicular bisector for this one. Now, a perpendicular bisector is nice for us to do. We can put our compass on the end, extend past halfway, and then we're going to draw a nice semicircular arc. Without changing the length of the compass, I'm going to go to the other side of the line, and I'm going to swing that arc all the way back round so that it joins those both together. We now know that if we connect this point over here, and let's put a dot on there instead, and this point over here, that's going to draw a line which is then equidistant from the line BC. So you want to use a ruler and a pencil to do this, but we don't just want to join those up, we're going to also want to extend the line so that it crosses through this circle. There we go. So those points on the circle are both equidistant from B and C, and they are 250 metres from point A. So you can see we have 2 points. We have this one here, and we also have this one here. Now it says on the map, show one of the possible points. Obviously we would only need to label one. I'm going to label this one, and we'll just say that's the point there. It's equidistant from B and C, and it is 250 metres from point A. Okay, so when expanding double brackets, there are a couple of methods that you can use. I tend to just connect them up using connecting lines. Now essentially what we actually do have here is 2 lots of a single bracket. You have to first do 5x multiplied by the 2x minus 3, and we also have the 2 in the first bracket, which is also getting multiplied by the 2x minus 3. Now you could write it out like this and then add them together. That's just technically what we're doing, but it's much easier to leave it as it is, and we'll just expand the first bracket by the 5x. So 5x multiplied by 2x would give us 10, and we get x squared, as we have an x being multiplied by another x. Then we have 5x multiplied by the 3, not forgetting to include or incorporate the symbol there. That is a negative 3, so we can put the negative in and then just do 5x times 3, which is 15x. We can then move on to the 2, doing our second bracket here. So 2 times 2x would give us plus 4x, and 2 times the 3 would give us 6, and again we have a negative there, a positive times a negative makes a negative, and there we go, we have expanded the double brackets. We now have this concept of simplifying as well, so where we simplify this double bracket or this now new quadratic, we need to look for the like terms. Now the 10x squared is the only piece there that has a squared with it, so that stays as it is. But these two middle pieces here are both an x piece. So they can be combined. The number at the end is on its own, so that's going to stay as a -6 as well, so you could always write that in if you want. But we need to simplify and combine these middle two. So -15 add 4 would give you -11x, and that would be your final answer, and that is your expanded and simplified double bracket. So our final answer, 10x squared minus 11x minus 6. And there we go, that's how we expand a double bracket. Now the reverse of expanding a double bracket is factorising a quadratic. Now we can take a very similar approach, but we're obviously going to do this in reverse. Now if we're going to factorise, we know it's going to go into a double bracket. Now this one here, we know that it's going to start with an x, as we have x's in our quadratic. There's no coefficient of x squared, so there's no number in front of it. So we know in both our brackets it's just going to be a single x in both, because x times x gives us x squared. We can then look at the factor pairs of this number here. So 3 only has one factor pair, that's 1 and 3. And if we had multiple factor pairs, we would obviously have to consider other factor pairs as well, but this is quite a nice one because we only have 1 and 3. And then the next step is to look at this number in the middle and think, how would we make +4? And that's by combining these numbers, because we know the middle two are going to get added together when we expanded the double bracket in the first place. So to make +4, we would want +1 and +3, as 1 + 3 is equal to 4. So we'd put those into our bracket, so +1 and +3. Now, of course, when you are factorising this, you could write that the other way around. We could have x + 3 and x + 1. That both mean the same thing. So you can have either option there. It doesn't matter what order you write them in. The important part is that the correct symbol is with the correct number. And here, both of the symbols are positive, so it's quite a nice one. Now, of course, you can have other variations. You can have something called a difference of two squares, which looks like something like this. So x squared minus 16 is a good example. So here you don't have anything in the middle. Now, it does factorise into a double bracket, but when there's no x piece in the middle, we just need to obviously bear that in mind when looking at our factor pairs. Factor pairs of 16, you could have 1 and 16, you could have 2 times 8, and you could have 4 times 4. But because there's nothing in the middle, this time we're looking how we can make 0. Now the only way that you can make 0 is if the two factor pairs are the same number, because essentially they cancel each other out. So you could have +4 and -4, and together they would equal 0, which is why there's no x piece in the middle. So that's a more unique scenario there. We could have x + 4 and x - 4, and of course they could be written in either order as long as the positive and negative is with the right number, but in the case of this one, both numbers are the same, so as long as there's a positive and negative with the same number, that would be a difference of two squares. Obviously lots of different variations of this. You can have positives and negatives in all the different positions, but the important part is to look at them very carefully when you're looking at your factor pair and just think, how do we make this number in the middle? And that should help you then get towards the symbols that you need in front of those two numbers. So here's a good example of a quadratic where there is also a positive and a negative. Now here we're actually asked to solve this quadratic. And when we are solving a quadratic, as long as it's equal to 0, we can actually go about solving it. But the first step is to factorise the quadratic. So for this particular step, we're going to kind of ignore the equals 0 for the moment, and we're just going to factorise the quadratic on the left. We need to look at the factor pairs of 24. So for 24, there's quite a few factor pairs. We can have 1 times 24, we can have 2 multiplied by 12, we could have 3 multiplied by 8, and we could have 4 multiplied by 6. Now we're looking for a factor pair that can combine in order to make negative, or positive for this one, positive 5, and negative 24 when they multiply. So a little bit of logic here can help, because we know that if we are multiplying to make negative 24, that one of the numbers has to be positive and one of the numbers has to be negative. Otherwise, when you times them together in that final multiplication here, you would get a positive otherwise, so we have to have a positive and a negative. So using that, how are we going to get plus 5? Well, there's no way of doing that with 1 and 24. There's no way of making 5 with 2 and 12, but we can make 5 with 3 and 8. You can make 5 by having minus 3 plus 8. I'm being very careful there not to do it the other way round, because if we had positive 3 take away 8, that would actually give us negative 5. So here we could have negative 3 and positive 8. Of course, these brackets can also be written the other way round, as long as we keep the plus with the 8 and the minus with the 3. Now, when we are solving one of these, it's really nice and easy at this point for us to solve. Now, this is equal to 0. Now, essentially, when we are solving this, we are actually finding, and you don't always have to go into this much depth, but you are finding the points where a quadratic crosses through the x-axis. So this is what we're looking for, and that's what equals 0 means. Where this x-axis is going through, that's where y is equal to 0. We know that this point just here is 0 on the origin, so it's where the x-axis crosses through 0. So we have two coordinates, and essentially we can take them in two steps. Now for the first one, we say, okay, well, when does x minus 3, when does that equal 0? And that gives us a nice little equation to solve. You can add 3 to both sides, and that's when x is equal to 3. And you might notice there a bit of a pattern that here it was negative 3, and here our solution is positive 3. And this one here should help emphasise that pattern, because here we get plus 8, and if we look at where x plus 8 is equal to 0, we have to take away 8, and we get x is equal to negative 8. So here, where the bracket had a plus 8, our solution was negative 8. So you can see there, both the numbers in the brackets, our solutions, are basically just the flipped sign. So it is quite quick to find them. You don't have to write out that equation there. As long as you know that that is what's happening, it's okay for you to just flip the signs and go, right, well, there's a negative 3 in the bracket, so our solution for that is positive 3, and there's a positive 8 in the other bracket, so our solution for that is negative 8. So there we go, that's how we would go about factorising a slightly harder quadratic and also solving it, but obviously pay attention to the words. You would not need to do that second step there if it just said to factorise. Now, when it comes to drawing a quadratic graph, we have a couple of methods that we can use. In this one, we're going to look at a non-calculator method, which is going to mean that we can solve this or answer this no matter what kind of paper it appears on. So here, it tells us to complete the table for this equation. And the equation there says y is equal to x squared minus x minus 6. So here we are also given a list of the x values. It tells us here we're going to be using x from negative 3 to 3. And we want to find these y values. And two of them have actually been given to us. We've been given the 6 and the negative 6. Now, when I'm solving these, I always like to start with the positive value. So I'm going to start over here so that I only have to substitute a positive number into my equation. So it says that y, which is what we're trying to work out, is equal to x squared, take away x, take away 6. So if x is 3, that would be 3 squared, take away 3, and then take away 6. So you need to take your time to work that out. You can always do it underneath. 3 squared is 9, so it's 9 take away 3, take away 6. 9 take away 3 is 6, take away 6 is 0. So this here is going to be 0. We can then move on to the next number. When we move on to the next number, this working out, we'll have to start again, but we're only going to replace those 3's. So here we are looking at 2, so we would have 2 squared, take away 2, take away 6. 2 squared is 4, 4 take away 2 is 2, take away 6 is negative 4. And again, we can just keep repeating this process to find our next numbers. We'll get rid of the 2's. We are now looking at the 1's. So we have 1 squared, take away 1, take away 6. 1 squared is 1, 1 take away 1 is 0, take away 6 is negative 6. And you'll notice in this kind of table here, you can have repeated values. So don't worry about seeing something like that. It'll make sense when we actually go about drawing it. Now we're moving on to the negative numbers. When you move on to the negatives, you need to be extra careful. If you are using a calculator here, then you need to make sure negative numbers are put into brackets. So here, I'm going to put the -1 now in a bracket. That's just going to ensure that my calculator, if I am using a calculator, doesn't square the 1 and then do a takeaway, because your calculator will follow the order of operations. If you put -1 squared like this in a calculator, it will give you the answer -1. And actually, -1 squared is not -1, it is +1, which we should know because a negative times a negative will make a positive answer. But you can test that out on your calculator and you can see you will get different values, so you need to be very careful with that part. So here, -1 squared is +1. Then we are taking away -1, which is going to add 1, and then take away 6. 1 plus 1 is 2, take away 6 is -4. And you might actually start to see a pattern. You can see here both of these were -6, both of these were -4, and that's going to follow the same pattern here with the 0, so we know that actually that's going to be 0 over here. Again, you can sub it all in though and make sure you're happy with that, but you might be able to start to see a pattern as you're going, which can save you a little bit of time, but just be very careful with spotting patterns. So now we can go about actually plotting this. It does say on the grid, draw this graph. So we'll plot each point. Be very careful when you plot them. Remember your x and y coordinates. You've got the x labelled on the graph over here and your y up here. And then you've got your x and your y to plot. So I'm going to start on the left. We'll start with -3 and 6, which is the coordinate -3, 6. So go along to -3 up to 6. And we get a point just here. Make sure you mark it nice and clearly. Then we have -2 and 0. So -2 and 0 is just here. -1 and -4 is going to be here. Then you have 0 and -6. We have 1 and -6. We have 2 and -4. And then we have the 3, which is with the 0. Now, when you are drawing one of these, a quadratic graph, or any graph that has a power in, we join these points up with a nice smooth curve. Meaning we're not going to get our ruler and join each one up dot to dot. We're going to try and make it a nice smooth curve. You can go from one dot to one dot. You don't have to do it all in one go. It's really important that you hit all of the points and go through as neatly as you can. So I'm going to do 1 point to each one. I'm going to try and make sure that when I do it, the line does have a little bit of a curve in it. And there we go. I'm going to try and join it up really nice and neatly. And there we go, that's a quadratic graph and how we go about drawing them on the graph and plotting the table and being careful with negative numbers. So there we go, that is drawing a quadratic graph. Now, when we are looking at area of a circle, it doesn't necessarily only have to appear on a calculator paper. So here is a really good non-calculator version of where we are working out the area of a circle. Now we have here a garden that's in the shape of a circle with a radius of 10 metres. Now as soon as it says the word circle and we think we might be looking at area, we want to write down our area formula. So area is equal to pi multiplied by the radius squared, or pi r squared. It says here we're going to cover the garden with grass seed to make a lawn. And grass seed is sold in boxes. Each box of grass seed will cover 46 metres squared. Bellina wants to cover all of the garden with grass seed, work out an estimate being a really key word here, for the number of boxes of grass seed Bellina needs, and you must show your working. Now as soon as we see the word estimate, we want to round any numbers that we can see to one significant figure. So one significant figure for the 46 metres would be 50 metres squared, and one significant figure for the 10, well that's already written to one significant figure. So now we have got numbers that we can actually estimate with. The only other number in this question, which isn't written as a number but is written as the symbol pi, that is also a number that we're going to want to round to one significant figure. Now pi to 2 decimal places is equal to 3.14. So if we were to write that to one significant figure, an estimated version, we would use pi is equal to 3. And that's going to mean that we can actually work out area of circles, or estimated area of circles, using pi as 3. So if we work out the area of this circle, which we know is pi r squared, well, we can do 3 multiplied by the radius squared, and the radius is 10, so 10 squared. That means we're going to do 3 times, and 10 times 10 is 100, so 3 times 100 would give us an area of 300, this is in metres, so metres squared. So that would be the area of the garden. We know from the question that each box of seed covers 46 metres squared, which we've rounded to 50. So if we want to figure out how many of those boxes are needed to fit into 300, we can do 300 divided by 50. Now, when you are dividing large numbers like this, when you are estimating, if we imagine it's written as a fraction as well, 2 ways that you could write it, but we can cancel off a 0 from the top and the bottom just to make that division a little easier. So 30 divided by 5 would give us an answer of 6, so we would need 6 boxes of grass seed. So that would be our final answer for how many boxes we need, and we have shown all our working along the way. Now it says in part B, is your estimate for part A an underestimate or an overestimate? And you must give a reason for your answer. Now the rounding that we did in terms of pi hasn't overly affected the answer for the area. If we did 1 or 3.14 times 100, we would have got 314 metres squared. But the rounding that we have done in terms of the division there is quite a large one. So we could actually go about figuring this out. You could sort of think to yourself here, well, if we did 314 metres squared and we divided it by the original 46, what would be our answer? Now, typically, the reason we've estimated it is probably because that was relatively complicated to work out. So here, I mean, you can think about this in terms of would it be more or less if we'd have done the real one, and you can already see that even if we'd have done the 314 metres squared, we would have had to have got an additional box. We'd have had to have got 7 boxes. And that's without even thinking about this 46 here, which could push it up to another amount of boxes. But the important part is we can see very clearly that our estimate is under what we'd actually need. So really, we'd have needed more than 6 boxes, and therefore ours is an underestimate. And we could just say that we rounded down the number that we divided by. So because we divided by 46, because we divided by 50 and we should have divided by 46, actually our answer would have been bigger than 6, and that's the reason that we would give to do with that division. So there we go, it's an underestimate. We would give a reason along with that. You could phrase it however you wanted, so I'm not going to put specific words there, but you could phrase that as because when we actually divided, we divided by a larger number, and therefore we got a smaller answer. If we had divided by 46, we would have got a number bigger than 6, and therefore ours is an underestimate. Now we can also have compound shapes where we are looking at area of a circle. So here it says a garden is in the shape of a rectangle and a semicircle, and AD is the diameter of the semicircle. It says here Carol is going to cover the garden with fertiliser, and a box of fertiliser costs £4.99. Carol has been told that 1 box of fertiliser will cover 12 metres squared of the garden. Work out the cost of buying enough fertiliser to cover the garden completely. Well, to do this, we need to get the area of both of these shapes, and we are going to be using a calculator for this question. So to start with, we can get the area of the rectangle because that's just going to be the length times the width, or 8.4 multiplied by 5.6. If we work that out on the calculator, we get 8.4 times 5.6, which comes out as 47.04. This is in metres, so metres squared. For the semicircle, we're going to want to first know what the radius is, as we know that the formula for the area of a circle is equal to pi r squared. So here, for this area, we will do pi multiplied by, and then we need to find the radius. Now the full length across is 8.4, given to us on the bottom of that rectangle. So if we divide that by 2, we get 4.2 metres as the radius, and we can put that into our formula, pi times 4.2 squared. If we type that in on the calculator, times 4.2 to the power of 2, we get an answer of 55.412 7. Now there are some more decimals there, but because we are going to figure out how many of these 12 metre squared boxes fit into our answer, I'm not going to worry too much about going into 4 decimal places. The important part here is that we add both of these together, so 55.417. There is a 6 after that. Technically it does round up to an 8, but again it's not going to affect our answer in this case, so I'm just going to add that to the 47.04, so plus 47.04, and we get a total here of 102 point, and it goes 4, 5 and some more decimals, but again I'm not going to worry too much about writing down all those decimals because I want to know how many boxes actually fit into that. So here, when I divide by 12, which is our amount of metre squared that each box covers, well, I'll divide by 12 and I get 8.538, again more, but I get over 8 boxes. Now we can't go in and ask for 8.538 boxes, we have to round this up. We'll go in, we'll buy 9 boxes of grass seed, we'll have enough to cover the garden, we'll have a little bit left over, but we will have enough. So obviously it does say to cover the garden completely, not to just undercover it. So here we're going to have to buy 9 boxes. Now it's asked here to work out the cost. Each box of fertiliser costs £4.99, so I need to do 9 multiplied by the £4.99 it's going to cost me for each box. So 9 times £4.99 is equal to £44.91. And there we go, that would be our final answer. Now it says here that Carol finds out that 1 box of fertiliser will actually cover more than 12 metres squared of garden. Explain how this might affect the number of boxes she needs to buy. Well, if she finds out it only covers 12.1 metres squared, because it doesn't tell us how much more, there's a chance it might not actually change it at all. But it does say explain how it might affect the answer. Well here, if we find out that it covers more than 12 metres squared, for example, let's imagine it covers 15 metres squared. Well, if I do the 102 divided by 15, I actually get 6.8, and in that case I'd only need to buy 7 boxes. So in terms of writing down an answer here, and again I'm not going to write down some words for this, we'll just talk about it because you can phrase this in different ways. But something along the lines of, if the grass seed covered more than the 12 metres squared, Carol may need to buy less boxes. We're not going to state any numbers because we don't know the exact amounts, but the important part there is it might mean that she needs to buy less boxes, and actually that would mean that she'd have to pay less. Now we obviously don't need to say that, it doesn't ask us about the actual cost, but thinking about real life here, it would just mean she would need to buy less and she might not have to spend as much on the grass seed. So there we go, there is a functional question looking at area of a circle. Now when it comes to looking at cones, you are given the formulas for these in your exam. So here we are told the volume of a cone for this one is 1/3 pi r squared h. We're given a little diagram that shows the radius down the bottom of the cone, and it shows us the height, and the height being the perpendicular height from the base to the top of the cone. Now this one here, it says the radius of the base of the cone is 5.7 and its slant height is 12.6. Now the slant height is along the edge of the cone. That's not the perpendicular height that we need for our formula. So here where it says calculate the volume of the cone and give your answer to 3 significant figures, we have a little bit more to work out than just plugging these numbers into the formula. So here you can see, and it has highlighted it for you quite nicely on this diagram, that it makes this particular shape, which you can hopefully see is a right-angled triangle. So here is another topic that is going to involve Pythagoras' theorem. If we have a missing length on a right-angled triangle, straight away we can use Pythagoras, and cones is a really nice topic that they like to include Pythagoras with. So if we were to draw that triangle to the side, you can see that we are given the length of the hypotenuse, 12.6, and we are given this base length here, or one of the shorter sides, 5.7. Pythagoras' theorem is a squared plus b squared equals c squared, and if we are working out one of the shorter lengths, we have to do a subtraction, essentially doing something along the lines of c squared minus a squared is equal to b squared. You can mix around the A and the B there. The important part is the shorter side that we have, we are going to call A, as our formula there has the A in it, and our longest side is always the C. So to work out the short side, we will do 12.6 squared, take away the 5.7 squared, and that's going to give us our value of B squared. So 12.6 squared, take away 5.7 squared, gives us an answer of 126.27. To find just the length, we have to square root our answer, and if we square root that on the calculator, we get quite a long number, but it's 11.23699,248. Now, because the question here wants that answer to 3 significant figures, we could probably get away with writing our working out down to 5 significant figures. But if I want to be super careful and make sure I don't miss any numbers or get a slight error in my rounding, particularly when it's only that many decimal places and it's not going on forever on the calculator, I'd be absolutely happy just writing all of those down just to make sure I don't make a mistake. So we know here the height is 11.236, and the rest of those decimals, I won't write them down there, but I will use them in my working. So for the volume of a cone, it does tell us the formula up here, 1/3 pi r squared h. So we want to type that into our calculator. So 1/3 multiplied by pi, multiplied by the radius squared, which is 5.7, and then multiplied by the height, which is 11.23699,248. Now, most calculators have the answer button that you can use on the calculator. So my last answer was the 11.236 number. So I'm just going to type in 1/3 multiplied by pi, multiplied by 5.7 squared, multiplied by, and then I'm going to click the answer button, which at least saves me a little bit of time typing in that big long number. So when we type that in, we get an answer which comes out as 382.321, some more decimals, but again, it does say give your answer to 3 significant figures. I've already written up to 6 significant figures there. So I'm going to chop this after the 3rd significant figure, and you can see there, that's not going to round up. So our final answer will be 382. This is a volume, and our question is in centimetres, so that would be centimetres cubed. And there we go, that is our final answer there for the volume of a cone, and really it's just using a formula, but this question was a little bit more complex because we did have some Pythagoras theorem involved to find the height of the cone. Now when it comes to spheres, again there are 2 formulas that you can have. You can have the volume and the surface area, and you are given those formulas. You can see they're given there on the right hand side. So it says here the diagram shows a solid hemisphere, and that has a radius of 8. Work out the total surface area of the hemisphere. Now here, working out the volume would have been a little bit easier because we can plug that straight into the formula, just divide the answer by 2. But when it comes to the surface area, we have 2 surfaces that we're going to have to work out. We have the circular surface, which is up here on the top, and we have the curved surface area that's going round the outside of the sphere round here. So we're going to start by working out the circle. So for the circle there has a radius of 8. The formula for the area of a circle is one that you are expected to remember. So area is equal to pi r squared. So we can work out that area by just doing pi multiplied by 8 squared. Now it's completely up to you. You can leave this in terms of pi as you are going through. So that does come out as 64 pi. Which can make it a little bit nicer when you have to add it to another number, or you can write out the decimal. The decimal version comes out as 201.0619298. Either way, I now have to work out the curved surface area as well. So we are looking at the formula here where it says the surface area of a sphere. So here the formula is 4 pi r squared. Now this here is a hemisphere, so once we've got our answer for that, we are going to want to halve the answer. So I'm going to work out the full curved surface area to start with, so I would do 4 times pi times the radius squared, which is 8 squared. I can work that all out, or I could straight away divide it by 2. If you do divide it by 2, you could actually simplify this a little further. You could just work out 2 pi r squared, or 2 times pi times 8 squared. Purely because this 4 here can divide by the 2, so it can simplify down and just write 2 pi times 8 squared. Completely up to you. You can either work it all out and divide your answer by 2, or you can simplify it a little bit and we'll do it in one go. So I'll work this out, 2 times pi times 8 squared, and that comes out as either 128 pi, if you want to write it in terms of pi, or you can write out the full answer again, which is 402.1238597. Now to finish this off, we are working out the total surface area. So to work out the total surface area, we just need to add both of those together. We do need to give it to 3 significant figures, so if we did leave it in terms of pi to start with, we're going to have to write the decimal this time, but I can do 128 pi, and I'm going to write this working out down here. So 128 pi, we're going to add to that the 64 pi. There you go, so plus 64 pi, and that equals 192 pi, which I'm going to write as a decimal. That decimal comes out as 603.185. I'm not going to carry on because, again, in this question, it says to write it to 3 significant figures. So chopping it after the 3 gives us a final answer of 603. And this is a surface area. It was in centimetres, so that would be centimetres squared. So there we go, that is our final answer for the surface area of the hemisphere. Now when we are looking at a volume of a cylinder, unfortunately we're not given any formulas for this, but the volume of any prism is very nice to work out. You work out the area of the cross section, which in this case is a circle, and you times it by the height or the distance that it goes through the shape. And in this case the distance that it goes through is 15 centimetres. So the numbers are given to us in the question, they are also on the diagram, but it says to calculate the volume of the cylinder and give your answer to 3 significant figures. So here, first things first, we're going to write down the formula for the area of a circle, which is pi r squared, and then work out the area of this circle here on the top. The radius is given to us. Remember, you could be given the diameter, in which case you'd need to divide that by 2, but this question has given us the radius. So we would do pi multiplied by 4 squared. You can write that in terms of pi if you want. That comes out as 16 pi, or you can write it as a decimal. I do tend to like to leave it in terms of pi until I get to the final step, just to reduce the amount of writing that I do. So that's the area of the cross section. Now we need to multiply it by the length that it goes through the shape, in this case the height of the cylinder. So that would be 16 pi, the area of the circle, multiplied by 15, which is the height, and 16 times 15 is 240, so that's 240 pi. Now of course the question might say to give your answer in terms of pi, in which case we could leave it as it is, but this one does say to give it to 3 significant figures, and that comes out as 753.982 and a few more decimals, but it only wants it to 3 significant figures, so I'm going to chop it after the 3rd significant figure there, and that is 754, as we have a 9 after the line. So we have 754, this was a volume, it's in centimetres, so centimetres cubed. And there we go, that's how we would work out the volume of a cylinder. Now working out the surface area of a cylinder is a little bit more complicated than working out the volume. So when it comes to the surface area of a cylinder, yes, we are going to need area is equal to pi r squared, because with the surface area we do have 2 circles that we need to work out the area of, but then we also have this curved surface area that's going around the outside. So we'll look at that bit afterwards, but we'll start with these 2 circles. Now this question has given us the diameter of the circle, so we want to divide that by 2. The radius is going to be 6 centimetres. So we can start by working this out. We've got pi multiplied by 6 squared, which is 36 pi. Now we do have 2 circles, so we would want to multiply this by 2. That's going to give us the surface area of both those 2 circles, which comes out as 72 pi. Now again, it's up to you if you want to label that as as a decimal, but you can leave it in terms of pi. Again, I've just sort of written there, that's the 2 circles. You could write that in words, but we've got the 2 circles done, and the area for that is 72 pi. For the outside or the curved surface area, if we unravelled that from the circles, it would make a rectangle. Now it's quite nice, we know the height of that rectangle, which is 18, this is in centimetres, so 18 centimetres, you can see that on the right here. But the top of that rectangle there, and this is the complicated part of this, if I highlight that on the shape, you can see the top of that rectangle wraps all the way around here, and that is the circumference of that circle. So you do need to know circumference of a circle anyway. The formula for circumference is equal to pi multiplied by the diameter, or you might write it as pi times 2r, as 2 radiuses is the same as the diameter, but pi times diameter is quite a quick one, a nice one to remember. We know the diameter of the circle is 12, it's down the bottom of the cylinder, so for the top there, the working out we would need to do is pi times 12. We could do that on the calculator. We can write it as 12 pi if you like. That might save you a little bit of time. It does come out as 37.69 and a few more decimals, but I quite like to just leave that as 12 pi. We now have a rectangle that we need to work out the area of. The height of that rectangle is 18. The length of the rectangle is 12 pi. So we can work that out by doing length times width, or 18 multiplied by 12 pi. And 18 multiplied by 12 pi comes out as 216 pi. Again, you can write out the decimal if you like, but it does save a lot of time just writing these down in terms of pi. The total surface area then, we've got the curved surface area, 216 pi. We're going to add to that the two circles, which was 72 pi. And if we add those two together on the calculator, we get a total of 288 pi. The question does say to give your answer to 3 significant figures though, so we are going to have to write this as a decimal now. We've saved a bit of time along the way, but that comes out as 904.778, a few more decimals, but it does say 3 significant figures. So if we round this to 3 significant figures, we will chop it after the 4 there, after that decimal place. It's a 7 after the line, so that would round up to 905. Again, this is an area, so centimetres squared. And there we go, that is the surface area of a cylinder. Now, when we are looking at fractions, obviously there's a couple of different fraction calculations that we can have. We can have to add, subtract, multiply, and divide. So these are 2 relatively nice ones. When we are adding fractions together, we need to have a common denominator. At the moment, the denominators are 7 and 5. Now do have a look to see if one of them can turn into the other. In this question here, it's not easy to turn a 5 into a 7 and vice versa. So we will have a look for the lowest common multiple of 7 and 5. Hopefully you can spot that that's 35. If you're not too sure, you can always times them both together for a multiple. Won't always give you the lowest common multiple, but in this case 7 and 5, the lowest common multiple is 35. Now to get 35 on this left fraction, you would have to times 7 by 5. And whatever you do to the bottom, you just do to the top. So 2 times 5 would give you 10. For the right fraction, we have to multiply the 5 by the 7. And again, you do the same to the top. So that would give us 7. We can now add these 2 fractions together, and that would give us 17 over 35, just combining those numerators. The only thing that would change in this question is if it was a subtraction instead of an add. So if this symbol here was instead a subtract, if it was, then we would do 10 minus 7 on the top, and we would get 3 over 35. Of course, this question is an add, so we were absolutely fine to add them together. Now, it doesn't say anywhere in the question to give your answer in its simplest form, so you don't even have to think about simplifying it. If it did, then you would obviously have to look to simplify. As it turns out, this fraction doesn't simplify anyway, but there we go. Even if it did simplify and it didn't say to give it its simplest form, we don't actually need to worry about it. So for part B here, we have a division. The problem is one of these is a mixed number. Now, when we are doing any sort of fraction calculations, we do need to convert these to improper fractions first. So to turn 1 2/3 into an improper fraction, we do the big number at the start, multiplied by the bottom, and then add the top. So 1 times 3 is 3, plus 2, and that's going to give us 5 as our new numerator over 3. So here we're going to have 5 over 3 divided by 3 over 4. Now when you are dividing fractions, all you have to do is multiply by the reciprocal. So here we've got 5 over 3, and we multiply by, and the reciprocal is where you just flip the numbers over, or flip the fraction over. So we multiply by 4 over 3. Multiplying fractions is one of the nicest topics. All you do is times the top, 5 times 4 is 20, and times the bottom, 3 times 3 is 9. So for this one here, we get 20 over 9. It seems a little strange to leave an answer like that, but it doesn't say in this question to give your answer as a mixed number, it doesn't say to give it in its simplest form, so it is fine to leave it as 20 over 9. It would also be fine to convert this, which you could do, you wouldn't be wrong to do so, but just for this particular question, you wouldn't actually gain any extra marks for it. 9 fits into 20 twice, up to 18, that leaves you with a remainder of 2, so you would have 2/9 left over, so you could write your answer as 2 and 2/9 as well. Obviously, if you were given a multiplication question, it would be the same as this step here, but of course you wouldn't need to do the reciprocal, you'd just times the top times the bottom and give your answer however you've been asked. But there we go, that is some fraction questions. Now you can have some slightly more complicated fraction questions as well. Here we have, in the first question, 2 mixed numbers that we're going to have to convert, and we are adding there, so we're going to get some quite large numbers. And in part B, it does ask us to give our answer as a mixed number in its simplest form, so we just have a little bit more to think about on these type of fraction questions. Now we're going to start by taking each of these fractions and writing them as an improper version. So 2 times 7 is 14, plus the 1 is 15 over 7. For the second fraction here, we have 1 times 4, which is 4, add the 1, which is 5 over 4. And we're going to add these fractions together. Now straight away you've got 7 and 4, we need to make a common denominator. The common denominator, or the lowest common multiple of 7 and 4 is 7 times 4, so 28, which means we're going to have to multiply this left fraction by 4 and this right fraction by 7. So straight away you can see we're going to get some quite large numbers. So 4 times 7 is 28, so both of these fractions will be over 28. The left we're multiplying by 4, 15 times 4 is 60. The right we're multiplying by 7, 5 times 7 is 35. And now you can just add those two together. So 60 add 35 is 95, and on the bottom is 28. So there we go, we get 95 over 28 for the first one. Thankfully there, that question doesn't ask us to simplify it or write it as a mixed number, but you could write that as a mixed number as well. You could say, well, 28 goes into 95, it goes in 3 times, and there's a remainder of 11. Obviously you could take your time to work that out, but as we don't need to for this question, we won't go through all the steps for that one. That would be quite a horrible one though. You'd have to write 28 and some multiples of 28 down to the side, particularly as this is more likely to be a non-calculator question. For part B, we have a division again, but we have this additional step of writing our answer as a mixed number in its simplest form. So we'll take the same first steps, 1 times 5 plus the 1 is 6 over 5. You could write this out up here first before we do the reciprocal, so divided by 3/4, but of course we are going to times by the reciprocal, 4 over 3, and work that out. So 6 times 4 is 24, 5 times 3 is 15. Now you've got 2 steps that you could take, and it doesn't matter which order you do it in. You can either convert it into a mixed number, or you can write it in its simplest form. So it doesn't really matter either way. I'm going to start by converting it into a mixed number. So 15 fits into 24 once, and the remainder from 15 to 24 is 9. So you get 9 over 15. Now this step here, it can sometimes look like the answer is finished, but 9 over 15 does simplify. So it's going to be 1 and something, but you just need to spot what 9 and 15 both divide by. Well, they both divide by 3, so we can simplify the fraction. 9 divided by 3 gives us 3, and 15 divided by 3 gives us 5. So our final answer there is 1 3/5. So you can see that one there had a few more steps. Of course, you could have simplified at this point. They both divide by 3. That would have given you 8 over 5. And then you could have converted it into a mixed number. 5 goes into 8 once with a remainder of 3. So 1 3/5. So you can do either step. You can do it in either order. It's completely up to you which one you prefer. But there we go. That's how we would tackle some of these fraction calculations. When looking at standard form conversions, it's obviously important to know some of the rules. So the number at the start, when we are looking at standard form, it has to be between 1 and 10. Which means if we are converting a number into standard form, we need to essentially move the decimal to a position where it's between 1 and 10. And looking at the number that we have in this question, you can see that we're going to want the decimal to move between the 5 and the 6. That's going to mean that the number would read as 5.62. But of course, when we're writing something in standard form, we're just writing it in a different way. So here, we need to know how many times we are multiplying it by 10. Now, in the case of a large number, something like 562, and let's imagine it's 0, 0, well, in that particular circumstance there, we would actually be timesing it by 10 to get to that number 1, 2, 3, 4 times. But this is actually a 0 point number. So although we count the jumps, 1, 2, 3, it's actually going to be a power of -3 that goes with our number. So 10 to the power of -3 is just a decimal 0.001 or 0.0001. Okay, lots of different variations depending on the power there, but all that means is that we are timesing by a 0.01 number or type of number that sounds like that instead of actually the whole number 10 multiples of times. So there we go. If you have something like this would be written with a positive power, 5.62, and that particular one there would be 10 to the power of 4. But here, where we have a 0 point number, we just need to remember to put the negative with the power. So here, when we are converting back, again, you could have a positive or a negative power here when we are writing it as an ordinary number. But whenever we do this, I like to write the numbers out that we have. And I know I'm going to move this decimal, so I kind of put it at the top here. And for a positive power, we are multiplying it by 10 3 times. So it would go 1, 2, 3. The decimal is going to move here to the end. As it's at the end of the number, we don't even need to write it. So the answer there would be 1,452. Of course, you could also have a negative power involved. So let's imagine it was a power of -3. Well, in that circumstance, 1,452, the decimal would just go 1, 2, 3 in the other direction. So the decimal is going to jump to there. When you have that type of question though, you do need to make sure you tidy this up and put all your zeros in plus a 0 at the start. So if it was 1.452 times 10 to the power of -3, that's the answer that you would have got instead. So there we go, it's just being aware that a large number is going to have a positive power and these 0 point numbers have negative powers. And there we go, that is some standard form conversions. Now you can also have calculations with standard form. Typically, these sorts of questions here, where it is a little bit more complicated, this would be allowed with a calculator. So this is more like a calculator question. You can have them without a calculator, and we'll talk about the process you would do if you didn't have a calculator, but when you are multiplying or dividing with these sorts of numbers, the 13.8 and the 5.4 are the starting numbers in terms of the actual ordinary numbers that these would be. So all you have to do when you're multiplying them is multiply the starting numbers. So 13.8 times 5.4. Being careful not to confuse this obviously with our method like we do with double brackets where we connect them up. Here we are just multiplying those starting numbers. So 13.8 times 5.4. A good logical way to think about this is if we do something like 30 multiplied by, let's just make something up, 600, you only have to multiply the starting numbers, 3 and 6 is 18, and then you just count the zeros and add them all together. So 1, 2, 3 zeros on the end, but all we had to do was multiply those starting numbers. Here it's just a little bit more complicated because it is written in standard form. But if you multiply those starting numbers, you get 74.52. As well as that, if we look at these powers of 10, if you remember about index laws, when you are multiplying with the same base number, you can add the powers together. So here we would have times 10, but the powers we're going to add. This is quite a complicated one because we have a negative power. So that'd be 7 plus negative 12. When you add a negative, that's a take away, so that'd be 7 minus 12, and 7 take away 12. Of course you have a calculator for this, so you don't have to think too much, but that is negative 5. So times 10 to the negative 5. So if you didn't have a calculator, that is a process that you could take. Obviously you wouldn't have numbers as complicated as that. It might have been 2 and 3 in the brackets, and maybe you didn't have to write it as an ordinary number, or at this point you could convert it. So here, if we type this into a calculator, I'm just going to type in the 74.52 times 10 to the minus 5 and see what we get. So for that, my calculator actually shows it me in standard form, so it doesn't really help. It does give me the answer, which is good for this because we can balance it out to standard form. So here, if we want the decimal just there, we make the number smaller, 7.452, and that means you make the power bigger. 1 bigger than -5 is -4. So you can balance it out as well if it did say to write your answer in standard form, but this does say give your answer as an ordinary number. Unfortunately, my calculator shows it in standard form, so we are going to have to convert it. So I'm going to write the numbers, 7452, it's a negative power, which means it's a 0 point number, which means I'm going to have to hop the decimal 4 places to the left, being really careful with this. So it's going to go just here, underneath each loop, I need to tidy that up with zeros. So there we go, my final answer for that is 0.0007452. And there is a more complicated standard form calculation. When it comes to congruent triangles, congruent is just a word for exactly the same, or mathematically exactly the same. So it says here, write down the letters of the two triangles that are congruent. Now if we look, the majority of these triangles have given us some angles. Some have given us 2. So some of them we can actually get some more information for. For the first triangle, triangle A, you can see that those two angles, 55 and 45, add up to 100. So our missing angle just here would be 80, as angles in a triangle have to add up to 180. For triangle B, we can't fill anything in, same for triangle C, but we can for triangle D. You can see that kind of matches triangle A, we've got an 80 and a 45, so this missing angle here has to be 55. Now with a congruent triangle, the same length has to be opposite the same angle. So what I mean by that is if we look opposite this 80, we have 10. Over here, 10 is opposite the 45. Over here, 10 is opposite the 55. So far, all of those have to be different because the 10 centimeters is opposite different angles. So this is going to be our deciding triangle, and over here, 10 is opposite the 80. So if 10 is opposite the 80 in this one, it's also opposite the 80 in this one. So our congruent triangles would have to be A and D. So there you go, you can see in terms of looking at congruent triangles, you can only really look at the angles and the sides. Obviously the angles have to be all the same in that triangle. So if there was a couple of different triangles where 10 was opposite 80, we might also have to look at the angles as well and make sure the other two angles were the same. So for example, if this one wasn't the only one, and maybe this angle was 35 and this angle here was 65, then they wouldn't be congruent triangles because the angles would be different, even though the 10 centimeters is opposite the 80. But this was quite a nice one. You had the 80 degrees opposite the 10 for both of those with all the same angles. So they are the congruent triangles. Now, similar shapes can be tricky and it can be relatively nice. This particular one here, the triangles that we've been given are overlapping one another. But when it says that shapes are similar, which this question doesn't, and we'll discuss how we know it's similar, but if you are told that shapes are similar, it just means that one is an enlargement of the other. And when it comes to enlargements, you are looking at the scale factor between the two. So here, we know that these shapes are similar because they share this angle here, and this line on both of the triangles is parallel, meaning it's going in the same direction. So they both share the same direction here. They both share the same direction here as their straight lines, and then those parallel lines are also the same direction as well. So these shapes have to be similar, it's just that the larger triangle there is an enlargement of the other. Now when you are given these overlapping shapes, you can actually redraw them. So I could redraw these triangles or try and draw them slightly to scale as well, so you can see which one's bigger than the other. Now on the big triangle, this is A, this is E, and this is C. And on the small triangle, this is B, this is C, and this is D. So it's given us some lengths here that we can actually label onto the diagram. It tells us E to C is 8.1, it tells us D to C is 5.4, and it tells us D to B is 2.6. and it says work out the length of A to E, which is this length just here. So in order to find the scale factor between the two, you need to match up the similar sides. So here on both triangles, we've been given the base of both. To find the scale factor, or in other words, what we've multiplied by to get from 5.4 to 8.1, you just do the bigger number, 8.1, divided by the smaller number, 5.4. We'll do that on the calculator. So 8.1 divided by 5.4 gives us 1.5. And that there is our scale factor. So that number can now be used to move between the triangles. So here, where we are going from the smaller triangle up to the larger triangle's length, we just need to multiply by 1.5. So 2.6 on the calculator times 1.5 gives us 3.9. So that one there is 3.9, and our first answer here would be 3.9 centimetres. This also has a part B, where it tells us that A to C is 6.15. A to C is this length just here on this larger triangle. It wants to know the length of A to B. Now A to B is quite an interesting length to ask, because here that is the gap between these two triangles. Or in other words, the difference between the larger length and the smaller length. Well, we can find the smaller length here on our diagrams that we've drawn. Because we know the scale factor is 1.5, we can just divide by 1.5 to go down to the smaller length. And if I do 6.15 divided by 1.5, I get 4.1. So the gap that's in between them must be the difference between 6.1, 6.15 and 4.1. So I can work this out. We can do 6.15, the length of the larger triangle, subtract 4.1, the length of the smaller triangle, and that gives us 2.05 centimetres, and that would be the gap there, which they've called AB. So there we go. But that's how we approach similar shapes. You just need to find the scale factor between the shapes by doing the larger divided by the smaller, and then you can use that scale factor to multiply or divide between the shapes. Okay, so for this question we're looking at some column vectors. It says shape A is translated by the vector 4, -7, and shape B is then translated by the vector -3 and -2, and that makes shape C. Describe the single transformation that maps shape A onto shape C. Now, if we had a grid, this would be quite nice to draw, because the vector just tells us a movement. And if we imagine a starting point, the first vector means 4 to the right, and then down by 7. Now this would obviously be nice and easy to do if we had a proper grid, but the next vector tells us to go left by 3, that's what the -3 means, and then down by 2. Now if we had a grid, it'd be really easy for us to count what this final vector actually did. How far have we gone left and right? But because we don't have a scaled grid, it's much easier just to add these together. And thankfully vectors are really nice to add together. So we can just add them up and see what we get. You just need to be very careful because we do have negative numbers involved. But when you are adding together vectors, you literally just add the top number with the other top number. So we have 4 add -3. If we add a negative, that is a subtract. So it's 4 take away 3, and that gives us 1 on the top. We do the same for the bottom. We have -7 add -2. Again, we're adding a negative, which is a subtraction. So -7 take away 2 would give us -9. And you can kind of think about this in terms of the diagram. I'm going to write my answer here, 1 and -9. But if you even look at the diagram, you can see if we have gone 4 to the right and then 3 to the left, technically we've only actually gone 1 to the right overall, which is why we have 1 on the top. If we also look at this downwards line, it's going down by 7, and then we go down by another 2, and overall we've gone down by 9. So you can kind of relay the vector back to a diagram and think about what it looks like, but it's much easier just to apply this method up here where we are adding the vectors together. Now you may have some more complicated column vectors where we have questions like this. We are told the vector A is 1 and 4, vector B is 3 and 2, and it says write down as a column vector, and for the first part here, we just have A plus B. So A is 1 and 4, we just want to write that down. We have a plus symbol in between, and B is 3 and 2. That's a nice one to add together. 1 plus 3 is 4, 4 plus 2 is 6, and there is our final column vector. But just looking at how that's been written and how it's given us A up here and B here. For the second part of this question though, we have 2 A's and 3 B's. Now when you have 2A, it just means that this vector A that we are given at the top, essentially we just want 2 of those. So you could write 2A as 2 lots of 1 and 4. I prefer just to times them straight by 2. So that would mean 2A would be 2 and 8, just doubling both those numbers. You can also write the 3B as 3 lots of 3 and 2, but again I just prefer to times them both by 3 and write 9 and 6. This is asking us to add those vectors together, so a nice one again, 2 plus 9 is 11, and 8 plus 6 is 14. Again, you just need to be very careful when it tells you to subtract, and also being careful if you have negatives involved, but this particular column vector question was quite a nice one, as all of the numbers in those vectors were all positive, and we were only adding these vectors together, so we didn't have to worry too much about actually worrying about negative numbers, and that's where these questions can get a little bit trickier when you have negatives involved. Okay, so here we have plotting a cubic graph. Now cubic graphs, there are lots of different types of equations that we can have for this. This one here we have y is equal to x cubed plus x squared minus 2x plus 1. Now if you can plot this cubic graph, you can pretty much plot any of these graphs, but we have to fill in the table. Now, similar to when we are plotting a quadratic graph, we're going to substitute these x values into the equation to find the corresponding y value. So for this first one, we're going to have to start with 2 cubed. Now, because we also have some negative numbers that we're going to need to sub in, I'm going to make sure that I put every number in a bracket. So to start with, I'm going to do 2 cubed, then we have x squared, so 2 squared. Take away 2x, which means 2 times x, so 2 times in brackets 2, and then plus 1. Now, if we type that all into a calculator, this will typically be a calculator question. We could work this out without a calculator as well. So just to think about if we didn't have a calculator, 2 cubed is 8, 2 squared is 4, 2 times 2 is 4, we're taking that away, so take away 4, and then plus 1. 8 plus 4 is 12, take away 4 is 8, add 1 is 9. But you will see if you type that into your calculator, you do get 9 anyway. For each number, we now just need to change the 2 into whichever x number we're substituting in. So here we're substituting in 0, so if we get rid of these numbers and just change those to zeros, you will see for that we get 1. We can then do the same for the negative 3. The fact that we've got it in brackets is going to mean that those negatives are not going to cause any issues. So when we sub this in, these zeros now are going to change into negative 3s. And we just need to take some time to actually type that in. Make sure we type it in really carefully. If you've already got it on your calculator screen, you can do what I've just done on the paper there, which is to just delete the 2's, change them into a negative 3, and press equals, and you'll see that we get negative 11. We can now actually plot these on the graph, remembering these are just x and y coordinates. So negative 3, negative 11, we'll go across to negative 3, down to negative 11. We're going to have to be really careful here because the graph does have a little bit of a strange scale. You can see that down here in between, that would be negative 10, and negative 11 would be in the middle of that. So we need to trace along really carefully. Ideally, I would use a ruler just to line it up, just to make sure I don't miss any of these. Negative 2 goes to negative 1, which is just here. Again, just labelling on any extra numbers that you need to. That's negative 2 just there. So it's between 0 and negative 2. Negative 1 goes up to 3. Again, being really careful, that would be 2. So 3 is in the middle. So 3 is just here. 0 goes to 1, which is between 0 and 2. 1 goes up to 1 as well, so that would be just here. And 2 goes up to 9. This is 10 in between, just here. So it's in between those two. So this would be 9. Now with this cubic graphs, when they are positive, have this sort of shape here. If they are negative, they do slope down the other way, so they can slope down this way as well. This is a positive x cubed, so when we join this up, we are going to join it up with a nice smooth curve. Now, it's okay to join up until you get about to this point here, but now when you come down through this x, what you don't want to do is now draw a straight line across. You can see that it has this almost flick in the curve, so when we're coming down, we can go below that and then back up again, and then back up to our final point. Now, we don't need to stress too much about whether it goes through the x-axis or not, we're just plotting it as best as we can. So you could have, as you did this little part here, you might have come all the way back down and back up, and that's absolutely fine as well. The important part is that it looks similar to how an x cubed graph should look, and we're really accurate with going through those coordinates. So there we go, there is our x cubed graph. Now you can also have to plot reciprocal graphs. A reciprocal graph is where we have a fraction involved, like this up here, where we are dividing by x. Now they're quite nice to draw because a lot of the time the divisions that we have to do aren't overly complex. If you look at the table that we have though, you can see it goes up by different amounts. It starts by going up by 0.5 and then it continues to go up by 1. So it doesn't really matter which side we start here, as we only tend to plot the positive region. So to start with, for this one here, if we start on the left, we've got 3 divided by 0.5. When you divide by 0.5, it just doubles the answer. So 3 divided by a half is 6. A few have been done for us. Here we have 3 divided by 3. 3 divided by 3 is just 1. Here we have 3 divided by 5. 3 divided by 5, you could type into your calculator, but it is a decimal, or you could convert it over 10 just to help you write it as a decimal. That would be 6 over 10. 6 over 10 is 0.6. And then for the last one there, we have 3 divided by 6. That is the fraction 1/2, and that can be written as 0.5. Of course, those last two there aren't the nicest, but most more than likely you would have a calculator for one of these, but if you don't, there's a method that you could take. We can now plot these points on the graph, being careful because 0.5 is down here between 0 and 1, so that's 0.5. The rest are on whole numbers, but that one there we just need to be careful. That goes up to 6, then 1 goes up to 3, 2 goes up to 1.5, so being careful we're in between 1 and 2 there. 3 goes up to 1, 4 now goes up to 0.75, which is going to be very difficult for us to draw. You could, just to help you, label the halfway point over here, so 0.5. You know now it's pretty much in the middle. Obviously, you can only be as accurate as you can see. If it's difficult to see, it's difficult to get it any more accurate than that. It might help to draw the last one first. We can see where halfway is, and then the 1 and the 5 is just in between those previous two, so somewhere around there. Again, we're only going to do our best to be as accurate as we possibly can, but with numbers like that, it's very difficult to get them absolutely perfect. Now again, a reciprocal graph, similar to that of a quadratic and a cubic, we join it together using a nice smooth curve. So I'm going to come down, doing 1 point at a time, trying my best to make it a nice curve. If you do make a mistake, obviously you've done it in pencil, so you can rub it out, you can go again. The really important point is that it's a nice curve, and it goes through each of these points perfectly. So there we go. There would be our nice curve. That is a reciprocal graph. We don't tend to draw the negative part of a reciprocal graph, because a reciprocal graph does look like this in the positive region. In the negative region, it goes down to here. So a full reciprocal graph can be really difficult to actually plot. So it tends to be that we only tend to look at this particular region here, where we are plotting the positive part of that reciprocal graph. Now, when it comes to simultaneous equations, the method that I use is I look at the coefficients of y. So when we have simultaneous equations, we need one of the coefficients to be the same. But the method that I use, I look at the coefficients of y. You may have learnt to do these where you look at the coefficients of x. If you do that, that's absolutely fine. But I just think it's a lot nicer to look at the coefficients of y. Now, I always start by labelling these equations. So I'm going to call this equation 1 and equation 2. I want to make the coefficients of y the same. So for 4 and 5, I could make them both into 20, which means I need to times the top equation by 5 and the bottom equation by 4. Once we have a coefficient which is the same, we can eliminate that coefficient by either adding or subtracting the equations, which we'll obviously talk about. So for the top one, if I times it by 5, 2x becomes 10x, the 4y becomes minus 20y, so we've got minus 20y, and the 19 becomes 95. 5 times 10 is 50, 5 times 9 is 45, so 95 in total. For the second equation, 3 times 4 would give us 12x. The 5y we already know is going to become 20y, that was the whole point, and 1 becomes 4. Now when you have these, where we have now a similar coefficient on both, I look at the symbols with that coefficient. So if the symbols are the same, we do same signs subtract. And if the symbols are different, we do different signs add. So in this particular case here, the signs are different. So we will add these two equations together. Now typically, if you look at these two coefficients at the start, more often than not, those coefficients are always going to be the same. So you will always subtract the equations, even if the symbols are different in the y coordinates or in the y coefficients there. So here I do have different signs, so I'm going to add these equations together. 10 plus 12x will make 22x. Negative 20 add 20y will become 0, so they disappear, that's the whole point of what we are doing. And then adding the 4 onto the 95 gets us 99. So here we can now solve for x. We now have a nice equation which does give us a not so nice answer here because 99 doesn't divide perfectly by 22. Now typically, questions like this, you would normally have a calculator if the answer does come out as a decimal, but that doesn't mean that you have to have this using a calculator. So if you don't, you will have to write it as a fraction, 99 over 22, or 99 divided by 22. Now if you do have a fraction, you just need to look and see can you simplify it, because we're going to need to substitute this back in to find y. Now 99 and 22 both divide by 11. So a good way to simplify this would be to divide them both by 11 and we get 9 over 2, and that's a much nicer fraction that we might be able to write as a decimal. 9 divided by 2 is 4.5, so we could write that as 4.5, and that's our value for x. Now with simultaneous equations we also need to find the value of y. We found the value of x, so we could put that onto our answer line. We've got x is equal to 4.5. We now just need to know what y is equal to. So pick one of the equations. Typically, if I have an option, I will always pick the equation that has the positive symbol in it, just to avoid using any negatives, but you can substitute into either equation. I tend to write what I'm doing, so I'm going to write sub x equals 4.5 into, and I have chosen equation 2, which I have labelled, so that makes it really clear what I'm doing. Now that means I need to do 3 times 4.5, as it's 3x, and then we have plus 5y, and that is equal to 1. So this isn't going to be very nice here, but I can work out 3 times 4.5. 4.5 add another 4.5 is 9, as we already know, because that was half of 9 that we got. And then adding another 4.5 would get us to 13.5. Obviously you could add those three together, but we get to 13.5. So we have 13.5 plus 5y is equal to 1. Here we have a number at the start, so we need to get rid of this number from both sides, just solving an equation like we normally would. So minus 13.5, and we get here that 5y is equal to negative 12.5. Now straight away, as soon as I see that, this does stand out as a very clear calculator style question. So this would be very difficult, it would certainly be a not very nice question at all to appear on a non-calculator paper. So typically this sort of question is more a calculator style question, because now we need to do negative 12.5 and divide that by 5. And that wouldn't be very nice to do without the calculator. So I'm going to type it into the calculator. We do get y is equal to negative 2.5. If you didn't have a calculator, this would be really horrible to do. To be fair, you could leave your answer at this point as negative 12.5 over 5, but you would probably want to simplify that. So we could think, well, the top and bottom do both divide by 2.5. That's not very nice at all, but 2.5 goes into 12.5 5 times. Obviously, it's negative on the top there, so it's negative 5, and it goes into 5 twice, so negative 5 over 2. 5 does divide by 2, it becomes 2.5. So we do get y is equal to negative 2.5. So a very difficult version of a simultaneous equation there, but if you can solve that one, or at least be happy with the steps there, even if you are at a point where, steps like this here, that's really, really horrible to come up in a simultaneous equation. You've got the steps like this, where it simplifies down to 4.5. If those are the bits that you're not liking, but the process you're actually okay with, then you can probably solve any simultaneous equation because it doesn't get any harder than that. So looking at another simultaneous equation, this one here, again, we have different signs, but you can see here that these coefficients at the start are actually the same. So you could just go about subtracting these equations straight away. But I do tend to still focus on those y coefficients. So here, I'm going to label them 1 and 2, and in this scenario, the top equation there can just be multiplied by 4, which makes it have a 4y, which is going to match our negative 4y below. So if we do that, we would have 12x plus 4y, and this time we have negative 4 at the end, so we get negative 16. Now the bottom equation this time, we don't actually have to change it. We can leave it as it is because it's got that 4y. So we have two equations with different signs in front of the same coefficients, so we will add these equations together. When we add them together, we get 15x is equal to negative 16, add 6 is negative 10. So again, we've got quite a horrible sort of solution going on with this question as well, because 15 doesn't fit into 10 perfectly. So if we divide by 15, we get negative 10 over 15. And notice as well how I've dropped the negative symbol off the fraction there. It doesn't have to be on the top or the bottom, you can put it out of the fraction. This one's not too bad. We can divide the top and bottom by 5, which does give us at least a fraction which doesn't look awful to substitute in. 5 goes into 10 twice, and it goes into 15 3 times. So our value of x is negative 2/3. So x is equal to negative 2 over 3. Again, now we have an x value. It's not the nicest to substitute in, but we're going to sub it into one of the equations. So I'm going to sub x is equal to negative 2/3. I'm going to pick an equation. Let's just go for equation 1. It doesn't really matter here. Equation 2 has a takeaway in. Equation 1 has a negative 4 at the end. Neither of them are going to be easier than the other. So let's just sub it into equation 1. Now, we do have 3 multiplied by negative 2/3, because we have 3x plus 1y, and that is equal to negative 4. So we need to work out 3 times 2/3. I might just do that to the side. That's 3 over 1 times negative 2 over 3. So I've just put a 1 underneath the 3. It's just going to help me to times the top times the bottom. So 3 times 2 is 6. 1 times 3 is 3, and it was negative. So negative 6 divided by 3, and that is actually negative 2. 6 divided by 3 is 2. So that part there just becomes negative 2 plus y, which is equal to negative 4. Now, again, you can either maybe look at that and think, well, what do you have to add to negative 2 to make negative 4? It has to be a negative. Or you could just add 2 to both sides of the equation, and you get y is equal to negative 2. So there we go, we've got y is equal to negative 2. Again, we've got 2 solutions there for x and y, neither of them being particularly nice. Obviously, a simultaneous equation that just has all positive solutions or positive integers, they're the nicest types to solve, but it is very common now that you are going to get negative or fractional solutions, and if you do, obviously we've gone over 2 of possibly the worst questions that you could have in order to practice those. Now, when we have shapes where we have algebra on the shapes, we are going to be looking at forming and solving an equation. This is a relatively unique one here, but we are given a rectangle where we are given 2 opposite sides but with different algebraic pieces. And then we also have a y on the top. It says here all measurements are in centimetres and the area of the rectangle is 48 centimetres squared. Show that y is equal to 3. Now that line there where it says to show that y equals 3 is really important. If we're going to show that y equals 3, we can't put 3 up here and then use that as part of our working out, because that wouldn't be showing it's 3, that would just be assuming it's 3 and then using it to prove that it is 3. But here, what we need to do now is essentially keep that as y. We're going to try and figure out what y is, and if we show that it's 3, then we will have shown it. Okay, so we're not going to use it at all. We're going to imagine that the question never even told us this, and we're just going to go about working it out. So the first thing, there are a couple of ways that you could make an equation. So either if the area is 48, well, we know that length times width is 48. So potentially we could do the length times the width and say that that is equal to 48. The problem is we have 2 letters involved and we want to avoid that at all costs. Obviously we can do that if we have simultaneous equations, but we are just looking for an easier route on this particular question. So if we can avoid that, that would be great. But here we do have these 2 lengths which we know are equal, but we've been given 2 different algebraic expressions. So what we could say is we know that 2x plus 6 is equal to 5x minus 9. We now have an equation with x on both sides. It only has one unknown in it, obviously on both sides, but just the one x, and we can actually go about solving that now. When you have an x on both sides, we want to get rid of the smallest x from both sides. So we'll get rid of 2x. That would leave us with 6 is equal to 3x minus 9. We want to isolate the x's, so we can move the 9 to the other side, and we get 15 is equal to 3x, leaving us with a nice equation to solve. We can divide by 3, and we get 5 is equal to x. Or of course you could write x is equal to 5. We can now use that to find the length of the rectangle. So over here, if we have 2x plus 6, well, if x is 5, that's 2 times 5 plus 6. 2 times 5 is 10, and 10 plus 6 gives us 16. So we know that the width of the rectangle, or the length of the rectangle, is 16. Now we can look at this information where it told us that the area is 48. We know that the area of a rectangle is the length times the width. So if the area is 48, if we divide that by the length of 16, that would tell us what the width is. And 48 divided by 16 is equal to 3, and therefore y has to be equal to 3. So there we go, that we have shown it. We have shown by forming an equation how we have found the value of x. We have shown on the left there how we have found the length of the rectangle being 16, and then we've shown how that means the width or the length, which however you want to refer to that, has to be 3. Of course, you could have subbed the x equals 5 into this length as well. You'd have just got 5 times 5 and then take away 9. And 5 times 5 is 25, take away 9 is also 16. So it didn't matter there which length we used to actually find that. So there we go, that is some forming and solving equations. Forming and solving equations can be one of the hardest topics that we actually look at, purely because they are some quite difficult problems. Here is a good example where we have 2 rectangles and it says all measurements are in centimetres. It says the area of rectangle A is equal to the area of rectangle B, and then tells us to work out the perimeter of rectangle B. Well, here we don't actually know any expressions for the area, but because they're rectangles, we do know that we can do the width times the length, or the length times width, to find the area of a rectangle. So for rectangle A, we can do 4x times 2.5. For rectangle B, we can do 2x minus 3 and multiply it by 7. And we know that they're then going to be equal to one another. So if I do these to the side, we've got 4x multiplied by 2.5. 4 times 2.5 is 10, so that would be 10x. For the other rectangle, we have 2x minus 3 times 7. Now if you're going to times something like that, 2x minus 3, by a number, typically we would write that using a single bracket. So 2x minus 3 multiplied by 7, 7 times 2x is 14x, and 7 times 3 is 21, keeping the symbol the same. So that would be our expressions for the area. Now it says here, the area of rectangle A is equal to the area of rectangle B. So we can write an equation now where we say, okay, well, the area of one is equal to the area of the other. And now we have actually formed an equation. We can now just go about solving this. So it's up to you what you do first. Typically, I would get rid of the smallest x from both sides. If we do that, it is a little strange though, because when we take away the 10x from both sides, we end up with 4x minus 21 is equal to 0. That's absolutely fine though, because now we can add the 21 onto the 0 to isolate the x's. We get 4x is equal to 21, and now we actually need to go about solving this and dividing it by 4. So typically this looks like it would be a calculator question, just because that's not a very nice division to have to do. But if we divide by 4 at this point, we get x is equal to 5.25. So not the nicest of x values to have, but we haven't even finished, because this question wants us to work out the perimeter of rectangle B. So rectangle B is obviously this rectangle here. We know now that x is 5.25. Now thankfully, on this particular rectangle, we also know that this length is 7, which means over here must be 7 as well. So we just need to find the length of 2x minus 3. That's going to be the same as the bottom. So we just need to work this out by substituting x is 5.25 in. So we've got 2 times 5.25 and then take away 3. 2 lots of 5.25 is 10.5 minus 3, and minusing 3 from 10.5 is going to equal 7.5. So the top there is 7.5 and the bottom as well is going to be 7.5. So we now have our 4 values, 7, 7, 7.5 and another 7.5. So for the perimeter, we just need to add them all together. So 7 plus 7 is 14, 7.5 and 7.5 is 15. So 14 plus 15 gives us 29. It did say all the measurements were in centimetres, so 29 centimetres would be our final answer for that one. And there we go, that is forming and solving an equation, and that is a very difficult version of forming and solving equations. Okay, that is the end of the video, so we have gone through every question in the Ultimate Revision Guide. Hopefully that was useful and helpful. Obviously at any point you can download the guide if you haven't already. You can refer back to the questions, you can go into the chapters in the video to access any particular unit or any particular question to go through at your convenience whenever you would like to. But hopefully that video was useful and helpful, and hopefully I will see you for the next one.